Hello friends, welcome to GATE Academy. I am Yogesh Tyagi and I am going to discuss complete revision, quick revision about heat and mass transfer. So whether you are a mechanical engineer or you are a chemical engineer can also join. We will take approximately 5 to 6 hours to just complete this quick revision. You just go through we will just not discuss each and everything in the deep. We will just discuss each and everything what is required in case of the GATE or other PSU exams which are coming. So you just have to see the video and just revise it, and after revising just solve the problem. You will be able to, if you have studied the heat and mass transfer, then definitely you will be able to solve approximately 95% problems. And if you have not studied the heat transfer previously, then at least you will solve 50 to 60% problem in the heat transfer. So we will just take a quick revision and discuss each and everything. I'll just write the formulas and basic topics and just dictate them. I'm not going to just teaching you, I'm just dictating and giving you the complete revision. So let us start the heat transfer, and one by one. First we will take the conduction. First topic is conduction, then we will start convection, then we will do radiation, and after that we will do heat exchanger. Heat exchanger. Conduction is little bit large topic. In the conduction we will first study about basic. First topic is basic concept. We will start from the basic concept. And in the conduction you will first study 3 cases. One is wall, another is cylinder, third one is sphere, and after that we will start fins and unsteady state. Fins and unsteady state, we will first study unsteady state, then we will start fins. And in the convection, after that radiation and heat exchanger. So it's a very I think you are aware with this. I think the weightage of the heat exchanger is 8 to 9 marks, whether you are a mechanical engineer or you are a chemical engineer. So the weightage of the heat transfer is very high. You just have to seriously listen this video, and if you like the video, just hit like over there. So let us start the heat transfer from here. So now let us start from the chapter 1. Chapter 1 is basic concepts, and initially we will start from the very basic. We say simply thermodynamics. What is thermodynamics? Thermodynamics deals with the systems in equilibrium. That is, to bring the system from one equilibrium state to another equilibrium state, how much heat is going to be transferred. In the thermodynamics, you have studied that it will deal with the 2 systems in equilibrium. That is, to bring the system from one equilibrium state to another equilibrium state. Definitely, if one system is at temperature T1, another system is at temperature T2. So to bring this system or this system from this equilibrium state to another equilibrium state, how much heat is going to be transferred, that we have discussed in thermodynamics. And in thermodynamics, similarly, if I just talk about the heat transfer. So heat transfer deals with the rate of heat transfer. Means to bring the system from one equilibrium state to another equilibrium state, at what rate the heat is going to be transferred. So in case of the heat transfer, we deals with the rate of heat transfer. In thermodynamics, we deals with the amount of the heat transfer, and in case of the heat transfer, we deals with the rate of heat transfer. For example, you can say, in case of the car radiator, let's suppose we have to design a car radiator, then definitely to remove the heat from the engine, piston cylinder arrangement, to remove the heat from the engine, what will be the size of radiator? What will be the size of radiator? It will be decided what? It will be decided by the rate of heat transfer. At what rate the heat is going to be transferred, the type of the radiator we needed. So heat transfer, the simple concept behind the heat transfer is we just need the rate of heat transfer. So at what rate? For example, if we have a fan, if we are designing a fan, then definitely we have to know first that at what rate we have to remove the heat from the room. Or if we are designing a AC, at what rate we have to remove the heat from the room. AC, cooler, whatever, or electronics devices. We have written, for example, radiator, for example, air conditioner, for example, electronics devices. Let's suppose you have seen your TV. So in case of the TV, you have seen some small hole at the back side of the TV. These holes are due to remove the heat which is generated due to electricity passing through your TV circuit. So heat transfer, the simple concept behind the heat transfer is that at what rate the heat is going to be transferred, or at what rate the heat we have to transfer. Now, so in case of the heat transfer, we will use the basic concept. That basic concept is what? Thermodynamics, first law of thermodynamics, that is heat loss. If I just take a container, we have a container like this, and in this container, let's suppose a water, and water is at temperature T1. So from here we can see, let's suppose we have a steel block, and we are just putting this steel block into this water. After putting this steel block into this water, if the temperature of the steel block is greater than the temperature of water, then definitely the temperature of water will rise. So from the first law of thermodynamics, we can easily say that heat loss by this block will be equal to heat gain by this water. So in case of the thermodynamics, we have already studied that the heat loss is equal to heat gain. Now the question behind this, in case of the heat transfer, they will simply ask you at what rate the heat is going to be transferred. So we are taking a complete revision of the heat transfer. So one by one, we will take one by one all the formulas and all the concept behind this. Now coming to the, so we can easily say, in case of the thermodynamics, we have studied the first law of thermodynamics and we deal heat in joule or kilojoule. But in heat transfer, we cannot deal this heat in joule or kilojoule. We deal in what? Joule per second or kilojoule per second. Joule per second is known as watt, kilojoule per second is known as kilowatt. So it was the basic concept behind the heat transfer, that heat transfer deals with the rate of heat transfer. In any of the furnace, like let's suppose you are taking a furnace, with the principle of thermodynamics, you will just study that how much amount of heat is transferring through the furnace. But with the principle of heat transfer, you will be able to tell at what rate the heat is going to be transferred. So that's why we have studied heat transfer. Initially, we have studied the thermodynamics, but after studying the thermodynamics, what was the need to study the heat transfer? So it's a simple solution. Why we are studying this heat transfer? Since we need the rate of heat transfer. At what rate? Let's suppose if we have a cup of coffee. So in case of the cup of coffee, with the help of the thermodynamics, you can easily tell that the coffee will transfer heat to the environment. But with the help of thermodynamics, you are not able to tell at what rate or how much time it will take to reach at the environment temperature. It is calculated by the heat transfer, principle of heat transfer. So that's why we are going to study this heat transfer. Now coming to the heat transfer, before studying heat transfer, whenever you have studied, what are the tasks? Simply they will ask you, what are the tasks of a design engineer? What are the tasks of a designer? If I just discuss the task of a design engineer, whenever you are going to the industries, so in industries, the first task they will give you in the designing process, let's suppose steam is flowing through the pipe, and if the steam is flowing through the pipe, definitely the pipe will start losing heat from the steam. And if pipe will start losing heat from the steam, then it is obvious you have to stop this losing amount of heat. if you want to stop this amount of heat to lose from the pipe, what you will do? You will just start insulating the pipe. So, one question he may ask you, that at what thickness the rate of heat transfer is minimum. I am not discussing about the critical thickness of insulation. We will discuss critical thickness of insulation later on, but I am just discussing what are the tasks when a design engineer, when you will be selected in the companies, and in the companies what are the questions they will simply ask you. One question they will ask you, that if we are just losing this amount of heat, then what will be the thickness of insulation? If we are restricted to lose this amount of heat, then what will be the thickness of insulation? It is obvious when you start wrapping the pipes, then definitely they are just saying the thickness of insulation. If you are start increasing the thickness of insulation, then definitely from here the heat loss will be reduced. So, one question they will ask you simply from here, if a steam is flowing through the pipe, what will be the thickness of insulation when the rate of heat transfer is this, rate of heat losing is this. Second question they may simply ask you, let the water is flowing through the tubes. If water is flowing through the tubes, they will simply ask you, let us start heating this tube. If I just start heating this tube, one question they may ask you, if the length of the tube is given, then what will be the exit temperature? What will be the exit temperature? And second question they may ask you, if the exit temperature is given, that we are required, this is the exit temperature, then definitely what will be the length of the tube, minimum length or maximum length of the tube, so that the exit temperature is this. So, the second work in the industries will be like this when you are a design engineer in case of the heat transfer industry. Now, coming to the third part is from electronics devices. Let you are insulating some electronics devices and let's suppose electrical wires. If you are insulating, then definitely you have to know that what amount of thickness of insulation should be, so that the rate of heat transfer will be minimum or maximum, whatever you are going to design. So, when we start the heat transfer, so heat transfer is a very basic subject, it is just an application of thermodynamics. So, we will start from basic. What we have studied the thermodynamics, and we are just going to study the advanced version of thermodynamics. So, in case of the thermodynamics, we have studied that Q should be in joule or kilojoule, that is to bring the system from one equilibrium state to another equilibrium state, how much heat is going to be transferred. Now, coming to the heat transfer. So, in the heat transfer we study what? We study that at what rate the heat is going to be transferred. Similarly, when you will become an engineer, then definitely, or they will ask you the questions in interviews or whatever, let's suppose they will simply ask you the problems in the exam. They will simply ask you the problems from the three sections. One section is what? When a steam flowing through the pipe. Another section is what? Water flowing through the pipes. And third section is electronics devices. So, these are the three sections they will simply ask you. Now, coming to the next part is what? We are just studying the basic concepts. It is a very basic chapter. After that, we will start the heat transfer. So, in case of the basic concept, first we need to know, let's suppose heat transfer is taking place from this, heat transfer is taking place from this, and heat transfer is taking place from this. The question arises that at how many modes the heat is going to be transferred. So, what are the modes of the heat transfer? First, we will have to discuss that what are the modes of heat transfer. So, we can say easily the modes of heat transfer are, it can be by conduction, it can be by convection, it can be by radiation. So, heat transfer can take place by conduction as well as convection as well as radiation. So, now coming to the first part, we will discuss one by one conduction and convection. Now, coming to the first part, that is conduction. So, I think you all are aware with the conduction. Conduction is what? It is the mode of heat transfer which generally takes place in solids due to temperature difference by molecular lattice vibrational energy transfer and also due to free electrons transfer. What I want to say, we are just discussing the modes of heat transfer, and in case of the modes of heat transfer, we have three modes of heat transfer. One is conduction, second one is convection, and third one is radiation. So in case of the conduction, we simply says conduction is the mode of heat transfer which generally occurs in solids due to temperature difference, due to temperature difference and due to molecular lattice vibrational energy transfer and also due to free electrons transfer. Why he is just saying molecular lattice vibrational energy transfer? Since in case of the solids, you are easily aware with this that the molecular distance between the molecule is very, very small. And if the molecular distance between the molecule is very, very small, so we can easily say these molecules cannot run like this. If they cannot run like this, it means they will vibrate at their place when they have the energies. And due to vibration, they will transfer their energy to the further molecules. What I want to say, over here, the molecule will not run like the liquid molecules or solid molecules. They will simply vibrate at this point, and due to vibration, they will transfer the energy to the another molecule. And another molecule will transfer to the energy like this, and again they will transfer. That's why the vibrational energy transfer is very, very less. In case of the solids, vibrational energy transfer is how much? It is 30%. It is 30%. And due to electrons means for a solid, if I just take a solid, in case of the solids, the heat transfer also takes place due to these free electrons. Means the motion of the free electrons will decide the rate of heat transfer. And due to free electrons, the rate of heat transfer is 70%. 70% of the total heat transfer is taking place by the free electrons transfer. Means from here it is obvious. In case of the solids, if the free electrons are more, it means the rate of heat transfer by the conduction, free electrons are more, so it means the rate of heat transfer by the conduction will be more. It is obvious. It is obvious. So in case of the solids, there are two modes of the heat transfer. One is free electrons transfer and another is molecular lattice vibrational energy transfer. And the heat transfer due to this free electrons is known as electronic conduction. Electronic conduction. And heat transfer due to these lattice vibrational energy transfer of the molecule is known as phononic conduction. So try to remember, they may ask you in the PSU's exam, like Coal India is very near to you. If Coal India is very near to you, they can ask you simply the question, the rate of heat transfer by the free electrons is known as, it is known as electronic conduction, and rate of heat transfer by free vibrational energy transfer is known as phononic conduction. You just have to simply remember this. Now, it means the molecules the solids or the metals on which number of free electrons are more will be a good conductor of heat. So from here we can easily say the material which is good conductor of electricity will also be a good conductor of heat. Simply we will say, if number of electrons are more, it means it will be a good conductor of electricity. So if it is a good conductor of electricity, then definitely it will be also a good conductor of heat. So from here it is obvious, the solid which is good conductor of electricity will also be a good conductor of heat. If it is a good conductor of heat, and in this there is a notable exception. An exception is what? Diamond. Diamond is very good conductor of heat, but it is a bad conductor of electricity. Due to what I want to say, in case of the diamonds, heat transfer takes place very fast, since conductivity is what? It is 2300 watt per meter Kelvin, but it is not a good conductor of electric. That's why we will say all the material which are good conductor of electricity will also be good conductor of heat. A notable exception in this is diamond. Diamond is a very good conductor of heat, but it is not a good conductor of electricity. So you have to remember the conductivity of the diamond. They have asked you so many times. Conductivity of the diamond is 2300 watt per meter Kelvin or watt per meter degree Celsius. So you have to remember like this. Now you also have to remember some of the metals like silver. Conductivity of the silver is 405 watt per meter Kelvin. Conductivity of the copper is 385 watt per meter Kelvin, or gold is 310, aluminium is 204, steel is 17 to 45. Sometime they may ask you in the increasing order or decreasing order, or he may ask you if the conductivity of this material is this, or he may simply give you the comparison, the rate of heat transfer from which material will be more. The material whose conductivity is very high, the rate of heat transfer will be very high, definitely. So you just have to remember in this manner that the silver, copper, gold, aluminium and steel. It is 405, 385, 310, 204 and 17 to 45. You just have to remember, formula unit is simply watt per meter Kelvin or watt per meter degree Celsius. You just have to remember the units also. I have not written the units since there is no need. So these are, one is diamond, conductivity of the diamond is 2300, and another is silver, copper, aluminium, gold, steel. So you have to remember in this fashion only. Now coming to the next part we can say we have discussed the metal part. The metal in which number of free electrons are more will be a good conductor of heat. Means the metal which is good conductor of heat will also be a good conductor of electricity or vice versa. But an exception is what? It is diamond. Now coming to the next part, in case of the non-metals. So non-metals are two types. One is known as crystalline, another is known as amorphous. So in case of the crystalline, why we say them as crystalline? We say them crystalline as they have perfect crystalline structure. For example, we can say K of the diamond. For example, we can say diamond, and conductivity of the diamond we have written, we have already studied. Diamond has a perfect crystalline structure. That's why the conductivity of the diamond is very high. Now coming to the next point, in case of the amorphous materials, amorphous material will have imperfect crystalline structure. For example, you can say glass. In case of the glass imperfect, there will be an imperfect crystalline structure, that is, you can say impurities will be more. And if there are lots of impurities, it means you can say conductivity of the glass is very less, that is 0.75. You just have to remember only one thing. If the conductivity is more, it means material is more pure. If the conductivity is less, it means material is impure. So as impurities decreases, it means conductivity increases. As impurities increases, it means conductivity increases. So now coming to the, you also have to remember in case of the amorphous material, one more material is PUF, polyurethane foam. Polyurethane foam, the material which used in the walls of fridges. In the walls of the fridges to just avoid the rate of heat transfer into the fridge, we use the material. That material is known as PUF, polyurethane foam. You just have to use polyurethane foam. Urethane foam. So it's a material which name is polyurethane foam. Now coming to the next point. So we have some other materials like freon gas. We may ask you the conductivity of the freon gas. Freon gas conductivity is 0.0083. Another material is graphene. Sometime they may ask you about the graphene. It's not graphite. Graphite conductivity is approximately 1100 and graphene has a conductivity of 5000. Now next material is copper crystal. You may confuse. It is not copper. These are the copper crystals. So copper crystal has the conductivity as 8000. So you just have to make an idea about the conductivities. They will simply ask you one problem in the PSUs that what is the conductivity of the material is. So these are the some conductivities I have given you 1, 2, 3, 4, 5, 6, 7, 8, 9 and these are glass I have also taken 7, 8, 9 almost 10 to 12 conductivities. So you can remember these conductivities and easily when you will sometimes they may not give you the value of conductivity in the problems, then you have to remember these. So please remember this. And one more thing is what the question comes in our mind is whenever you are discussing the modes of heat transfer and we have taken the first modes of heat transfer, that is conduction. So in case of the conduction we says conduction is the mode of heat transfer which generally occurs in solids due to temperature difference by molecular lattice vibrational energy transfer and also due to free electrons transfer. Now the question behind this is why the heat transfer takes place, and heat transfer into the materials takes place due to a property which is known as conductivity. And we have given the conductivity for just diamond and other materials like this. Now just one more thing, let us define the conductivity. Sometime you may confuse. Conductivity is a simple thermophysical property. Why I am saying thermophysical property? It depends on the temperature. Conductivity simply depends on the conductivity is a thermophysical property. It depends on the temperature. Now coming to the point, we can easily say we have studied the Q is equal to minus K into A into dt by dx. So I am giving you the two definitions of the conductivity. One definition I can say conductivity is a thermophysical property of material which allows the heat to get conducted through it. Conductivity is a thermophysical property of material which allows the heat to get conducted through it. What it means? Just saying it is a thermophysical property of material which allows the heat to get conducted through it, means to pass through it. If conductivity is more, it means heat will transfer, heat will pass fastly. If conductivity is less, it means it will not transfer fastly. So one physical definition is what? It is a thermophysical property of material which allows the heat to get conducted through it. And next, we can also define the conductivity like this. If we can say, if area is equal to 1 and dt by dx is equal to 1, then definitely we can say this K is equal to Q. It's a Fourier law of conduction heat transfer we will discuss. Initially, we are just discussing the basic concepts. So from here we can say if K is equal to Q, then we will definitely define Conductivity is the amount of heat transfer. Conductivity is the amount of heat transfer in a unit length per unit temperature difference per unit area. Conductivity is the amount of heat transfer in a unit length per unit temperature difference in a per unit area. So we will say it is defined as the amount of heat transfer in a unit length per unit temperature difference per unit area is known as conductivity. He will simply ask you amount of heat transfer in a unit length per unit temperature difference per unit area is known as. You have to remember it is a conductivity. It is nothing, it is conductivity. So one question they may ask you from here. Now coming to the next point, conductivity simply a function of temperature, pressure, density, porosity, moisture. Conductivity is a function of 5 properties. One is known as temperature, pressure, density, porosity and moisture. Where we can say we can say K also varies with the direction. We are just saying conductivity simply if we just asking the question like this, conductivity is a function of, it is a function of temperature, pressure, density, porosity, moisture. It is a function of 5 properties. Conductivity varies with the direction. If conductivity is independent of the direction, then it is known as the isotropic material. So in case of the isotropic materials, at any point means you can say like this, in case of the x direction, conductivity is Kx. In case of the y direction, conductivity is Ky. In case of the z direction, conductivity is Kz. So he is just saying the conductivity varies with direction. At a single point in 3 directions, conductivity is different and different. What he want to say, for isotropic materials, conductivity not varies with respect to directions. So for isotropic materials, K is not a function of x, y and z. You have to remember, for isotropic material, conductivity is not a function of x, y and z. Now coming to the next point, K also varies with position in a given direction. K also varies with position in a given direction, and these types of the materials in which K is varying with position, these types of the material are known as heterogeneous material. Heterogeneous material. Look, you have to remember conductivity is a function of. Conductivity is a function of pressure, temperature, density, porosity, moisture. First thing. Second thing you have to remember, conductivity varies with directions. If it is independent of direction, means these types of the material are known as heterogeneous material. And these types of the material are known as isotropic material. It is independent of direction. If it is independent of direction, then these types of the material are known as isotropic material. If conductivity varies with position in a given direction, let's suppose we are going in x direction, and in x direction if it is changing continuously K1, K2, K3 and K4 and so on, then we will say yes, conductivity is varying. If it is if it is varying in these types of the material, then these types of the material are known as heterogeneous materials. Now coming to the next point. So next point is what? We can easily write the variation. Let's suppose, let's see one more thing, that is variation of conductivity in solids. Variation in conductivity in solids. We will see one by one. So the first case is metals. In case of the metals, we say K is equal to K0, K1 plus K1T plus K2T square and so on. Let us take k naught as common. So 1 plus k1 by k naught t plus k2t square we have taken as common. So it is like this. If I just neglect the higher degree terms, we can write k is equal to k naught 1 plus alpha t. Now you have to remember one thing from here. You have to remember this alpha value is negative for metals and this alpha value is positive for alloys. Alpha value is negative for metals and this alpha value is positive for alloys. So for metals and alloys, we can easily write it is a case of definitely if the conductivity is varying like this. Let's suppose we are taking this as a constant conductivity case. Over here we can say if conductivity is increasing with temperature, if conductivity is increasing with temperature, then definitely it is a case of what? Alloys. So for alloys, you will simply say that the conductivity variation will be like this. And if the conductivity is decreasing with the temperature, then the graph will be like this. So simply he may ask you like this. This graph represent and this graph represent. This graph will represent what? K naught into 1 plus alpha t, and this will represent what? K naught into 1 minus alpha t. Simply, this is a case of alloys, this is a case of metals. Now the confusion is, in case of the metals we can say if alpha is negative, it means as temperature increases, conductivity decreases. And in case of the alloys, as temperature increases, definitely conductivity increases. And this K naught, you have to remember this is the conductivity at 0 degrees Celsius. K naught is the conductivity at 0 degrees Celsius. Now the question is, why this is happening? Why conductivity of the alloys is increasing and conductivity of the metals is decreasing? The reason behind this, let's suppose we are simply saying we have a alloy and you are aware with this that alloy is a mixture of various materials. Let's suppose we are making an alloys. So in case of the alloys, it is obvious that there will be some asperities when we mix the metals, then definitely there will be some asperities. And when we start heating the alloys, then definitely asperities will decrease. Whatever the asperities, they will burn out. And asperities decreases, it means impurity of the alloy decreases. And if impurity decreases, purity gains, it means conductivity is increasing. The material which is more pure will have more conductivity. The material which is more pure, and hence you can easily say metals, whatever it is a single metal, it is already pure, and hence we can say for alloys as temperature increases, conductivity increases. For metals as temperature increases, conductivity decreases. So they will simply ask you the problems from here. Now coming to the next point, from here if he is just asking the graphical representation, you may simply ask, just let's suppose it is conductivity and it is temperature. So in case of the metals, you can easily say that conductivity is decreasing, and in case of the alloys, you can easily say the conductivity is increasing like this. Now, it is a case of solids. In case of the solids, you just have to remember the formula like this. K is equal to what? K naught into 1 plus alpha t. Alpha is positive for alloys, alpha is negative for metals. Now coming to the next point. From the next point, we can easily say, alpha is okay from here. Now coming to the next point is, let's suppose we have non-metallic solids. We are discussing about the solids. Let's suppose we have non-metallic solids. So in case of the non-metallic solids, conductivity is simply a function of porosity and moisture. Conductivity is simply a function of porosity and moisture. For example, we can say, let's suppose we have refractory bricks and red bricks. So one thing you have to remember, refractory bricks means the bricks which are using in furnace, and red bricks, the bricks which are using in home appliances. So red bricks have the more moisture as compared to refractory bricks. Simply the concept behind is what? As moisture increases, conductivity increases. As porosity increases, conductivity decreases. Why is just saying? Let's suppose we have a brick like this. Let's suppose we have a brick like this. If we just saying you are making porous, you are making this brick as porous. So it means what do you want to say? If it is porous, it means these holes will contain air, and definitely this air will have the conductivity less than as compared to conductivity of this brick material. Since the brick material will have the conductivity approximately 0.9 and air has conductivity what? 0.021, approximately 0.021. So it is obvious, when you are just making holes or making porous the bricks, then definitely the average conductivity of the material will decrease, and hence we can say as porosity increases, conductivity of the material decreases. And in case of the moisture content, as moisture increases, conductivity increases. From here you have to remember one thing, it has less moisture, it has more moisture, means you can say K of the refractory brick will be less than K of red bricks. So in case of the red bricks, the conductivity is more. That's why you generally use these refractory bricks in case of the furnace, since in case of the furnace you don't want to lose the heat. But in case of the red bricks, you just want to pass the heat from the walls so that you can live happily in the homes. Now coming to the next point, we can say green buildings. Green buildings, for example, consumes less energy. Whatever the green buildings in which the moisture content is more, these types of the buildings consumes less amount of energy. And simply we can say, also we use the hollow bricks to decrease the rate of heat transfer. Why we use the hollow bricks? As conductivity decreases, definitely rate of heat transfer decreases. Since conductivity gives, it allows the heat to get conducted through the material. So it was just what we was discussing. We have started the complete revision from here, and initially what chapter 1 we have started from the basic concept. Basic concept, and I have just given you what I want to say. I have told you that thermodynamics only deals with the quantity of heat transfer, and heat transfer deals with the rate of heat transfer. We have just taken the first law of thermodynamics, which is like this, and we will use this first law of thermodynamics in further applications. Now, in case of the thermodynamics, we use Q as joule or kilojoule, and in case of the heat transfer, we use watt or kilowatt. For example, these radiator, air conditioner, electronics devices, these are made with the principle of heat transfer. So when you will just go to the industries. In the industries, they will give you the 3 tasks, or in the problems, they will ask you the problem from the 3 areas. One area is what? Steam flow through the pipes. Another area is what? Heat transfer to the water flowing through the pipe tubes. And third one is heat transfer through electronics devices. Now we have discussed the modes of heat transfer, and we have discussed the three types of the modes of heat transfer: conduction, convection and radiation. After that we have started the conduction. So in case of the conduction, I had told you it is a mode of heat transfer which generally occurs due to temperature difference by molecular lattice vibrational energy transfer and also due to free electrons transfer. From here we have observed that the material which have large number of free electrons, means which is a good conductor of electricity, will also be a good conductor of heat. But an exception in this case is what? Diamond, whose conductivity is what? 2300 watt per meter Kelvin. So it is a very good conductor of heat, but it is not a good conductor of electricity. It will work as an insulator in case of the electricity. Now from here we can see, you have to remember these conductivity values. They will have simply asked in so many exams, the conductivity is like this. Now coming to the next point, in case of the non-metals, we have taken the two types of the crystalline and amorphous. In case of the crystalline, they have the perfect crystalline structure, for example diamond or copper crystals you can say, and in case of the amorphous, imperfect crystalline structure. You just have to remember the conductivity of these materials, and after that we have defined the conductivity. Conductivity has the two definitions. One definition is what? It is a thermophysical property of material which allows the heat to get conducted through it. Second one, I have told you, it is the amount of heat transfer through a length or through a width per unit temperature difference per unit area. It is also known as conductivity. Now coming to the point, conductivity I have just given you, it is a function of temperature, pressure, density, porosity and moisture, and after that we have just given you K varies with the direction. If it is independent of direction, then this types of the material is known as isotropic material, and also K varies with the position in the given direction, and these types of the material are known as heterogeneous material. So we have discussed, after that we have discussed the variation of conductivity in solid metals. So solid, and in the solids we are seeing the first case, that is metals. So in case of the metals, conductivity varies with temperature. So in case of the pure metals, as temperature increases, conductivity decreases, and in case of the alloys, as temperature increases, impurities decreases, purity increases and conductivity increases. So we have discussed this, and this K naught is the conductivity at 0 degrees Celsius. You also have to remember this graphical representation. It is like this. This is for alloys, this is for pure metals, and also this graphical representation. Now we have also discussed the non-metallic solids. Non-metallic solids are like this. In case of the non-metallic solid, this conductivity varies with the porosity and moisture. Refractory bricks and red bricks. We have taken the two types of the bricks. These have the less moisture and these have more moisture. That's why I have told you the red bricks will have more moisture. It means they have the more conductivity value as compared to refractory bricks. So from here we have seen that as moisture increases, conductivity increases. As porosity increases, conductivity decreases. That's why we make the porous walls, to decrease the conductivity, to decrease the rate of heat transfer. And in case of the green building, when we use the green building to consume less amount of energy. Now coming to the next topic. So the next topic is variation of conductivity in liquids. So in case of the liquids, conductivity varies according to the formula K is equal to AC rho to the power 4 by 3 upon m to the power 1 by 3. Here A is nothing, it is a constant whose value depends on the molecular velocity. You have to remember, they will simply ask you in this formula, A is what? It is a constant whose value depends on molecular velocity. C is nothing, it is specific heat, and rho is density, m is molecular weight. So from here it is obvious, as density varies, this A is a constant, specific heat is constant, molecular weight is constant. It means this K is directly proportional to rho to the power 4 by 3. And from here we are obvious that rho is a function of pressure and temperature. And we all are aware with this, rho is equal to mass upon volume, and as pressure increases, volume decreases, overall value decreases for a fixed mass system. And if overall value decreases, it means density decreases by increasing the pressure. And as temperature increases, definitely density can be written as mass upon volume. As temperature increases, volume increases, overall value, as pressure increases, this volume will decrease, and if the volume will decrease, it will just increase. So by increasing the pressure, density will increase. And from here we can write as temperature increases, volume increases, and this value will decrease like this. So from here it is obvious, we can say, in case of the liquids, as temperature increases, density decreases, means conductivity decreases. And as pressure increases, density increases, conductivity increases. So in case of the liquids, we can say, K is directly proportional to pressure and K inversely proportional to what? Temperature. As temperature will increase, conductivity will decrease. As pressure will increase, conductivity will increase. We can see from here. Now, this just whatever the formula we are using, in case of the liquids, we have some notable exceptions. We says in case of the liquids, as pressure increases, conductivity increases, and as temperature increases, conductivity decreases. But we have two notable exceptions. One is water and another is glycol. In case of the water, in other liquids, in general liquids, we says as temperature increases, conductivity decreases, as we have studied. But in case of the water and glycol, as temperature increases, conductivity also increases. As pressure increases, conductivity decreases. It will be just opposite. In case of the water and glycol, they will behave different from the other liquids in that case. So we have to remember these two exceptions. Now coming to the next part. Next part is what? It is the variation of conductivity in gases. Dear, in case of the gases, we use the formula K is equal to 1 by 3 C rho into L into V. Just first we have to know C is nothing. C is the specific heat. Rho, you all are aware with this, it is density. L is what? It is mean free path. And V is nothing, it is the RMS velocity. And from here, if we can see, we can easily write this K will be a function of density, mean free path and RMS velocity. But in case of the gases, you just have to remember, let's suppose we have a gas cylinder, and in case of the gas cylinder, you can see as the density, as the gas comes out, it means the density decreases, and as the density decreases, the mean free path between the molecules increases. So it is obvious in case of the gases, this density is inversely proportional to mean free path. You can take a simple example of gas cylinder. In case of the gas cylinder, as molecules go away from each other, it means their density decreases and their mean free path increases. So it means from here we can write this conductivity is not the function of mean free path and density. It is a function of RMS velocity. Now first we have to know what is RMS velocity. RMS velocity is nothing, it is under root 3 RT by M, under root 3 RT by M. It can also be written as under root 3 PV by M. But you all are aware with this in the case of gases, as pressure increases, volume decreases, pressure decreases, volume increases, and this will remain same. So from here we can also write this conductivity is not the function of pressure, not the function of pressure. It is only a function of what? Temperature. As temperature increases, RMS velocity increases, and definitely conductivity will also increase. So from here we can write conductivity is directly proportional to Vrms, and Vrms we all are aware with this, it is 3 RT by M. So from here he will simply ask you the problems like this. For a gas, for two gases he will say, for two gases if they are different temperatures, find the conductivity of other gases. If he has given the two gases, they will give you the molecular weight, everything is constant, this 3R is constant. Now T by M. So from here K directly proportional to what? T by M. If K directly proportional to T by M, so from here you can write T1 by T2, T1 by T2 into, from here we will write M2 by M1. So if two gases are at different temperature, you can just get the comparison between the conductivities. Or he is just saying if two gases are at same temperature. If two gases are at same temperature, then you can compare like this. T1 is equal to T2, it will become 1. It means you can directly just compare from M2 by M1 under root. Or he may ask you for a single gas. If a single gas at different temperatures, if the temperature increases by 2 times, temperature increases by 3 times, or from here he may simply ask you, just arrange them in increasing order of conductivity. It may be he will give you S2, N2, O2, CO2 like this. He has given. So you all are aware with this, K directly proportional to what? Sorry, from here you can write K directly proportional to what? 1 by root M. So it means the gas whose molecular weight is more, conductivity will be less. So you can easily tell S2 molecular weight 2, it's 28, it's 32, it's 44. It means it has the lesser conductivity. Let's suppose it is K1, K of O2. From here you can write K of N2. From here you can write K of S2. K of S2. From here you can write K of O2 and then K of S2O, CO2 like this. So you can easily calculate from here. You just have to remember these formulas. He will simply ask you a comparison between the conductivities. A simple question from here he can ask you in the PSUs or in the GATE exam. Now coming to the next part, if he is just asking for a single gas, we will simply ask you the problem, let the temperature of the gas is increases by 2 times. If the temperature of the gas is increases by 2 times, it means conductivity will be what? 1 by root 2 times. So K1 is equal to root 2 times of K2 like this. K1 is equal to root 2 times, K2 is equal to what? Root 2 times of K1. If temperature is increases 4 times, so K2 will be equal to what? 2 times of the K1 like this. So you can easily compare the questions from here. Now, we have studied from the initial part, we have studied that conduction is what? Conduction is a mode of heat transfer which generally occurs in solids due to temperature difference with molecular lattice vibrational energy transfer and also due to free electrons transfer. We cannot say that conduction not occurs in case of the liquids and in case of the gases. Conduction also occurs in case of the liquids and in case of the gases. In general, we just take the neglection of the conduction, since generally the conduction in case of the liquid is very negligible and in case of the gases. But how it occurs? In case of the liquids, let's suppose we have a container. So in the container, let we have a liquid over here, and if we are supplying any amount of heat in the container, if we are supplying an amount of heat in the container, then it is obvious the temperature of these molecules start increasing. And if the temperature of these molecules start increasing, then definitely these molecules will start rising like this. And if these molecules will start rising, or we can say they will transfer their heat to the other molecules. They will again transfer, and during this transfer of the heat between the molecules is known as the conduction heat transfer in liquids. Similarly, in case of the gases, we generally say when high pressure, high temperature, high velocity molecule comes into the contact with the low temperature, low velocity molecule, they start colliding, and during the collision they transfer their heat between them. This is known as the conduction in gases. In case of the liquids, when we start transferring the heat, definitely due to collision they will transfer the heat. In case of the gases, also due to high velocity, high temperature of the molecule collide with the low velocity, low temperature molecule, they start transferring their heat. And this phenomena is known as conduction in gases. In general, if you will see the liquids and gases, in case of the liquids, if you will see, liquids are better conductor of heat as compared to gases. In general, liquids are better conductor of heat as compared to gases. For example, you can see the conductivity of the water is 0.69 and conductivity of the air is 0.023. In general, it will be written as 0.02122 whatever. So conductivity of the water, liquids are in general greater than conductivity of the gases. It means liquids are better conductor of heat as compared to gases. Solids, definitely they will be better conductor. Now coming to the next part, that is convection. So it was the description about the conduction. We have just given a short description about the conduction and conductivity. Now coming to the next part, that is convection. Convection is what? We generally says convection is the mode of heat transfer which generally occurs when a flowing fluid comes into the contact with the solid boundary. We simply says convection is the mode of heat transfer which generally occurs when a flowing fluid comes into the contact with the solid boundary, and the heat transfer between the flowing fluid and solid boundary is known as convection heat transfer. Convection is the mode of heat transfer which generally occurs when a flowing fluid comes into the contact with the solid boundary. Means the solid boundary should be in rest and there will be motion of the fluid. Why we are saying like this? We say since when the flowing fluid comes into the contact with the solid boundary, it start taking heat from here. If it start taking heat from here, it will transmit this heat to the upper molecule and it will just transport like this, and this will just transfer the heat to the upper molecule, it will transport like this. Means in case of the convection, whatever the heat which is transferred by the conduction, it is transported by the flowing fluid. So convection is the transport phenomena. Convection is the transport phenomena in which heat is transported by the flowing fluid which is coming by the conduction. Now coming to the next point, so convection, in case of the convection, convection is of two types. One is known as forced convection. Another is known as free convection. So first we have to know what is forced convection. If the motion to the fluid is provided by some external agent, then it is known as forced convection. And if the motion to the fluid is provided by the buoyancy forces which are arising out due to density difference. This types of the motion is known as, this type of the heat transfer is known as natural convection. For example, we can easily say, let's suppose we have studied PV is equal to mRT. So from here P is equal to m by V RT, that is rho RT, and from here we can see rho is inversely proportional to temperature. Means as temperature increases, density decreases, as temperature decreases, density increases. So what I want to say, in case of the natural convection, let's suppose air comes into the contact, cold air comes into the contact with this hot body, then definitely its density decreases, and if density decreases, it will rise like this. It will rise like this. Definitely, that's why we always say convection is the mode of heat transfer when a flowing fluid comes into the contact by the solid. Flowing fluid can comes into the contact with the directly by the some external agent, or it can flow naturally. In case of the natural flow, it will just take, the flow will takes place with the help of buoyancy forces, which are arising out due to density changes, which you have studied in the fluid mechanics. Now coming to the next part, that is radiation. We just want to make a small description about the radiation. Radiation is what? Radiation is the mode of heat transfer. In case of conduction, it was taking place through the solids, and in case of the liquids and in case of the gases also. Convection is the mode of heat transfer when a solid comes into the contact with the flowing fluid, or a flowing fluid comes into the contact with the solid. Now, in case of the radiation, radiation is the mode of heat transfer which do not require any material medium, and hence the radiation heat transfer takes place with the help of electromagnetic wave propagation, which travels with the speed of light. What I want to say, radiation is the mode of heat transfer which do not require any material medium, and hence radiation heat transfer takes place with the help of electromagnetic wave propagation, which travel with the motion of fluid. Electromagnetic wave propagation, generally in case of the radiation heat transfer, we do not require any material medium. If you have just taken the vacuum over here, then definitely they will start transferring their heat. Since in the radiation heat transfer takes place with the electromagnetic waves, which travels with the speed of lights. It means if the temperature difference is sufficiently high, then the radiation heat transfer will dominate over conduction as well as convection. Since convection and conduction needs an medium, but radiation does not need any type of the medium. So you have to remember, radiation do not require any material medium. All the bodies, if you just want to, also you have to remember one more thing, all bodies at all temperatures emit thermal radiation except the body is at 0 Kelvin. All the bodies at all the temperature emit thermal radiations except the body is at 0 Kelvin. If the body is not at 0 Kelvin, then the body will definitely emit the thermal radiation. Since at 0 Kelvin, you all are aware with this, molecules become motionless, and if there is no motion of the molecule, then definitely there is no heat transfer takes place. So, these are the three modes of heat transfer which we have discussed. One is conduction, we have discussed. One is convection, we have discussed. Another is radiation. Now coming to some laws. Laws of heat transfer we are going to discuss. And first law is Fourier law of conduction heat transfer. Laws of heat transfer, the first law is Fourier law of conduction heat transfer. Fourier law of conduction heat transfer says, when rate of heat transfer by conduction, rate of heat transfer by conduction is directly proportional to the temperature gradient in the direction of heat transfer. Just try to understand. Let's suppose it is dx, and let's suppose temperature difference is T1 or whatever it is dt. So it just simply says rate of heat transfer by conduction is directly proportional to the temperature gradient in the direction of heat transfer. In the direction of heat transfer. Why he is taking negative? You all are aware with this. He is taking negative since the temperature is decreasing in the direction of heat transfer. If temperature is decreasing, so he has taken as negative. And it is also directly proportional to the area which is lying perpendicular to the direction of heat transfer. Means simply he is just saying if the heat transfer takes place like this, then you have to take the temperature gradient in this direction and this perpendicular area you have to take. So from here you can see this will be, if the rate of heat transfer is over here, it means this will be the temperature gradient. This will be the temperature gradient. Sorry, this will be the area which we have to take. So from here you can write Q is equal to minus K into A into dt by dx. When we have merged this K is nothing, it is the thermal conductivity, which is a thermophysical property I have discussed earlier. Now coming to the next law. Next law is what? Newton's law of cooling. Newton's law of cooling says, it says, let's suppose we have a plate and fluid is flowing from here. Fluid is flowing from here. It just simply says the rate of heat transfer by convection is directly proportional to the temperature difference. This is the temperature of the plate and this is the temperature of, and it is T infinity, it is TW. So it simply says rate of heat transfer by convection is directly proportional to the temperature difference between the fluid and solid surface, and also directly proportional to the area of exposure. Let's suppose the heat transfer taking place, air is blowing over this surface. Means this is the area of exposure. Whatever the surface area through which the heat is going to be transferred. In this case, we not have to take the perpendicular area. We have to take the area of exposure only. So just try to remember, this is the area of exposure, that is surface area. This is TW minus T infinity, and the rate of heat transfer by the convection is like this. But one thing you have to remember, this conductivity is the thermophysical property. Thermophysical property. If conductivity is a thermophysical property of material, but similarly, you can say H is a thermophysical property. No, H is not a thermophysical property. It depends on the various properties of the material. Various properties means length, that is characteristic length, velocity of the fluid, rho, mu, Cp and K in case of the forced convection. In case of the forced convection, this H is not the thermophysical property of material. It depends on the various thermophysical properties, And in case of the forced convection, H is a function of what? L, V, rho, mu, Cp and K. For free convection, H is a function of G, beta, delta T. Why they are taking G, beta, delta T? Since in case of the free convection, it is taking place due to buoyancy forces, and definitely there will be an effect of gravity, since air is blowing like this, either like this or like this. So from here they are taking this, beta is known as coefficient of volume expansion. This beta is known as coefficient of volume expansion. And this beta can be given as, it is 1 by V into del B over del T under isobaric condition. Under isobaric condition, we write like, coefficient of volume expansion del V over del T under isobaric condition. So from here, if we just simply asking for an ideal gas, you can also write for an ideal gas. For an ideal gas, beta is definitely 1 by T. 1 by T per Kelvin. per Kelvin. So you just have to remember on what the values H depends for forced convection as well as free convection. Now you just have to remember one more thing, that is ranges of H. Ranges of H. Ranges of H means in the problems they will simply ask you which type of the convection is taking place. For example, you have calculated the value of H. Let's suppose H is equal to 40. He will simply ask you whether it is a forced convection or free convection. So we have given the ranges of H. If he is just saying free convection in air, in case of the free convection in air, H lies between 3 to 25. In case of the forced convection in air, H lies between 25 to 450. In case of the free convection in liquids, 250 to 600. And in case of the forced convection in liquids, 600 to 3000. And in condensation heat transfer, it lies between 3000 to 25,000. And phase change, this is also phase change but vapor to liquid. And if phase change liquid to vapor, it lies between 5000 to. In the objective problems, they will ask you in the as well as numericals, or directly they will ask you the values from here. So it was the description. It is the description of the, we have discussed the two laws. One is known as Newton's law of cooling, another is known as Fourier law of conduction heat transfer. We have discussed what are the modes of heat transfer. We have discussed conduction, convection and radiation. In case of the conduction, we have also discussed what is conductivity and how it varies in case of the solids, liquids and gases. And in case of the solids, we have just taken metals and non-metals as well as. Now we are discussing about the first law is Fourier law of conduction heat transfer. Second law is Newton's law of cooling. Now coming to the third law. Third law is Stefan Boltzmann law of thermal radiation. So let us discuss third law, Stefan Boltzmann law of thermal radiation. So now let us discuss Stefan Boltzmann law of thermal radiation. Stefan Boltzmann law of thermal radiation says the rate of heat transfer by radiation from a surface per unit time per unit area is directly proportional. I have taken the area. So we can say the rate of heat transfer from a black surface is directly proportional to the fourth power of absolute temperature of the body. Look, what he is just saying? He is just saying according to Stefan Boltzmann law of thermal radiation, this law simply states that rate of heat transfer by radiation per unit time from a black surface is directly proportional to the fourth power of the absolute temperature of the corresponding surface, and also directly proportional to the area of exposure from where the radiation energy is emitting. Now if I just take, so we can write, we have studied that it is Q is equal to what? Sigma into A into T to the power 4. So this was the rate of heat transfer by the radiation coming out from one surface. And the condition is what? The surface should be a black surface. Black surface is what? The surface which absorbed all the thermal radiation incident on it is known as black surface. We will discuss this black surface. So where the sigma is what? It is Stefan Boltzmann law of thermal radiation, and sigma is what? It is equal to, mathematical value is what? 5.67 into 10 to the power minus 8. So now let us just, we have discussed the three laws. First law was, it was Fourier law of conduction heat transfer. Second law was Newton's law of cooling, and third law is Stefan Boltzmann law of thermal radiation. So this was the basic part. This was the basic part which we have studied till now. Now we are going to start the chapter number 2, that is conduction. The conduction. And in the conduction, We have just taken the all of the basics, whatever the basics we have taken. Now coming to the conduction, and the conduction, the first topic is integration of Fourier law of conduction heat transfer. We have studied what is Fourier law of conduction heat transfer. Now we are going to study integration of Fourier law of conduction heat transfer, or we can also say conduction heat transfer through a plane wall, or he may ask you in terms of slab. Look, whenever, let's suppose we have a plain slab like this, we are just taking that, let the length of the slab is L, over here it is x is equal to 0, over here it is x is equal to L. Before making the integration, we just have to take the assumptions. We just have to take the assumptions, and you have to remember the assumptions. Sometimes they may ask you the assumptions. The first assumption is what? Whatever the flow is taking place, that is, we will just say it is a steady flow. Initially the flow is a steady flow. If the flow is a steady flow, it means what I want to say, this Q x is not a function of time. It is not a function of time. And also we can say this Qx is not a function of space. Now why he is just taking space and time? Since let's suppose we have a wall over here and this is the other side of the wall. If we have a wall and this is the other side of the wall, let's suppose we are just supplying the heat over here. If we are supplying the heat over here, it means at whatever the rate of heat transfer, we are supplying a constant rate of heat transfer. Now it depends on what is the conductivity. According to the conductivity, if conductivity is very high, it means the total heat transfer will take place from here. If conductivity is very less, it means from here, whatever the rate of heat transfer will remain same. It means what we will see, we are not getting the effect on this side if the conductivity is low. For example, insulators. In case of the insulator, on one side the temperature is very high, on the other side temperature is very low. So it is totally a case of conductivity. If conductivity is very high, it means what we will get? We will get the slope like this. If conductivity decreases, we will get the slope like this. Means we are supplying the constant source, supplying from a constant source, it means rate of heat transfer remains same. Just what? If conductivity is high, it will transfer fastly. If conductivity is low, it will transfer slowly and slowly and slowly. It means from here you can just say, if temperature difference is sufficiently high, if temperature difference is very large, it means conductivity of the material is very less. So from here, first condition we have taken that steady flow should be there. Yes, we can also say temperature is not a function of time, but temperature is function of space. Temperature is function of space. It is changing with respect to space. Now also we are just saying the material is isotropic. Material is isotropic. Means conductivity is not varying with respect to direction. Now let us integrate this. What we have studied? We have studied Q is equal to minus K into A into dt by dx. So let us solve this. If I just solve this, what we are getting? We are writing like this, it is Qx is equal to Qx plus dx, so no issue with this. We are writing Q into dx is equal to minus K into A into dt. So let us integrate this. If I just integrate this, we are going, this Q is constant, it means we are going from 0 to L, that is dx, is equal to minus K into A is a constant, dt, that is T1 to T2. So from here it is obvious, we can write Q into L is equal to minus K into A into T2 minus T1. So from here, if I just write, we can write Q is equal to I'm multiplying by the minus, so we will get K into A into T1 minus T2 by L. T1 minus T2 by L. So this is the heat transfer through the plane wall. This is the heat transfer through the plane wall. Now, from here, now we have assumed the material is isotropic, temperature is a function of x, not the function of time. Not the function of time. Q is neither a function of x, not a function of time, since we are just supplying the continuous amount, constant amount of heat from here. So this heat flux always remains same. If I just multiply this Qx by area, then we will get this Q. So Q is nothing. It is a heat flux, that is Q per unit area. And this heat flux always remains same. Now coming to the next point. Whenever we have solved this, we also have to study the electrical analogy of conduction heat transfer. So in the electrical analogy, what we have studied, in the 12th level we have studied, over here let the voltage is V1 and over here let the voltage is V2 and current supplied is I, and from here we are just taking R of the electrical. So we have studied delta V is equal to I into R, and we have calculated R electrical is equal to delta V by I, where delta V is what? It is V1 minus V2 upon I, since flow always takes place in the decreasing potential side. Now in this case, if I just take a thermal energy flow rate, means if the heat flow rate takes place like this, over here we will take the resistance as R thermal, and in this case we have taken as V1 and V2, in this case we will take T1 and T2. Similarly, we can also write this R electrical is equal to delta V by I. Similarly, R thermal can be written as T1 minus T2 by Q. So we have put it the value of Q. Q is equal to what? Minus K into A into dt by dx. Minus dt can be cutted from this T1 minus T2, since dt is what? T2 minus T1. So minus dt we have cut it. We have got dx by K into A. So after putting the values, what we have got? Q is equal to delta T, RTH is equal to what? It is L by K into A. And if again we are just writing Q is equal to delta T by RTH. Now in this case you have to remember this delta T is nothing. It is T1 minus T2. It is not T2 minus T1. So from here delta T by RTH, we have put it the value of RTH, that is, so we have got Q is equal to one formula, that is delta T by RTH, that is equal to K into A into delta T by L. And it is obvious that Q inversely proportional to L and Q directly proportional to K. Means if the conductivity of the material is very high, the rate of heat transfer will be very fast. And if the thickness of the material is very, very large, it means the rate of heat transfer will be small. So this was the basic concept behind the electrical analogy of conduction heat transfer. You will simply use delta Q is equal to delta T upon RTH, where RTH is equal to L by K into A and delta T is what? It is T1 minus T2. Now coming to the next part. Next part is what? Conduction heat transfer through a composite slab. Next part is what? Conduction heat transfer through a composite slab. In this case, we were taking conduction heat transfer through a plain wall, and now we are taking a composite wall. We have just taken a simple concept, that is Q is equal to delta T by RTH, and you have to use only one concept, that is Q is equal to delta T by RTH. So from here you can see RTH over here will be different, that is RTH1, and RTH over there will be different. If RTH are different, so it means From here we will write Q is equal to delta T by RTH of this and RTH of this, that is sigma RTH. We have written right here. And if I just take the thermal circuit, we can see there will be one resistance which will be applied by this wall, and there will be another resistance which will be applied by this wall. So we can write from here, it is T1 and let's suppose T interface and this. The resistance applied by the first wall is L1 by K1 into A, and resistance applied by this wall is K2, L2 by K2 into A. We have put it and we have got. Now one concept we have to discuss. What I want to say from here, whatever the heat we are supplying, it is same. Rate of heat transfer we are supplying same. It means what I want to write, this Q is same, so we can write minus K1 dt by dx of 1 is equal to minus K2 dt by dx of 2. If it is like this, minus K1 dt by dx of 1, it means what I want to say, you just have to remember only one thing, that if the temperature difference over here is very high, it means the effect at this point we are not able to see. If the effect at this point we are not able to see, means total heat transfer is not transferring like this. It is our wish that we want to transfer the heat from like this, but it depends on the material that what way it will transfer. So from here we can write that if conductivity is very less, it means the temperature difference is very high. And if temperature difference is very high, so we have written if dt by dx is greater than dt by dx of this, it means conductivity of this material will be lesser as compared to this. That's why we have you just have to remember this concept, that the rate of heat transfer is same, means dt by dx of 1 is greater as compared to dt of dx by 2. It means K1 is less than K2. And also there is no need to write the formula like this. You can write like this, T1 minus T interface. If you are taking the temperature difference of this, it means you have to take the resistance up to here, that is RTH1. If you are taking the temperature difference of this, it means you have to take this resistance, that's RTH2. You just have to remember only one thing, that the rate of heat transfer remains same, means up to where you are taking the temperature difference, up to that point you have to take the resistance only. Just one thing you have to remember. Now let us make a special case of conduction, convection, heat transfer through a composite slab. Let's suppose we have a composite slab like this, and in the composite slab over here, let's suppose some air is flowing like this. If air is flowing, means over here it will be a convection heat transfer, and also over here there will be a convection heat transfer. Let the conductivity of these material is K1 and K2, length is L1 and L2, like this thicknesses. Now what I want to say, we have studied, first we will make the thermal circuit, and for here we have studied the convection heat transfer. In case of the convection heat transfer, what we have studied, the Q is directly proportional to, or we have written H into A into T minus T infinity, like this, or we can simply write it as H into A into delta T. So it means we can write like this, it is delta T by 1 by HA, and it is what? RTH of convection, that is equal to 1 by H into A. So if it is RTH of convection, so from here to from here, look, over here we are taking at conductivity as constant, this is as constant, that's why we are taking at as a straight line. If we just think conductivity increasing, decreasing, then you will get the curves like this. But at this point you will not get the straight line since it is a convection and it depends on the various properties. Initially you will see the temperature is decreasing like this, and over here the temperature will also decrease and reaches to the environment temperature, so it will become like this. So you have to remember this. Now from here this is the first RTH1, RTH of the convection, that is equal to what? 1 by H1 into A, that is conduction, that is L1 by K1 into A. This will be what? L2 by K2 into A, and this is what? L3 by K3 into A. Sorry, only two walls are there. So it is what? S2 by 1 by S2 into A. Now from here we have the all resistances, or resistance 1, resistance 2, resistance 3, means simply up to the point we are taking, up to what point we are taking. Let's suppose we are taking temperature difference this. Since the rate of heat transfer is same, if rate of heat transfer is same, so Q can be written as, if I just write T1 minus T2. If T1 minus T2, then the resistance will be 1 by H1 into A. Since area of contact is same, whether it is a conduction or convection, so no issue, perpendicular and contacted. Or if I just write T1 minus T3, then we have to take these two resistances, 1 by H1 into A plus L1 by K1 into A. Or if you just want to take from here to from here, let's suppose over here this is T1 and it is T5, T1 minus T5, then you have to take the total resistance, sigma RTH. So simply you can just compare like this. It's a simple concept, that is sigma RTA, Q is equal to delta T upon RTH, or RTH is equal to delta T by Q. Now coming to the next case, after calculating this conduction convection heat transfer through a composite slab, one more concept is this. We have just please remember that over the convection, they have asked the problem from here. It is not a straight line, it will behave like this. Now coming to the overall heat transfer coefficient. Next topic is overall heat transfer coefficient. We all are aware with this. Overall heat transfer coefficient is what? It is a coefficient which takes into account all modes of heat transfer. All modes of heat transfer, whether it is a conduction or it is a convection. There is no radiation over here. So, and it is denoted by capital U, and Q is equal to U into A into delta T can be written. So, from here Q is equal to, we can write delta T upon 1 by UA, or we can write, we have also studied Q is equal to what? Delta T by RTH. We have compared. After comparing, you will get 1 by U is equal to what? 1 by H1. 1 by H1. Since area is same, so we have cutted this area. 1 by H1 plus L1 by K1 plus L2 by K2 plus 1 by S2. From here it is obvious, this overall heat transfer coefficient is inversely proportional to the resistance. Means if resistance is more, it means the rate of heat transfer will be less. Sorry, the flow rate will be less. It means what? If RTH is, so it means we are not getting the desired heat transfer on the other side. If we are not getting, it means this Q into A, delta T is same, area is same. So what will be affect? It will affect the U. So it means we can say U will be less. It is like this. So it was the description. Now coming to the next topic. So next topic is generalized conduction equation in Cartesian coordinate. So we have given the Cartesian coordinate system. Let's suppose it is a wall which we are discussing about, and the flow rate is in this direction. Let initially the heat transfer at this phase is Qx and at this phase is Qx plus dx. So we will calculate how? We will calculate the net heat transfer in x direction, net heat transfer in y direction, and net heat transfer in z direction. So I am just giving you the idea, net heat transfer in x direction will be what? Qx and minus Qx plus dx. This will be the total heat transfer in x direction. So from here we can just break this. If I just break this, this is Qx minus, this will be what? Qx plus rate of change of Qx with respect to x, and if we have to take the total change in the dx direction, so in the dx length, so we will have to multiply by the dx. If I just put the value del over del x, it is minus of minus minus become plus, k into a, area will be what? It is the perpendicular area. If we are going in x direction, means dy into dz will be the area into dx. So we will get the net heat transfer in x direction is what? Del over del x of k dt by dx into dy into dz. If k is constant, then k will come outside, and k into del 2t over by del x2 into whatever it is dv. Now if we just solve this, so we will apply the energy balance equation over here, and after applying the energy balance equation, it is net heat transfer in x direction, net heat transfer in y direction plus net heat transfer in z direction, and net heat transfer in, and heat generation within the element. What I want to say? We are just taking net heat transfer in x, y and z direction, and also we are taking, let's suppose there is some generation. Now coming to the generation, whenever the heat generation takes place, it will always takes place throughout the volume. For example, we are saying it is heat is generating throughout this. So it means we have to take the volume of this. Since heat generation will not take place across the area, that's why the unit of heat generation will be, it is watt per meter cube. Just have to remember, the unit of heat generation is watt per meter cube. Now let us put, if we just solve, we will get the generalized conduction equation in Cartesian coordinate system. It will be like this, and this equation can be written as, this is in the form of del square t plus q generation by k is equal to, this is the vector form. It is a Cartesian coordinate system, it is a vector form. Now coming to the next point, in case of the next point, so let's suppose we have just defined this alpha is what? Alpha is nothing, it is known as thermal diffusivity. And thermal diffusivity is what? We says it is a thermophysical property of material which allows the heat to get diffused into it. It is a similar property, just don't confuse about this. It is a thermophysical property of material which allow the heat to get diffused into it. What I want to say, we are just taking, let's suppose we have a material like this and it has some thermal diffusivity, that is alpha. Then it is obvious, if its thermal diffusivity is very, very high, so when we put this material into the environment, it will reaches very fastly to the local environment. If thermal diffusivity is very low, it means the outer environment will penetrate very, very slow and it will not reaches to the local environment very fast. So thermal diffusivity is nothing, it just allow the heat to get diffused into it. Let's suppose my thermal diffusivity is alpha. So heat is penetrating like this. If my thermal diffusivity is very good, it means the heat will penetrate from here to center of my body. If thermal diffusivity is very less, it means it will take some time. So thermal diffusivity is a similar property as kinematic viscosity in fluid mechanics. Thermal diffusivity is a similar property as kinematic viscosity in fluid mechanics. Now what is the difference between them? In case of the fluid mechanics, kinematic viscosity gives the molecular momentum transfer. Molecular momentum transfer. In fluid mechanics, kinematic viscosity gives molecular momentum transfer, whereas thermal diffusivity gives molecular energy transfer. You have to remember, he will just ask you molecular energy transfer. Means, what I want to say, in case of the fluid mechanics, if molecular momentum transfer is very high, it means the boundary layer thickness, hydrodynamic boundary layer thickness will be very high. And in case of the thermodynamics or in heat transfer, if value of the thermal diffusivity is high, it means molecular energy transfer is high. And if the molecular energy transfer is very high, whatever the molecule is coming, it is transferring the energy very fastly. If it is transferring energy very fastly, so means thermal boundary layer thickness will be very, very high. So it always gives, this kinematic viscosity gives about hydrodynamic boundary layer thickness and thermal diffusivity gives about thermal boundary layer thickness. You have to remember, thermal diffusivity is what? It is a thermophysical property of material which allows the heat to get diffused into it, like this. So whenever he is asking about the thermal boundary layer thicknesses or hydrodynamic boundary layer thicknesses, in case of the hydrodynamic boundary layer thicknesses of the two material, you will just check the kinematic viscosity. For example, in case of the air and water, the kinematic viscosity of air is what? It is mu by rho. You can just say nu is equal to mu by rho. And kinematic viscosity of the water, if you just take mu is what? 10 to the power minus 3 upon rho is what? 10 to the power 3. It is 10 to the power minus 6. And nu of air you will take, it is what? 10 to the power minus 3 upon 50. It is 1 by 50 times of water into rho of the air is what? 1.2. So you can easily see nu of the air is greater than nu of water. It means the boundary layer thickness in case of the air will be greater as compared to boundary layer thickness in case of the water. So from here we can also say, if alpha is greater, then the thermal boundary layer thickness of the fluid will be greater. And in this case, now just you have to remember the result. Result number 1 is conductivity of the liquids is greater than conductivity of gases. It is always true. Since liquids are the better conductor of heat as compared to gases. Liquids are better conductor of heat as compared to gases. So conductivity of the liquids is greater than conductivity of gases. But in case of the thermal diffusivity, you can easily see that the thermal diffusivity says it is K by rho C. So from here if you will see, you will just see that alpha directly proportional to K. Alpha directly proportional to K. It means the material whose conductivity is more will have the more thermal diffusivity. But thermal diffusivity not only depends on K, it's also depend on the heat capacity. It also depends on the heat capacity. So when you compare, for example, if I just take alpha of the water is what? 0.69 by density of the water is 1000 into C of water is 4.18. Let's suppose we are calculating alpha of the air. Alpha of the air is what? K of the air is how much? It is 0.023 upon rho of the air is 1.2 and C of the air is what? You can take it is Cp. So it is what? How much? Cp is equal to 1.005. 1.005. Now the condition behind is, you can easily see alpha of the air is greater than alpha of the water. And if alpha of the air is greater than alpha of the water, so any of the case is possible. Alpha of the liquid can be greater than alpha of the gases. Alpha of the gases can be greater than alpha of the liquids. Similarly, you can also say nu of the liquid can be greater than nu of the gases, or nu of the gases can be greater than nu of the liquids. But in case of the mu is always greater, the mu of the liquid is always greater than mu of the gases. So it's a simple concept you have to remember. In case of the thermal diffusivity, it is a simple thermophysical property which allow the heat to get diffused into it. Thermal diffusivity has only one significance, that it will give the thermal boundary layer thickness. Thermal boundary layer thickness means, as the thermal diffusivity is greater, it means molecular energy transfer is greater. If molecular energy transfer is higher, it means thermal boundary layer thickness will be higher. Now coming to this point, you have to remember this generalized conduction equation. If he is just saying you have to calculate in case of a steady flow, you can just take it as 0. If he is just saying if there is no heat generation, you will take this as 0. If he is just saying for 2D, you will just take this 0. If he is just saying 1D, you will take this 0. So it's a generalized conduction equation. Whatever he is asking, you have to write in that form only. You just have to remember this equation. Now let us take some special cases in case of the generalized conduction equation for steady flow. So the case 1 is one dimensional generalized conduction equation for steady flow. So in case of the steady flow, we have to calculate one dimensional generalized conduction equation. So from here it is T1, it is T2, and you just have to, whenever he is asking, I am not deriving over here, you just have to remember this one dimensional steady flow generalized conduction equation without heat generation. It means you will write like this, and when you solve, you will get the temperature variation like this. T is equal to T2 minus T1 into X by L. So from here you can say if there is no heat generation, temperature variation will be linear. Temperature variation, we simply ask you, if there is no heat generation in the conduction heat transfer through the wall, the temperature variation or temperature profile, it is linear. You have to remember this. Now coming to the next point, when you will solve, you can easily calculate the temperature at any point. If you are just saying x is equal to 2 centimeter, x is equal to 1 centimeter, x is equal to 3 centimeter, you will just use this formula and you can calculate the temperature at any point. This was the case 1. Now coming to the case 2. So in case of the case 2, we are just taking one dimensional generalized conduction equation for steady flow with variable conductivity. And variable conductivity was, we have discussed earlier, variable conductivity case. And in case of the variable conductivity, you will just get Q is equal to K mean. Whenever the conductivity is varying, you will take K mean into A into T1 minus T2 by L. So if the conductivity is varying like this, you will calculate K mean like this. K mean like this. K mean is equal to what? K naught 1 plus alpha Tm. Tm is nothing, it is T mean, that is T1 plus T2 by 2. Means if this wall has temperature T1, this wall has temperature T2. So T mean is what? It is T1 plus T2 by 2, like this. It is T mean. Now the conductivity can vary like this. It may be he has just seen, shows conductivity over here is K1 and K2. It may be he has given the linear variation. In case of the linear variation, if he has just given the conductivity at this point is K1, at this point is K2, then you can calculate the K mean is equal to K1 plus K2 by 2. If he has just given like this, then you can calculate the K mean value like this. So it's a simple, just variable conductivity is important for you. You just have to remember the condition like this. Now coming to the next point, in case of the next point, case third says one dimensional generalized conduction equation in a steady flow with heat generation. So let us take with heat generation case. If we have to take the with heat generation 1D, you can just easily the equation will be like this. And when you will solve, you will get two equations. One equation is like this Another equation is like this, whatever, T minus T max upon TW minus T max is equal to XYL, or you can form, fill in case of the TW, T minus TW upon T max minus TW, it is 1 minus XYL. Whatever the formula, you can just remember only one formula and you will get the answer. Or I always suggest you just remember this formula. What you will do after this? You will do like this. It is d2t upon dx2 is equal to what? Minus q generation by k. You will first differentiate, then second differentiate. You will get two constants, and when you put the values of the boundary conditions, you will get the values of the constants. Now, it is a case of when the generation takes place at the center of the plate. It may be the generation is not taking place at the center line. So, whatever, you just remember this formula. Why I am solving this? I am solving this because he will ask you when the heat transfer takes place, one dimensional generalized conduction equation, he will ask you if the heat generation takes place within the wall, then the temperature profile will be, or heat generation not taking the place, then the temperature profile. If heat generation do not takes place, then the temperature profile will be linear. And if heat generation takes place, then the temperature profile will be parabolic. Then the temperature profile will be parabolic. So, that is why I have written this formula. You can just calculate any of the type, you will just get the formula as, the profile as x by L whole square. So, the temperature profile will be definitely parabolic. We have discussed the generalized conduction equation, and in case of the generalized conduction equation, you can just calculate net heat transfer in x direction like this. Also, you can calculate the net heat transfer in y direction. The volume will be same, and z direction. And after calculating this, we have just taken the energy balance equation. Energy balance equation is what? Net heat transfer in x direction, y direction and z direction, plus there will be some generation within this. And if I just put the values, we will get it is equal to change in internal energy of the system. Why? He will ask you why you are taking this change in internal energy of the system. Since we all are aware with this, dq is equal to du plus dw, and it is a solid, and in case of the solid it will behave as a rigid container, and in case of the solid definitely dw will be 0. So, the change in energy will be equal to change in internal energy. That is why I am taking du by dt. And after that, we have just got one more definition, that is thermal diffusivity, which is a thermophysical property of material which allow the heat to get diffused into it. After that, we have seen thermal conductivity of the liquid will be always greater than thermal conductivity of the gases, but thermal diffusivity can be greater or can be lesser. Yes, thermal diffusivity gives the molecular energy transfer, and similarly kinematic viscosity gives what? Molecular momentum transfer. Thermal diffusivity of the liquids can be greater than thermal diffusivity of the gases, can be lesser than thermal diffusivity of the liquids. So, whatever the solution, you just have to remember the molecules, the substance whose thermal diffusivity is more will have the more thermal boundary layer thickness. Similarly, in the fluid mechanics, you will say the substance whose kinematic viscosity is more will have the more hydrodynamic boundary layer thickness. Now, coming to the next point, we have just taken three special cases. Case 1 was generalized conduction equation for steady flow. You don't have to remember this, you just have to remember the temperature profile will be what? Linear. If there is no heat generation, it means temperature profile will be linear. In this case, if the conductivity is varying, so you will get three cases. One is conductivity is K1 and K2, K1 and K2. Another is conductivity increasing, another is conductivity decreasing. This was what? K mean is equal to K1 plus K2 by 2. This is what? K is equal to K0 into 1 plus alpha Tm and in this case was k is equal to what? K naught into 1 minus alpha T, like this. So you will solve like this. These are the three cases you will get in the variable conductivity. Now if the heat generation takes place, so in case of the heat generation, the temperature profile will be parabolic. So these the things you have to remember in case of the generalized conduction equation through the wall. Now coming to the next topic. Okay. So the next topic is radial conduction heat transfer through a cylinder. Now in case of the cylinder, let's suppose we have a cylinder and it is a center line of the cylinder. What we are assuming, we are just taking the heat transfer takes place radially. Let the heat transfer takes place radially. Means this Q is not the function of R. Since what we are saying, it is a heat flux and rate of whatever the rate of heat transfer, it will just change according to the area. If area is not changing, it means the heat flux will remain constant. Now from here we can also write temperature is a function of R, means as R increases or decreases, temperature will changes according to this. Next point is what? Temperature is not a function of time, means we are just taking it as a steady flow. And last one is what? Material is isotropic, that is conductivity remains constant. Now coming to the next, if I just take the radial conduction heat transfer, so the formula for the radial conduction heat transfer will be given as minus K into A into dt by dr. And when we start solving, we just had to Q into dr is equal to minus 2 pi K into dt. And from here we can just calculate this. And the formula you will get for the radial conduction heat transfer through a cylinder, it will be 2 pi K into L T1 minus T2 upon ln of R2 by R1, where RTH can be what? It is T delta T upon RTH can be compared as delta T upon RTH. So RTH can be written as ln of R2 by R1 upon 2 pi K into L. Now from here we can also draw the thermal circuit if you are confused. In case of the thermal circuit, the resistance will be in this region, and this resistance will be nothing, it is R2 by R1 upon 2 pi K into L. And from here you can easily say, as R2 increases, means thickness of the cylinder increases. As R2 increases means thickness of the cylinder increases, means it will offer more resistance and rate of heat transfer will decrease. So it depends on the R2, whatever the outer radius. Now coming to the one more case, another case is conduction convection heat transfer through a composite cylinder. In case of the composite cylinder, we have just taken, let's suppose it is inner side R1 and R2, and it is other material whose conductivity is K2, that is radius R3. So we have first made the thermal circuit, it is like this. Initially inside, let's suppose a fluid is flowing whose temperature is T infinity 1, and outside that fluid is flowing whose temperature is T infinity 2. So we are getting RTH of convection 1 plus RTH 1 of this plus RTH 2 of this plus RTH of convection 2. Now from here if I just take the RTH, we can easily write it is initial what? RTH is equal to 1 by H into A. But inside we are just talking about, it means inside area will be what? AI. And outside, if we just talking about outside area will be what? A naught. Since area is continuously changing, that's why we have to take area A1 and A2 or AI or A naught, whatever. So again, you will just find the formula. Q is equal to what? You can just write delta T upon RTH. Whatever the temperature difference you will take, you just have to take the resistance over there. For example, if you are just taking T infinity 1 minus T1, it means you just have to take 1 by H1 into AI simply. You can write like this. No issue with this. Since heat flux remains same, so no, don't you have to confuse, you just have to write like this. Now from here, if I just calculate the overall heat transfer coefficient, overall heat transfer coefficient is what? It is a coefficient which include all modes of heat transfer. So in this case, we have included two modes of the heat transfer, conduction and convection. So we will write Q is equal to Ui Ai into delta T and U naught A naught delta T. Why I am writing Ui Ai? Since inside area is different and delta T is same, it means Ui will be different. Why Ui will be different, same? Ui will be different since we have to take this as constant. Similarly, for outside area will change, it means U will change. Again, we will write like this delta T upon 1 upon Ui Ai. And if we just solve this, you will get the formula for Ui. 1 upon Ui is equal to 1 upon Hi plus R1 by K1. R1 means inner radius, conductivity, inner material conductivity, ln of R2 by R1 plus R1 by K2 ln of R3 by R2 plus R1 by R3 1 by H naught. And from here we will write 1 by U naught is equal to R3 by R1 1 by H1 plus R3 by K1 and R3 by K2 and so on. Similarly, you just take these types of the two overall heat transfer coefficient. You just have to remember how, just otherwise you will solve the problem by using this formula only. So no need to you just have to remember what is the overall heat transfer coefficient. Just remember how we will calculate this. Now coming to the next most important topic, they generally ask the problem from here. The topic is critical radius of insulation. So in case of the cylinder, critical radius of insulation is given by K insulation by H, and in case of the sphere, critical radius of insulation is given by 2K insulation by H. So we have not discussed sphere, but further I am just discussing over here. Now the condition is what? What is critical radius of insulation? Look, critical radius of insulation is what? Let's suppose we have a pipe through which steam is flowing. If a pipe is like this, in which steam is flowing, and if there is no insulation around the pipe, then what we will do? We will start insulating it so that the rate of heat transfer from the steam will be decreased. But what happened in case of the pipe? Let's suppose we have a pipe like this. We have a pipe like this whose material is over here. Now what I want to say, let's suppose whatever the fluid is flowing through this pipe, means from here if I just see, we have been seen it is RTH, sigma RTH is equal to what? Sigma RTH is what? It is 1 by H1 into A1 plus ln of R2 by R1 upon 2 pi K1 into L plus ln of R3 by R2 upon 2 pi K2 into L plus 1 by H2 into A naught. Now what I want to say from here, let's suppose this is the resistance which is offered by the cylinder. Now what I want to say, it is possible when we are putting a material over here. This is radius R1, this is R2 and this is R3. Now just try to understand, critical radius of insulation is what? When we start wrapping an insulation over here. When we start wrapping an insulation over here, the contact of the fluid will suddenly removed from here. Means initially when there was no insulation on the pipe, it means what we are getting, we will be getting one is conduction resistance another is convection resistance. Means heat transfer was taking place by conduction and also by convection. Here, from here to here conduction, and from here to here convection. Means the resistance offered are RTH will be RTH of convection plus RTH of conduction plus convection. Now what I want to say, as you start wrapping the insulating material, no doubt the conduction resistance will increase. No doubt this conduction resistance will increase, but you will see there is no contact with the fluid. It means the convection resistance will decrease drastically. So what I want to say, you will see a total decrement in the resistance. This total decrement in the resistance means, what I want to say, as you start wrapping, this resistance will start decreasing. RTH of conduction will increase, but as compared to increment in the RTH of conduction, RTH of the convection further decrease, and overall again there will be decrement in the resistance. Now what I want to say, overall if you will see the decrement in the resistance, as the resistance decreases, rate of heat transfer increases. As the rate of heat transfer, and if we start wrapping, this continues to happen up to a point at which resistance is minimum. That point, resistance is minimum, rate of heat transfer is maximum. That point is known as, or radius of that point is known as, critical radius of insulation. What I want to say, in case of the wires or pipes, when we start insulating them, the heat transfer increases instead of decreasing it. Why? Why? In case of the, when we put the resistance, when we put the insulation around it, conduction resistance no doubt increases, but as compared to conduction resistance, convection resistance decreases, and overall there will be a decrement in the resistance, and this continues to happen up to a radius. That radius is known as critical radius of insulation. Means critical radius of insulation is nothing, it is a minimum radius at which resistance is minimum and rate of heat transfer is maximum. So critical radius of insulation is nothing, it is a minimum radius at which resistance is minimum and heat transfer is maximum. So we can say, let's suppose it is a critical radius of insulation. Over here, if you just see RTH, RTH will start decreasing, and over here you will get RTH minimum, and over here you will get Q maximum. So critical radius of insulation is a radius at which RTH is minimum and rate of heat transfer is maximum. Now how he will ask the problems, now coming to that section, how they will ask you the problems. Now in case of the critical radius of insulation, it is obvious, it is a minimum radius at which resistance is minimum, rate of heat transfer is maximum. Now he will ask you the problems of two types for steam carrying pipes. For steam carrying pipes. In case of the steam carrying pipes, let's suppose we have pipes and it is carrying steam. Now in case of the pipe, look, critical radius of insulation, we are not going to wrapping, we just have to calculate. So first we will check the heat transfer coefficient over here and whatever the conductivity of insulating material. Let's suppose if we have calculated K by H value, we have calculated K by H value, and if the K by H value RC is greater than RC is greater than radius of the pipe. If RC is greater than the radius of the pipe, this is the radius of pipe and RC is this. It means what will happen? Up to critical radius of insulation, when you put the insulation around it, the resistance start decreasing, rate of heat transfer will increase. Means whenever the radius of the pipe is less than the critical radius of insulation, any insulation put around the pipe will directly increase the rate of heat transfer, means steam start condensing. So she will simply ask you whether we have to put any insulation around the pipe or not. In this case, if the steam carrying pipe is there, then definitely you will not put any of the insulation around it. If you put any of the insulation, definitely the rate of heat transfer increasing and steam start condensing. So no insulation you will put over here. No insulation. Now, if you just, he will ask you if RC is less than R. Yes, R is greater. Yes, R is greater, means RC will lie over here something. It means it is obvious after the RC, when you start, after RC it will start increasing. It will start increasing as compared to decrement in this. It means overall you will get an increment in the resistance. So from here, if the RC is less than R, it means you will put, now the resistance start increasing, Q start decreasing. Yes, you can put the insulation around it. So in case of the steam carrying pipes, your first aim is to save the heat, not to lose the heat. So in this case, if the RC is greater than R, in simply you will just ask, he will give you the K of the insulation and H value. You will just calculate RC and he will give you the value of R. You will just compare and you will give the answer whether the insulation is required or not. Second part he may ask you, in the current carrying wires, it's an important topic for you. In case of the current carrying wires, it is obvious if these are carrying currents, so it means our aim is to carry the current, not to carry the heat. It means we have to lose the maximum amount of heat. So in this case, if RC is greater than R, it means we have to put the insulation up to RC. So yes, insulation required. If RC is less than R, you will not put any of the insulation, since it will directly decrease the rate of heat transfer. So this is the physical significance of the RC. RC is the minimum radius at which heat transfer rate is maximum, resistance is minimum. In the steam carrying pipe, our aim is to carry the steam, to carry the heat. So we don't want to lose the heat. If the radius of the pipe is less than the critical radius, means up to critical radius we will start losing the heat. And at the critical radius, heat losing will be maximum. That's why we will not put any of the insulation. If R is already greater than, then we will definitely put the insulation around it, and it will reduce the rate of heat transfer. Similarly, in case of the wire, it will be opposite. We just want to carry the current, not to carry the heat. So we want to lose maximum amount of heat. If the radius of the wire is less than the critical radius of insulation, means we will wrap up to critical radius of insulation. If we start wrapping above the critical radius of insulation, then heat transfer rate first increase, then start decreasing. So he will simply ask you the problem either from the wire or from the pipes, and you will just answer like this. One more thing, he may ask you the critical radius, critical thickness of insulation. If he is asking the critical thickness of insulation, it is nothing, it is the difference between the outer radius and critical radius. This will be the critical thickness of insulation. So simply they will ask you the problem like this. Okay, so we have discussed the cylinder. Now coming to the next topic. So now start with the next topic. Next topic is generalized conduction equation in cylindrical coordinates. And in cylindrical coordinate, before starting the cylindrical coordinate, we are just discussing cylindrical and spherical coordinate system. This is your cylindrical coordinate system. Cylindrical coordinate system. And this is your spherical coordinate system. Spherical coordinate system. So what I want to discuss from here, in case of the cylindrical coordinate, we are just discussing about, in the Cartesian coordinate system, we take the coordinates as x, y and z, and in cylindrical coordinate we take the coordinate as r, theta and z. In case of the spherical coordinate system, we take similarly r, phi and psi. In just Cartesian coordinate, we take x, y, z. So in the Cartesian coordinate, at any point we take the coordinates as x, y, z. If we just solve, we get an angle. This angle is theta. We are just taking theta. So this angle is known as zenith angle. And if we convert the Cartesian coordinate system into cylindrical coordinates, so in the Cartesian coordinate and cylindrical coordinate, we can write x is equal to r cos theta, y is equal to r sin theta, and z is equal to z. So you can convert like this. Okay. So next point is what? If we just convert the Cartesian coordinates into spherical coordinates, in this case, this angle is known as the zenith angle and this angle is known as azimuth angle. So just remember, sometimes they may ask you in the objective problems, this angle is what? Zenith, and this is azimuth angle. This is azimuth angle, this is your zenith angle, and again you can convert like this. X is equal to r sin psi cos phi, y is equal to r sin psi cos phi, sin phi cos phi, z is equal to r cos phi. I am not deriving over here, I am just giving you the overview how you will convert. Now, if we just convert the generalized, there is two methods to solve the cylindrical coordinates or spherical coordinates. One, you can directly convert the Cartesian coordinate system into cylindrical coordinate or spherical coordinate system. Second one is what? You can directly solve the cylindrical coordinate system. So if I just come to the cylindrical coordinates, let's suppose we have taken a cylindrical element like this, and in this cylindrical element we are just seeing, let's suppose the heat transfer at this end is QR and rate of heat transfer at this end is QR plus dr, since we have taken this distance as dr. So we are assuming there is some, since it is a generalized conduction equation, so we are assuming there will be some change in the Q. We are just discussing this generalized conduction equation for cylindrical coordinates. Now coming to the next point, in this case we can take, in the theta direction it is Q theta and Q theta plus d theta, and in z direction we can write QZ and QZ plus dz. Now I am just giving you an overview. When you solve QR, how you will write QR? We have studied in the wall or cylindrical case. In the cylinder case, we have the K into A into del T over del R. So if I just write K into area, area will be always perpendicular, means we are going in this direction, means this area will be the perpendicular. This is theta and this is what? dz. So we have written this theta, d theta, and it is dz. But this d theta is an angle, it is not the length. That's why we are multiplying by the length by r. So we write like this, minus k r d theta into dz into del t over del r. Similarly, if I just write q r plus dr, so first if I just write minus k into a into del t over del r plus what is the change in qr with respect to dr, and I have just written the area over at outside. We cannot write, we will write r over here. So if you just solve, if you will just solve, this R is varying with respect to dr, that's why I am writing R over here. Now, what I want to say, if you just solve the energy balance equation, whatever I have told you in case of the wall, you will just simply write rate of heat transfer in R direction, rate of heat transfer in theta direction, rate of heat transfer in Z direction. You need not to derive this, you just have to know the final equation. And the final equation you will get like this. They will simply, sometimes they have asked directly the equation. And the final equation is what? 1 by R del over del R, R del T over del R, plus 1 by R square del to T over del theta 2, plus del to T over del Z 2 plus Q, generation by K is equal to 1 by alpha del T over del T. The similar condition as we have got in the wall case. Now coming to the next point, sometimes, many times they will ask for only one dimensional, not for three dimensional. For three dimensional you can write like this. If you just want to write for three dimension, then it is obvious we have to take this term one dimension. This term is in R dimension, and with heat generation this term, and if it is a steady flow this will become 0. So 1D steady flow, if I just write, we will write 1 by R del over del R, R del T over del R plus Q generation by K is equal to 0. This equation can also be written if I just break this bracket. What we have to do? We have to differentiate. First function differentiation of second function differentiation of first function. And if we will solve, you will get the equation like this. It is del to T over del R2 plus 1 by R del T over del R plus Q generation by K is equal to 0. So you just have to remember, most of the time they have asked for one dimensional only. If you can take the steady unsteady flow, so you will take like this. It is 1 by alpha del T by del T if you want to take. So they have asked this equation so many times. You just have to remember the equation like this. Or I just suggest you remember this equation, and whether he is asking for steady flow, you will cut this. If he is asking without heat generation, you will cut this. If he is asking for two dimensional, you will cut these. And if you are just asking for 1D, you will cut these two dimensions. So just remember this equation only. And after getting this equation, you will, whatever he is asking, you can simply put the value and you will get the answer. Now, this is the equation. If I just write, this is just what I want to say. It is one dimensional. We are just discussing first case. One dimensional without heat generation, steady flow. And if I just write one dimensional without heat generation, steady flow, in that case we can write the equation 1 by R del over del R, R del T over del R. So we have written this equation like this. Now if you just solve this, you will, what you will do, R will be over here and you will differentiate. And when you differentiate, you will get the value for T as C1 ln R plus C2. But from here we have to tell one thing to you. Let's suppose the temperature profile is like this. So from here, first thing we can say, in case of one dimensional without heat generation through a cylinder, this means the temperature profile will be what? It is logarithmic temperature profile. So we will get the temperature profile as logarithmic. Second thing what I want to tell you, I just want to tell you, if the cylinder is a solid cylinder, in case if the cylinder is a solid cylinder, what I want to say, it means if I just want to take the temperature at the center of the solid cylinder. If you just want to calculate the temperature at the center of solid cylinder, what I want to say, at the temperature at the center of solid cylinder, R become 0 and temperature become undefined. And hence we will say the temperature at the center of cylinder is not defined in case of one dimensional without heat generation, steady flow is taking place through the cylinder. So whenever he is asking if in a cylindrical coordinate system or heat transfer through a solid cylinder, in one dimensional steady flow with without heat generation. So you will say in this case the temperature will not defined. Yes, if you will take a hollow cylinder like this, if you will take the hollow cylinder like this whose inner radius is R1, outer radius is R2, and we are taking an average radius that is R. So we have taken at inner radius temperature is T1, outer radius temperature is T of the wall, and at an average this temperature is T. Then you will get the relation, and the relation will be equal to T minus T1. T is the temperature at any R. T minus T1 upon T of the wall minus T1 is equal to ln R by R1 upon ln R2 by R1. By using this equation, you can calculate the temperature at any point in the cylinder. At any point you can easily calculate. This is the case for a sphere. We will discuss this case later on. But in case of the cylinder, if he is asking find the temperature at the half of radius, or at the 2/3 of the radius, or 1/4 of the radius, so you will just put the value and you will get the temperature. Or if he is just saying at what, this is the temperature at what radius, so you can calculate the radius. So these types of the simple question they will simply ask you from the cylindrical coordinate system or from heat transfer from the cylinder. We have also discussed the heat transfer through the cylinder, that is Q is equal to minus, Q equals what? 2 pi KL into T1 minus T2 upon ln of R2 by R1. By using that you can just calculate the heat, and by using this formula you can directly calculate the temperature at any point in the cylinder. But the cylinder should not be a solid cylinder. Cylinder should be a hollow cylinder. We always discuss with the hollow cylinder, not with the solid cylinder. And in case of the solid cylinder, you just have to take like not in 1D, you will just take again in 3D, that is in the volume. Now coming to the next point. Next case we are going to discuss case one dimensional with heat generation, steady flow. And in case of one dimensional with heat generation steady flow, we just write it, the equation will be like this. And if you will solve, you will get T is equal to minus QR square by 4K plus C1 ln R plus C2. Again the same thing. If the cylinder is solid, the temperature at the center of the cylinder. Temperature at the center of cylinder means R will become 0, and if R will become 0, temperature become undefined. So whether the heat generation takes place or heat generation does not takes place, temperature at the center of cylinder, in case the cylinder is solid, will not defined. Will not defined means you can't calculate. You can't calculate at the center line of the cylinder. Yes, if the cylinder is hollow like this, then you will solve. And you will get the equation like this. It is Tmax minus T upon Tmax minus Tw, where Tmax is the maximum temperature, T is the temperature at any R, Tw is the temperature at the surface of the cylinder. Tmax minus T upon Tmax minus Tw is equal to R by R whole square. So from here it is obvious, if the heat generation within the cylinder takes place, the temperature profile will be what? It is parabolic. In the wall case, temperature profile was also parabolic, and in the cylinder case, if the heat generation takes place, temperature profile will be again parabolic. If you just put R is equal to 0 in this, you will get Tmax is equal to what? T. So we can say if the heat generation within the cylinder takes place, it means the maximum temperature will be at the center of cylinder. It means the maximum temperature will be at the center of cylinder. If the cylinder is a hollow cylinder, not a solid cylinder. Also you can get the formula like this. This is Tmax minus T upon Tmax minus Tw. You can also write like this, Tw minus T upon Tw minus Tmax. These are, you can use any of the formula. Just one formula you have to remember, either in this case or in this case. In this case also you can write it is 1 minus r by r whole square. So this formula and this formula, these are the two formulas which you have to remember. So these are the simple formulas for the cylindrical coordinate. One formula is this and another formula is this. You just have to remember the two formulas. In case of the, either you just remember this equation and whatever he is asking just solve and you will get the equation like this. It's a simple problem. We have just put it over here. It is just t is equal to C1 ln r plus C2 and we have calculated the value of C1 and C2 by putting these boundary conditions and we have written the formula. So you have to remember these formula. Better to remember the formula. I think we have studied all of the theory portions previously. We are just revising. So this type of the formula, and in case of this just heat generation, you will just remember this formula or this formula. Now the next part is conduction heat transfer through a sphere. So in case of the sphere, we also have to calculate the conduction heat transfer. So we are just taking a simple sphere which is hollow, and in this case Q can be written as 4 pi k R1 R2 T1 minus T2 upon R2 minus R1. If he is simply asking about the composite sphere, you will write what delta T upon sigma RTH, and from here you can easily calculate the value of RTH. The value of RTH is what? So we can write the RTH value. RTH value will be what? This will be the RTH value. This is what? R2 minus R1 upon 4 pi k R1 R2. So you can calculate the RTH, and if it is a composite cylinder, you will just put the value of RTH behind this, below this. So from here we are getting the formula. Either you can write the formula like this or you can write the formula like this. This is the basic formula. We have solved R2 minus R1 we have got over here and R1 R2 we have just put over here. So it's a formula for conduction heat transfer through the sphere. Now he may also ask you, and he have asked so many times, generalize conduction equation in spherical coordinates for one dimensional. If he is asking the generalized conduction equation in spherical coordinates in one dimensional, you have to remember only cylindrical coordinate generalized equation. Cylindrical coordinate generalized equation was, it is 1 by r del over del r del t over del r plus q generation by k. You just have to remember this equation only. And on the place of, in case of the spherical coordinate system, you just have to replace this r by r square. Just replace this r by r square and you will get the equation for a spherical coordinate system. And you will get the equation for a spherical coordinate system. And again, in the second part, if you have just differentiate, and in that case, if you are you have remember in this case, then what you have to do? You just have to remember this 1 by r by 2 by r, 2 by r. So spherical coordinate equation is easy to remember. Just remember the cylindrical coordinate equation, and by using the cylindrical, just in that case, you have to just replace this r by r square, and in this case, you just have to replace this 1 by r by 2 by r. So what I want to say, if sometimes he may ask you, calculate, so what will be the generalized conduction equation in spherical coordinate system without heat generation? So we can say without heat generation the equation will be like this, or it will be like this. Means we can also remove this r. This will be the equation in the spherical coordinate, or this will be the equation. Now from here, if we just solve this equation like this, if I just solve this equation in case of the spherical coordinate system, you will again get some case over here. And in that case, you will get the equation for temperature variation. How you will remember? You just have put what T minus T1. T was the temperature at any point, okay. T1 was the temperature at inner radius. So you will write like this, ln of T was the temperature at any R upon R1 upon it was the temperature upon TW minus T1. T1 was the inner, T minus T1, this minus this and this minus this. So you will again write it is of ln of R2 by R1. Simply you can also remember for the sphere. In case of the sphere, if you have just taken like this, he has just taken T minus T1. Let it is T and it is T1. So you will write what? It is the case of just hyperbolic. So you will write it is what? 1 by R1, that is T. 1 by R1 minus 1 by R upon TW minus T1 is equal to what? It is 1 by R2 minus 1 by R1. It is 1 by R minus 1 by R1. You will write like this. You just have to remember the equation like this. What you will write? You will just T minus T1 upon TW minus T1. So you will just have to remember like this. It means either you can solve the equation. If you just solve the equation, T minus T1 upon TW minus T1 is equal to what? It is 1 by R minus 1 by R1 upon 1 by R2 minus 1 by R1. So these two formulas you have to remember, since in general they will ask the problem, find the temperature at this radius in case of the sphere, either in case of the cylinder. So if they are asking, you can just calculate by using this. Now one more thing we have to discuss. He will simply ask you if no heat generation is taking place in case of the sphere, and what will be the temperature profile. You can just check, this is the equation for hyperbola. So the temperature profile will be what? Hyperbolic. Temperature profile will be what? Hyperbolic. Again you can calculate the generalized conduction equation with heat generation. If you just calculate the generalized conduction equation with heat generation, you will again get the temperature profile as parabolic. So just have to remember these formulas like this. Now coming to the next point, I have just made a table for you. You have to remember, like we have discussed three cases. One is wall, another is cylinder, and third one is sphere. In case of the wall, we have given for constant conductivity and for variable conductivity. And in case of the constant conductivity, we have got the equation for heat transfer, that is K into A into T1 minus T2 by L. And in case of the variable conductivity, we have got Km into A into T1 minus T2 by L. Now, without heat generation, if I just take without heat generation temperature profile, definitely the temperature profile without heat generation we have studied as linear. So he will simply ask you, if the heat transfer takes place through a plain wall or composite wall without heat generation, the temperature profile will be, it is linear. And with heat generation, if he is talking about, it will be parabolic. It will be parabolic. Now, if conductivity is varying, in that case, you will write the Q equation like this, and the profiles will be like this. If he has just given the conductivity over here and over here, it is K1 and K2, then you will take the average conductivity like this. If it is varying linearly, either if it is varying, K is equal to increasing in case of the alloys or in case of the metals, pure metals. So you will write like this. In case of the cylinder, we have written the formula over here. Formula was like this, and profile was logarithmic, we have discussed, and in case heat generation takes place, profile was parabolic. Now, in case of the sphere, we have discussed, it is 4 pi k R1 R2 upon R2 minus R1, and profile is what? It is hyperbolic. And if heat generation takes place, the profile will be parabolic. So what we have started? We have started from the beginning, that is generalized conduction equation in cylindrical coordinate system. In the cylindrical coordinate system, first I have told you how to convert these Cartesian coordinate system into cylindrical and into spherical coordinate system. You just have to remember these angle, what are the name of these angle. This is zenith angle, this is zenith angle, this is azimuth angle. And we have just given you one equation, that is generalized conduction equation in 3-dimensional. And after putting this equation, we have taken the different cases. He may ask you for 1-dimensional, you can write like this. With heat generation, you can write like this. Without heat generation, you can cut this. For 2D, you can cut this. For unsteady flow, you can write this. Now coming to the next point, we have taken the first case was without heat generation. And in this case, I have told you one thing, that in case of the cylinder is solid, then the temperature at the center line of the cylinder will not define. And if the cylinder is hollow, then the temperature at any point can be calculated by this, and temperature profile will be logarithmic. Now coming to the next point, we have also discussed for 1D with heat generation steady flow in case of the cylindrical coordinate system. So we have got the equation like this. And again, if heat generation takes place, it means the temperature at the center line will not define in case of the solid cylinder. And if heat generation takes place, if the cylinder is hollow, then the temperature profile will be parabolic. So from here, we have got the two equations. You can remember any of the equation what you want to remember. After that, we have discussed about the sphere, and in case of the heat transfer through the sphere, the formula is like this. R critical, we have discussed already, it is what, 2K by H, and what is the significance we have discussed in deep. Now, so from here we can write the generalized conduction equation by using the cylindrical coordinate system. So we have to remember only cylindrical coordinate system. Also, I have given you the temperature. If you want to calculate at any point in case of the sphere without heat generation, you can calculate by using this. Now coming to the next point, we have discussed this table. You have to remember this table, and most of the things you can just compare from here. Just what is the temperature profile, whether it is linear, parabolic, whatever. Now coming to the next topic. So now coming to the next topic, that is logarithmic and geometric mean area. In case of the logarithmic and geometric mean area, he will simply ask you, whenever the heat transfer is taking place through the cylinder, and if we are making an equivalent wall of the cylinder. In that case, let's suppose it is a cylinder and we are cutting this cylinder, we are making an equivalent wall. In that case, we will get the mean area in the form of logarithmic mean, that is given by surface area of outer side minus surface area of inner side upon ln of surface area outer side upon surface area of inner side. How we will calculate? We will simply calculate like this. Let's suppose we are making a wall, and in that case, inner radius and outer radius, that will be the thickness of the wall. And in that case, we are just saying, since we are making an equivalent, so Q through the wall and Q through the cylinder remains same. It means we will write delta T by RTH of the cylinder, and delta T of the RTH of wall will remain same. So temperature is same since the wall is same. So from here we will get RTH of the cylinder is equal to RTH of the wall. And from here, if you just multiply, if you just put the values, you will just write the mean area, and you will get in this form, that is surface area outer side AM is equal to AS2 minus AS1 upon ln of AS2 minus AS1. Now similarly, we can also calculate for the sphere, and in case of the sphere, the mean area is given by, we can write like this. In the mean area is equal to what? Under root AS1 and AS2. Whenever you will calculate, just you have to put RTH of the sphere is equal to RTH of the wall. You will get AS1 into AS2, and from here you can write it is 4 pi Rm square. It is equal to under root 4 pi R1 square into 4 pi R2 square. You will get like this. So 4 pi will be finished. Rm square will be equal to under root R1 into R2. and Rm will be what? Under root of R1, R2. So from here you can also calculate the geometric mean radius. It will simply ask you, in a sphere the heat transfer by conduction is taking place, what will be the geometric mean radius? What will be the mean radius? In case of the sphere, you always have to calculate the geometric mean radius. In case of the cylinder, you always have to calculate the logarithmic mean area. It is simple, you just have to remember these two formulas, geometric mean areas and logarithmic mean areas. If he is asking about the cylinder, it will be logarithmic mean area. If he is asking about the sphere, it will be geometric mean area. And also you can calculate the geometric mean radius. Now let us come to the next chapter, and the next chapter is unsteady state conduction heat transfer. Initially, up to here we have studied about the steady state conduction heat transfer, in which properties were not changing. But in case of unsteady state conduction heat transfer, it is obvious that properties will change with respect to time. So in that case we can just take a solid. Let's suppose we have a solid body, which is initially we are removing from the furnace. If we have removed from the furnace, let's suppose mass of the body is m, density of the body is rho, specific heat is C, volume of the body is V, initial temperature when it is removed from the furnace is Ti, area, surface area of the body is A, like this. Whenever we have removed from the furnace, it is obvious it start losing heat from its surface. And when it start losing heat from the surface, it means what I want to say, whatever the amount of heat loses from the body, it will directly equal to rate of decrement of the energy of the body. So we can directly write, we have the three forms of the energy, kinetic, potential and internal energy. If we just take the difference or decrement, we will write d of this, d of this and d of this. Since it is a solid body, so I think there is no change in the kinetic energy, and it is put it at any place, so there is no change in the potential energy. What will be the change? There will be only a change in the internal energy. That's why we always take rate of change of total energy will be equal to rate of change of internal energy of the body, since it is a solid body. So from here we can easily write U is equal to what? Du is equal to mc dt, and we have written mc dt by dt. Now in the case of unsteady state, you just have to remember only one concept. The concept is what? Rate of heat loss by the convection is equal to decrease in the internal energy of the system. So rate of heat loss by the convection is equal to what? HAT minus T infinity, where T is the temperature at any point and T infinity is the temperature of environment. From here, it is the loss in the internal energy, so decrease in the internal energy we are putting minus, and from here we can just put the boundary conditions. What the boundary condition? That T is equal to 0, we can take T is equal to Ti. At T is equal to any time, then the temperature will be any of T. And from here if I just put the value, we can write like this: T minus T infinity upon Ti minus T infinity, which is a well known formula to you. You have to remember this formula. In case of an unsteady state for conduction heat transfer, first concept is this: H into A into T minus T infinity is equal to minus mc dt by dt. If the body is losing heat, in case if the body is gaining heat, it will become positive. Now what I want to say, from here this formula will be what? T minus T infinity upon Ti minus T infinity is equal to e raised to the power minus h into A into T upon rho Vc. So you will put like this, but the condition behind to use this formula is, whenever you are using this formula is only valid when the lumped heat criteria is applicable. When the lumped heat criteria is applicable. And before applying this formula, first we will know what is lumped heat criteria. Look, let's suppose we have a body. Let's suppose we have a body. This is a body, and we are just removing this body from the furnace. Whenever you will remove this body from the furnace, it is obvious it will start losing heat. At a time you will touch the body and you will say the temperature is T. But what I want to say, you will simply assume the temperature of the body at each and every point is same. Means if the body is like this, it means you will say the temperature of the body at this point, at this point, at this point, at this point, it will always same at each and every point. It means the temperature gradient with respect to space is not changing. In any of the body, we always assume the temperature at any instant of time will be same at each and every point. So, in case of the lumped heat criteria, it is assumed that the temperature at each and every point will remain same. Means the temperature gradients with respect to space are not changing. They will change with respect to time. And to analyze this, what we can say, we can simply say if temperature at each and every point is same, it means heat is transferring from here to from here like this. Initially we have studied like this, but in that case the heat is transferring, means we can say the conductivity should be infinity. If the conductivity is infinity, then only it is possible that the temperature of the body at each and every point is same. So, at this point, we first take the conductivity at each and every point is same, and if the conductivity at each and every point is same, it means there will be no resistance. And it is defined by Biot number. Biot just has assumed that internal conduction resistance and external. Over here it is losing heat by convection, and over here up to here it is losing heat by conduction. So from here we can say if there is no conduction resistance, it means conduction resistance is what? L by K into A. It means conductivity should be infinity, which is not possible. Conductivity of any material is not possible. That's why Biot number has given an analysis that we will take the ratio of internal conduction resistance to the external convection resistance. And if this ratio will become very less, then we will assume this condition will be satisfied. Either if this resistance becomes 0, that is ICR by ECR we are taking, external convection resistance, internal conduction resistance. If this becomes 0, it means automatically this becomes 0. Either it is not possible. It is not possible. So what we will show that the ratio of ICR upon ECR, it should be very less, almost close to 0. So in the lumped heat criteria, we have assumed that if the value of Biot number is less than equal to 0.1, then only we can assume the temperature within the body at each and every point is same. So whenever he is giving you the questions on the unsteady state, the first target is to check the lumped heat criteria is valid. And to check this, you just have to calculate the Biot number. Biot number is what? It is Hs by K of the solid. You will just put the values, and if the Biot number is less than 0.1, then you will apply the formula. And if it is not less than 0.1, then you will not apply. It is the most, definitely they will ask you the problem from here in the mechanical engineering. Now coming to the next point. Here H is nothing, it is the heat transfer coefficient. S is what? It is the characteristic length, and K is the conductivity of solid. So here we are just defining S. In case of the sphere, S is nothing, it is V by A. V by A. And if you will calculate for sphere, V by A is R by 3. In case of the cylinder, it is R by 2. And in case of the cube, it is A by 6. I always suggest you just remember these three values. Generally, they will ask the problems from here. If they are asking like this, you will simply write in the formula. In the formula, you are getting a value of A by B. I have given you the value of V by A. You just put, for sphere, you will put 3 by R. For cylinder, you will put 2 by R. For cube, you will put 6 by A, like this. So this formula is very, very important for you. And how we will use this formula? We will first apply the lumped heat criteria. After applying, you can only put the value. Now coming to the next point. Here this rho Vc, this is HAT by rho Vc. It means rho Vc by HA will have the unit of time, since it will become T by T. It will become T by T. So if it become T by T, then the unit become. Now from here we says that this rho Vc by HA, this is known as time constant. Time constant is what? Time constant always gives that when a body removed from the furnace, at what earliest time, it will not give the time, it will just how fastly it will reaches to the local environment. It will not give the time, it will just tell about how fastly it will reaches to the local environment. So from here you will just calculate the time constant. Sometime he may give you the time constant. So this formula will be equal to minus T by tau. Sometime he will give you the time constant, he may ask you what is the time. So you can calculate the time from here. Time constant just signifies how much fastly the body is reaching to the local environment, that you have to calculate. So this is the time constant. Now one more thing, in case of the fluids, when you study the fluid, in case of the fluid, it will resemble the Nusselt number. Sometimes they may ask you Biot number resembles or Nusselt number resembles. Biot number resembles Nusselt number resembles Biot number. Formula is approximately same. This L is also a characteristic length. In Nusselt number we use K of the fluid, and Biot number we use K of the solids. Biot number is always less than 1 since it is heat transfer coefficient, and K of the solid is a large value, and in that case K of the fluid is very, very small value. That's why Nusselt number is always greater than 1. This will be less than 1. You have to remember. This is what we have represented, the graphical representation of this. We have represented the graphical representation. This is dt by dt, and this is what? dt by ds. It means there is no change in the spacious direction, with respect to space. If the body is losing heat, it will exponential curve will be like this, and if the body is gaining heat, the exponential curve will be like this. You just have to remember only one formula and how to use this formula. They will simply ask you, let's suppose we are just putting a ball. We are putting a ball into the water, which is coming out from the furnace. At what time the temperature reaches to this, or how much time it will take to reach this temperature, or at this time the temperature will be. So these types of the question they will simply ask you, and the formula is this. Formula is simple. It is this, and in this formula you can just put the values V by A by V. I just suggest you will always write A by V value, since we don't need so much calculations. So you can put like this, or in the PSUs they will simply ask you the problem. They will simply ask you the problems like this. Now coming to the next point, one more point we can discuss over here. We have studied the formula. It is T minus T infinity upon Ti minus T infinity is equal to e raised to the power minus HAT by rho Vc. So we are just converting in terms of the Biot number. Biot number is what? HS by K of the solid. So from here, this is what? we will be writing like this, minus H into, S is what? H into T upon rho into C into V by A is what? S. V by A is what? S. Now we have to just convert in terms of the H's by K. So we are multiplying by S and also by S. Now if I just multiply, so also by K, so let us multiply by K. So from here, if I'm just writing Hs by K, it is minus of Hs by K into. From here, we can write like this, K by rho into C. K by rho C into, we can write, it is what? T by S square. T by S square. This Hs by K is what? It is the Biot number. It is the Biot number. So we will be writing like this. It is minus of Biot number. No, I'm not writing E, into this K by rho C is known as alpha into T upon S square. S is the characteristic length. So this alpha T by S square is what? It is known as Fourier number. So sometime you will get the formula like this also. T minus T infinity upon Ti minus T infinity is equal to e raised to the power minus Biot number into Fourier number. Fourier number is nothing, it is alpha T by S square, like this. So you can also calculate the Fourier number from here. Now coming to the next topic, that is fins. Fins, if I just simply ask about the fins, fins are what? Fins are the projections protruding or coming out, which are used to increase the rate of heat transfer coming out from the hot surfaces. Why we use fins? Let's suppose we have a transformer or we have an engine. In case of the transformer or engines, when the heat transfer takes place, let's suppose combustion is taking place inside an engine, and if combustion takes place, no doubt we have to remove some amount of the heat from the cylinder. If we have to remove some amount of the heat from the cylinder or from the engine, then what we will do? This heat will be removed by the convection. And in case of the Q through convection is equal to what? H into area, surface area into delta T. What we can do? We can increase the temperature difference. We can increase the temperature difference, which is not. So let's suppose we have an engine. We will not increase the temperature difference, environment and this temperature. First thing. So we cannot use this. Either we can change the fluid. Either we can change the fluid by increasing H, or we can increase the surface area. So what we will do? Fins are the projections or surfaces which are used to increase the rate of heat transfer by increasing the surface area. They simply increasing the surface area without altering the fluid. Since in the environment, if the engine is running in the environment, we cannot change the environment. So the temperature of the environment remains same. So H of the environment will also remain same. That's why we cannot change this. We cannot change this. What we will accept? We accept the increment in the surface area. That's why in case of the engines or in case of the transformers, we use fins. By increasing the surface area, you can also increase the rate of heat transfer. So simply you can put like this. Now coming to the next point. In that case, so we use the fins to increase the rate of heat transfer by increasing the surface area. Now let us take some analysis of the fin. We have steady state 1D analysis in the fin. Let's suppose this is known as what? This is the bed of the fin. Bed of the fin, or we can take, it is a base plate. From the fin is coming out. And it is a fin like this. We are taking a fin. We are not assuming whether area is increasing, decreasing. It may increase, it may decrease, or it may remains constant. Now, what concept we use? We simply use over here, let's suppose the heat transfer is Qx and heat transfer is coming out from here is Qx plus dx. First, we have to know the concept behind the fin. What concept? Let's suppose fin is coming from here. It means whatever the heat which is coming from here, heat transfer will take place into the fin. This is the heat which is coming from here, source. And when it transfer through the fins, it means it will also transfer by the conduction and also by the convection, since fluid is in contact. So, in this direction it will transfer by the conduction, and in this direction or in the environment it will transfer by the convection. So, the mechanism of the heat transfer through the fin is heat get conducted in the direction along the length, and simultaneously it is get convected to the environment. So, we use the concept like this. Whatever the heat which is coming, it will just transfer by two types. One is what? It is Qx plus dx, which is coming out like this, and also similarly by the convection, which is like this. Now, let us, if I just take, so from here we can easily write, if I just solve this energy balance equation, we got the equation like this: del 2 t upon del x2 plus 1 by ax del ax by del x into dt by dx minus hp by k into ax. Why I am taking ax? Since we are assuming, let's suppose area is varying with respect to x, is equal to 0. And after solving this, if it is assumed that the whatever the fin, let's suppose it is a fin and area of the fin is not changing. If area of the fin is not changing, it means you will just, this will be what? 0. Initially, this is the basic governing equation for the fin. Del 2t upon del x2 plus 1 by ax del ax by del x into dt by dx minus hp by kx t minus t infinity. But if area is not varying, so then the governing equation will be like this. Now, in the fin we can assume this t minus t infinity is theta. So, from here we can take dt by dx is equal to d theta by dx. So, dt by dx2 is equal to d theta by dx2. We are assuming this hp by kx is equal to what? M. If I just put the value, we got the equation d2 theta upon dx2 minus m square theta is equal to 0, which is a second order differential equation. And you all are aware with this, the second order differential equation solution will be given by theta is equal to c1 e to the power mx plus c2 e to the power minus mx, where c1 is what? C1 and C2 are constants. So, please remember, you just have to remember this equation only. Now, coming to the next, this is the first. Now, the solution of this differential equation is given by the boundary conditions. And the first boundary condition is very simple. At x is equal to 0, t is equal to tb. It is obvious. First boundary condition is what? X is equal to 0, t is equal to tb, means theta is equal to, we have studied t minus t infinity. T minus t infinity means theta is equal to, we will got tb minus t infinity, which is known as theta naught. And other boundary conditions are like this. So, we have taken the first boundary condition. Let's suppose the fin is infinitely long. If the fin is infinitely long, in that case, the formula will be solved. After solving, the formula will be like this. We are not deriving the formulas. So, formula will be theta by theta naught is equal to e to the power minus mx. And this theta is what? T minus t infinity. Theta naught is what? Tb minus t infinity is equal to e to the power minus mx. This is the case for infinitely long fin. It means in case of the infinitely long fin, this theta by theta b varies according to e to the power minus mx. And this is t infinity, this is tb. the variation will be exponential. You have to remember this. In that case, also he may ask you what is the efficiency of fin. If he is asking the efficiency of the fin is nothing. It is the ratio of maximum possible heat transfer from the fin upon the heat transfer from the fin when the fin is maintained at the base temperature, that is maximum temperature. And when you calculate, you will get 1 by ml. Now what I want to say, in case of the infinitely long fin, as L tends to infinity, that's why you always get the efficiency of the fin is minimum. So whenever he is simply asking what is the minimum efficiency, when will be the minimum efficiency in case of the fins. So first case, that is fin is infinitely long, will get the minimum efficiency. What we have discussed from here, initially we were discussing about the unsteady state. Unsteady state, in that case we have just studied the properties are changing with respect to time. And in that case, the properties are changing with respect to time. You have to remember only one formula, that is T minus T infinity upon Ti minus T infinity. Also, you have to remember in that case, this is what T. Also, you can write it is what e raised to the power minus T by tau, or also you can write e raised to the power minus Biot number into Fourier number. Whatever the form, you can just write like this. Fourier number is what? Alpha T by S square. So in that case, unsteady state, you just have to remember one formula, but that condition is what? When the formula can be used. Formula can only be used when the lumped heat criteria is valid. And lumped heat criteria is what? Internal conduction resistance to the external convection resistance. The ratio between this is always less than equal to what? 0.1, almost close to 0. So it was the description about unsteady. Then we have started the fins. And in case of the fins, we all know fins are the projections or surfaces coming out from the hot surface, which are used to increase the rate of heat transfer coming out from the hot surface. So we have got three cases: either we can increase the temperature, or we can increase the fluid, or we can change the fluid, or we can increase the surface area. So we have chosen third option by increasing the surface area. This was the study of the fin. And in the fin, the mechanism is what? Heat transfer takes place by conduction as well as convection. So in that case, when we have studied, this is the governing equation for the fin, and this is the governing equation when area of the fin is not going to change. Now from here, we have assumed some value where m is equal to under root hp by ka, and we have got the equation like this. Theta is equal to c1 e raised to the power mx plus c2 e raised to the power minus mx. We have solved this theta for three different boundary conditions. First boundary condition is fin is infinite long, and in that case the formula is this, and after that the graphical representation is this. After that we have calculated the fin, and we are aware with this. In case of the infinitely long fin, we will get the minimum efficiency. Now coming to the next. So next we have calculated the efficiency for infinitely long fin, that is neta of the fin is equal to 1 by ml. We have discussed this, it will be the minimum efficiency in case of the infinitely long fin, and in general the infinitely long fin will get the efficiency less than equal to 20%. When we say the fin is infinitely long, when the efficiency is less than equal to 20%, then we will say the fin is infinitely long fin. So in that case, this can be written as what? 20 by 100. So we can write this efficiency is what? 1 by ml less than equal to 1 by 5. It means for long fin we can say ml should be greater than equal to 5. Simply he will ask you in the objective problem, what is the condition for the long fin? For the long fin, you can just see it is ml greater than equal to 5. For long fin, it should be what? Efficiency should be less than 20%, or you can write ml should be greater than equal to 5, or the length of the fin should be greater than equal to 5 by m. If the length of the fin is less than 5 by m, then you will say the fin is short fin. You just have to remember the condition for long fin and short fin, when you will say it is a long fin, when you will say it is a short fin. Now, one more formula is what? Heat transfer through the fin. When you calculate, you will get the formula like this. You don't have to calculate, just remember the formula. Q through the fin is under root HPK into A, TB minus T infinity e raised to the power minus mx. H is heat transfer coefficient, P is the perimeter. P is the perimeter. For example, the fin is like this, sum of these. This is the perimeter. K is the conductivity and A is the cross section area, not surface area. A is the cross section area. This is TB minus T infinity e raised to the power minus mx. Now, coming to the next point, the second boundary condition is what? Fin is finite in length and tip is insulated. If he is just taking fin is finite in length and tip is insulated, the condition is theta by theta naught is equal to cos. Formula, first formula is cos of hyperbolic m L minus x and cos of hyperbolic ml. L minus x means he is just asking at any x. Theta by t at any x he is just asking if it is what? T minus T infinity upon Tb minus T infinity. So, at any x he may ask you the temperature at any x. So, from here we can calculate the temperature, and also if he is just asking temperature at the tip, definitely you will write x is equal to L and you will get Tb minus T infinity. This is cos of hyperbolic ml, cos of hyperbolic ml. From here T is equal to Tb minus T infinity cos of hyperbolic ml plus T infinity. You will get the temperature like this. Now, heat transfer through the fin is given by, it is equal to under root HPKA, theta b is again Tb minus T infinity into 10 hyperbolic ml, into 10 hyperbolic ml, and efficiency of the fin is given by 10 hyperbolic ml upon ml. Now, the condition, sometime they may ask you when the efficiency of the short fin will be equal to efficiency of the long fin. So, we all are aware efficiency of the short fin is what? 10 hyperbolic ml by ml, and it is what? 1 by ml. So, we have equated, and 10 hyperbolic ml formula we have got, it is e raised to the power ml minus e raised to the power minus sine hyperbolic ml upon cos hyperbolic ml. Sine hyperbolic ml is what? Sine hyperbolic theta is what? E minus e by 2, and this is e plus e by 2. So, we have got, and when we will say the efficiency of short fin is equal to efficiency of the long fin, when this condition will satisfy. So, you remember this condition, they will ask the condition like this, and this condition is only valid when ml is greater than equal to 5. Okay, simply they will ask you when the short fin is said to be a long fin, when short fin is said to be a long fin like this. Now, for he may simply ask you for what value of ml efficiency of a short fin is maximum. We have the efficiency of short fin formula like this. So, we are just calculating the minimum. Let ml tends to 0, 10 hyperbolic ml upon ml. So, it is a 0 by 0 condition we have differentiated. After differentiating, we are getting sec square hyperbolic ml upon 1. Now, if I just put ml is equal to 0, we are getting 1. It means for ml is equal to 0, efficiency is 100%. For ml is equal to 1, efficiency is equal to 76%. For ml is equal to 2, efficiency is equal to 48%. So, he will simply ask you if the value of ml is equal to 0, then the efficiency is what? Or what is the minimum value of ml at which the efficiency is maximum? You can simply put it as 0. So, you can remember like this. As the ml value increases, efficiency, you can see as the length increases, definitely the efficiency will decrease. So, from here you can calculate. Now, coming to the third case is similar one to the second case. It is what? Fin is finite in length and uninsulated tip. Fin is finite in length and uninsulated tip. So, in finite in length, we will just use the characteristic length if uninsulated tip is there. So, in case of the uninsulated tip, the formula will be exactly same, just LC will be replaced by, L will be replaced by LC. So formula is theta by theta b. It is cos hyperbolic m LC minus x upon cos hyperbolic. You can just also write theta naught. So from here Q through the fin formula will be same and efficiency will also be same. You just have to remember the value of LC. LC is equal to what? L plus D by 4. And over here, if the fin is rectangular, so this is in circular fin, it is L plus D by 4. And if the fin is rectangular, it is L plus T by 2, like this. So it is the description about the fin. You just have to remember these formulas and you will be able to solve the problem. One more question he may ask you from the effectiveness of the fin. From the effectiveness of the fin. So effectiveness of the fin is nothing, it is denoted by epsilon and it is given by Q through the fin upon Q without fin upon Q with fin, like this. So he just simply asked Q with fin upon Q without fin. Q without fin. So Q with fin will be, you have calculated Q with fin. Any of the case you can just take the second case. It is equal to under root HPKA. H, this is the formula, HPKA theta naught tan hyperbolic ml. So let's put this theta naught tan hyperbolic ml upon Q without fin. It is Q without fin means, let's suppose it is a fin, it is a base and from here we have to just transfer the heat. So it is definitely equal to what? H into area of cross section into temperature at this point is TB into minus T infinity. So it is TB minus T infinity. From here this TB minus T infinity, TB minus T infinity will be cut it. And what we will get? We will get the formula for the effectiveness. It is equal to HA will be finished. So we will get under root Kp by HA. Kp by HA tan hyperbolic ml. Hyperbolic ml. So you will get the formula like this. Tan hyperbolic ml. So from here effectiveness of the fin you can just see it is the area of cross section, not area. So you can just Q with fin and without fin. What this effectiveness signifies? Effectiveness signifies when we are putting the fin, whether the putting the fin is worth keeping or not. Means let's suppose we are putting the fin in an environment of water. So whether we have to put the fin or not, we have to apply the fin or not. So this will be signified by the effectiveness, whether the putting the fin is beneficial or not. Efficiency tells about what is, whether the fin is efficient or not. So just try to understand, it is the effectiveness, that is with and without, and that was the efficiency. So just remember, efficiency is nothing, it is the actual upon maximum. Actual upon maximum, this heat transfer from the fin upon the heat transfer when the fin is at the base temperature. So I have missed this, you can just use and just remember the formula only. Just remember the formula only, formula is very, very easy. Okay. So it was the discussion about the fins, and in the conduction first we have calculated we have just seen the steady state conduction. In that case we have taken the three cases, number 1 wall, number 2 cylinder, number 3 sphere. And in case of the other unsteady state, in case of unsteady state we have taken only one formula. After that we have studied fins, and in the fins these are three cases, and it is important to you. You just have to remember the fin topic is not for chemical engineer. Fin only have to study for mechanical engineers. So now let us discuss the next chapter, that is convection. So we have discussed previously, convection is what? Convection is the mode of heat transfer which generally occurs when a flowing fluid comes into the contact with the solid boundary. Convection is the mode of heat transfer which generally occurs when a flowing fluid comes into the contact with the solid boundary. So convection is nothing we are just going to discuss. We have just discussed convection is of two types, that is forced convection as well as free convection. So now we are going to revise the convection one by one. Look, whenever you are going to solve the problems in convection, the main aim in convection should be is to calculate convection heat transfer coefficient or heat transfer coefficient. So whenever you are just attempting the problem on the convection, the main aim should be what? You have to calculate the convection heat transfer coefficient. Once you are able to calculate the convection heat transfer coefficient, you can easily calculate the heat transfer by convection. Since we have studied convection heat transfer is equal to what? H into A into delta T. So the main focus should be to calculate the convection heat transfer coefficient. And in the chapter, you have just focused how to calculate this convection heat transfer coefficient. And what is the way does not matter, you just have to calculate convection heat transfer coefficient. Now coming to the next, we have discussed that in forced convection, this heat transfer coefficient is a function of L, V, rho, mu, Cp and K, 6 properties. And in free convection, this heat transfer coefficient is a function of G, beta, delta T, L, V, rho, mu, Cp and K. So from here, beta is, you are aware with this, beta is nothing. It is the coefficient of volume expansion and it is given by 1 by B del V over del T under isobaric condition. Under isobaric condition means whatever you are just transferring the heat, it is either at the environment or pressure will be constant. Now coming to the next point, if I just calculate the beta for an ideal gas, so for an ideal gas, beta is given by T mean. T mean is what? 1 by T mean is what? Let's suppose air is coming into the contact with this pan. If air is coming into the contact with this pan, it means there will be some temperature of this surface and there will be some different temperature of the air. You just have to take the average of these temperatures. The average of these temperatures, that will be the T mean. You always, let's suppose that you are calculating the density, density, kinematic viscosity, whatever. All the properties will be taken at an average temperature, that is T mean. And the temperature should be in absolute scale. So the unit will be per Kelvin, not in per degree Celsius. You just have to remember how to calculate T mean. Now, so we are starting the forced convection, and in the forced convection, first there will be two cases. Either first case will be either the flow will be inside a pipe or a duct, and second case will be either the flow over a flat plate. So in case of the pipe or duct, we can get two types of the flow. One is known as laminar, another is known as turbulent. If the flow is laminar, it means the velocity profile inside the pipe will be what? Parabolic profile. Generally, they may ask if the fluid flowing in a pipe is laminar, then the velocity profile will be. You have studied in the fluid mechanics, the velocity profile will be parabolic. Look, in case if you are just studying the convection, it is necessary that you have to understand the fluid mechanics, basics of the fluid mechanics. You need to just apply some fluid mechanics formulas over here and some fluid mechanics concept. Most important thing is boundary layer. So we will discuss something. Now coming to the point, in case of the flow taking place through a pipe or a duct, then if the Reynolds number is less than 2000, it is obvious, then the flow will be laminar, and it is greater than 4000, then the flow will be turbulent. And Reynolds number, the formula of the Reynolds number is what? Rho into V into D by mu, where D is what? It is characteristic length. D is what? It is characteristic length. This characteristic length will change according to the pipe or duct or plate, whatever. So in case if the fluid flow takes place inside a pipe, then this D will be nothing. It will be equal to dia of the pipe. If the fluid flow takes place inside the pipe, then definitely the dia of the pipe will be the dia, characteristic length or characteristic dia. And if the flow takes place inside the duct, that is rectangular pipe, if the fluid flow taking place like this, then the characteristic dia will be what? It is 4 area of cross section upon watted parameter. 4 into area of cross section upon watted parameter. Area of cross section is what? It is x cross y. And watted parameter is what? This plus this plus this plus this. So we have written it is 2 times of x and 2 times of y. When we solve, the characteristic dia in case of the rectangular pipe will be 2xy upon x plus y. You just have to remember, they have asked the problem one time in the case when the flow was taking place through a rectangular duct. And in case of the rectangular duct, you have to calculate this characteristic length or characteristic dia. Now coming to the next point, if the fluid flow takes place over a flat plate, if the fluid flow takes place over a flat plate, let's suppose we have a flat plate and fluid flow takes place. And if it is like this, in the plate case, the Reynolds number will be different. Reynolds number is what? If Reynolds number lies between 2 to 5 into 10 to the power 5, then the flow is said to be laminar. Sometimes they just take 2 into 10 to the power 5 and sometimes they take 5 into 10 to the power 5. Means whenever you are getting the Reynolds number less than 5 into 10 to the power 5, you will definitely say the flow is laminar. If the flow is over a flat plate, in case of the pipe or a duct, the formula will be or condition will be different. So if the fluid flow takes place over a pipe or duct, if Reynolds number is less than 2 to 5 into 10 to the power 5, then the flow is said to be laminar. And if the Reynolds number is greater than 6.5 to 7 into 10 to the power 6, then we will say the flow is turbulent. Now, if the fluid flow takes place, let's suppose we have a plate and fluid flow takes place like this. And at some point, let's suppose this flow start changing from laminar to turbulent. At the point at which flow start changing from laminar to turbulent, that point is known as critical point. That point is known as critical point. Means from here the flow start changing from laminar to turbulent. It means at this point we will write this number is known as critical Reynolds number. So sometime he may ask you what is the critical Reynolds number. So critical Reynolds number is 2 into 10 to the power 5. Either he will give you in the option 2 into 10 to the power 5, or he will give you in the option as 5 into 10 to the power 5. Whatever the option, you just have to absorb. Okay, so he will give you only one option. If he has given both options, then you have to multiply and just take 2 into 10 to the power 5 as the critical Reynolds number. Now, in that case, if the fluid flow takes place through a pipe, in this case also you can take the critical Reynolds number. What? After 2000 it start changing from laminar to turbulent, means critical Reynolds number is what? Critical Reynolds number is what? It is 2000. After 2000 it will never be a laminar flow, it will be under transient condition. So we says critical Reynolds number will be what? It is 2000. So from here it is just one more thing. In case if he has not given flow over a flat plate, he has just given the flow over a flat plate and he has not given the type of flow. In that case you can say, yes, Reynolds number value is very high, and if the Reynolds number value is very high, it means the flow can be assumed to be laminar. So whenever if type of flow is not given, in case if the fluid flow takes place over a flat plate, then it is known as the laminar, then it is assumed to be
laminar flow. And in case of the pipe or duct, since the Reynolds number value is very, very less, that's why in case of the pipe or duct, we generally assume the flow is turbulent flow if it is not given. In case of the plate, we assumed the flow is laminar flow, and in case of the pipe or duct, flow is assumed to be turbulent flow. Now, coming to the before solving the convection problems, let's suppose we have a fan and we have started the fan, or we have to design the fan. Fan, AC, whatever we are designing, radiator, where the convection heat transfer takes place. If we have to design these instruments, so before designing, we have to calculate that all the instrument should be dimensionally balanced. Dimensionally balanced means, let's suppose a fan is running or a cooler is running. In case fan is running, what it will do, it will just start blowing the air. If the air will start blow, so first we have to take the balance condition, whether whatever the air is provided by the fan, it is up to the level, whatever the people who are getting the air will be able to get the air or not, or at what distance they will be able to get. Or in case of the cooler or in case of the AC, what amount of heat, let's suppose we are taking an AC, what amount of heat it is rejecting. So what will be the size of the room? These will be decided by the convection. For example, it is just one is fluid flow, another is solid. Now, in these cases, before designing any of the instrument which is just calculating, the convection heat transfer, first we calculate whether the instrument, before designing, first we calculate whether the instrument is dimensionally balanced or not. If the instrument is dimensionally balanced, then we start designing the instrument. So for the dimensional balance, we use Buckingham pi theorem before solving the convection problem or conduction problem. So we use first Buckingham pi theorem, and by using the Buckingham pi theorem, you can easily calculate whether the system is dimensionally balanced or not. You all are aware, Buckingham pi theorem says what? In any system, if there are n number of total variables and m number of fundamental variables, then the system can be grouped into n minus m number of dimensionless terms. It means from here, in case of the forced convection, we have how many variables? 3, 3 and 1, that is 7 variables. So n is equal to, he has given 7, m is equal to what? Length, mass, time and temperature. So in case of the heat transfer, you will get 4 fundamental variables. So n minus m will be what? 3. Means in this case you will get, in case of the forced convection, you will get 3 pi terms. So 3 pi terms are these. When you solve these pi terms, pi 1, pi 2, pi 3, and when you solve, you will get the relation as Nusselt number is equal to function of Reynolds number and Prandtl number. Means you just have to remember one thing, that in case of the forced convection heat transfer, what will be the condition? The condition is, if Nusselt number is a function of REPR, or you can write RE is a function of NUPR, whatever, means if these numbers are in such a manner, then definitely you will say the system under forced convection is dimensionally balanced. Before studying the forced convection or before designing any part of the system which is working on forced convection, you should have to take the dimensionally balanced. Means if any system is satisfying this condition, then you will start solving the problems or start designing the system. After, in that case, Reynolds number, you all are aware with this, it is rho Vd upon mu. Prandtl Nusselt number is what? It is Hd by K of the fluid. We have discussed. K of the fluid is very less. That's why you get Nusselt number is greater than 1. Now, similarly, we have studied the Biot number. Biot number is equal to what? HS by K solid. This S and D are nothing. These are the characteristic dia. So, in that case, Biot number we always get as less than 1 since K of the solid is very high. So, in that case, Nusselt number is nothing. It is SD by K of the fluid. Sometimes they may ask, Nusselt number resembles Biot number and Biot number resembles Nusselt number. Nusselt number we use in case of the fluids, Biot number we use in case of the solids. Nusselt number always greater than 1, Biot number always less than 1. So, you have to remember like this. Now, coming to the next point, next number is Prandtl number, which is the most important number in case of the forced convection heat transfer. Now, coming to the next point, the Prandtl number is what? Prandtl number is equal to mu into Cp by K. Mu into Cp by K you have studied. I am assuming, I am just revising you. So, Prandtl number is equal to, we can write mu by rho and rho Cp by K. We have just multiplied and divided by rho. This mu by rho is known as nu and K by rho Cp is known as alpha. And hence, this Prandtl number is what? It is equal to nu by alpha. That means we can write nu represent what? Nu represent the molecular momentum transfer, means the fluid whose nu is more, kinematic viscosity is more, will have the more hydrodynamic boundary layer thickness. And alpha represent what? It is molecular energy transfer, means the fluid which have more alpha will have more thermal boundary layer thickness. So, Prandtl number is the only dimensionless number which represent or which gives the relation between hydrodynamic boundary layer and thermal boundary layer, which simply says Prandtl number is the only dimensionless number which is the connecting link between hydrodynamic boundary layer and thermal boundary layer. You just have to remember, they will ask you which number is the connecting link between hydrodynamic boundary layer and thermal boundary layer. And from here, we all are aware that Prandtl number is the connecting link between hydrodynamic boundary layer and thermal boundary layer. It represent what? HBl. It represent what? TBl. So, Prandtl number gives the link between, the relation between HBl and TBl. Now, one more thing, he may ask you which number represent the property of fluid. In that case, you are seeing, you can see that nu is also the property of fluid and alpha is the property of fluid. So, Prandtl number is the only dimensionless number which is the property of fluid and it gives the connecting link between HBl and TBl. You have to remember this line. Now, coming to the next point, from here we can easily say if Prandtl number is greater than 1, if Prandtl number is greater than 1, it means nu by alpha is greater than 1. And if nu by alpha is greater than 1, it means nu is greater than alpha. Nu represent what? HBl. Alpha represent TBl. It means you can easily say that the hydrodynamic boundary layer thickness will be greater than thermal boundary layer thickness. Simply they have asked the question so many times that if the Prandtl number is 1.1, Prandtl number is 2.2, if he has given the Prandtl number is greater than 1, then you just have to close your eye and just stick hydrodynamic boundary layer thickness will be greater than the thermal boundary layer thickness. Next point, if he has given Prandtl number as less than 1, it means nu by alpha should be less than 1 and nu will be less than alpha. If nu is less than alpha, then we will say the HBl thickness will be less than the TBl thickness. Means hydrodynamic boundary layer thickness will be less than thermal boundary layer. And if it is equal to 1, this nu by alpha is equal to what? It is 1, that is nu is equal to alpha like this. So you just have to remember whether the Prandtl number greater than 1, less than 1, equal to 1, what will be the condition? Greater than 1 means HBl greater than TBl, less than 1 means HBl less than TBl, and equal to 1 means HBl is equal to TBl. A simple concept you have to remember. Now coming to the next point. Next point is what? From here, the relation. Sometimes he may ask you, you are saying that delta is greater than delta T or HBl is greater than TBl. Now, what will be the TBl? So, in the fluid mechanics, you have just learned how to calculate delta. I think you have learned how to calculate deltas for various profiles. So, you can just calculate delta, and after calculating the delta, you will just put this relation. Delta T by delta is equal to 1 by 1.026 PR to the power minus 1 by 3. And you have to, from here, delta is what? It is hydrodynamic boundary layer thickness. And you are aware with this, what is this delta? I'll also give you some point that you have to remember. Now coming to the next point. The next point is, let's suppose we are discussing, this is what? This is hydrodynamic boundary layer thickness. So before studying this, before giving the table, I am going to discuss what is hydrodynamic boundary layer thickness and how the formation of hydrodynamic boundary layer takes place. It's a simple topic, you just have to remember. Hydrodynamic boundary layer thickness is what? We simply says, let's suppose we have a solid object like this, and a fluid comes into the contact with this solid boundary. If a fluid comes into the contact with the solid boundary, it attains the same velocity as the velocity of solid boundary. Means if the solid boundary is in rest, fluid will be in rest. If the solid boundary is in motion, fluid will be in motion. Relative velocity between the fluid and solid boundary will be 0. This is due to no slip condition at the surface. This is due to what? No slip condition, and this no slip condition is known as Maxwellian no slip condition. This is known as the Maxwellian no slip condition, since it is given by the Maxwell. Means fluid will stick over here, or we can say this layer will be the stagnant layer. This layer will be the stagnant layer. Now what I want to say, from here if any of the fluid particle comes into the contact, initially the velocity of the fluid particle becomes 0, and on the upper layer if the fluid particle comes into the contact, it will have some velocity and it will start increasing like this. It will start increasing like this. Like this. Means upper layer will have some velocity and upper and so on. Now what I want to say, how this boundary layer start forming. How this boundary layer start forming? We can say, let's suppose we have a plate. We have a plate like this, and a fluid comes into the contact with this plate. If the fluid comes into the contact with this plate, it means initially the fluid reaches to 0 velocity, and on the upper layer if fluid comes into the contact, it will feel some little less friction. It means it will have some velocity. On the upper layer as well as fluid start increase its velocity, and after some time it will reaches to some velocity. Now what I want to say, it means the velocity as we just take, let's suppose fluid is coming like this. Initially the velocity becomes 0, and as it goes up like this, velocity will continuously increase, and if velocity will continuously increase, at point, it means let's suppose it is u, let's suppose u plus du, let's suppose u plus 2 du, and the distance between them is dy. So we always says the reason in which velocity gradients are exist, the reason in which velocity gradients are exist, this reason is known as boundary layer reason. The reason in which velocity gradients exist, that reason is known as boundary layer reason. So boundary layer reason is nothing, it is the reason where velocity gradients exist. Now from here we just want to say the formation, we are just discussing the formation. Let's suppose the first particle comes over here, and it will just, when it comes into the contact, it will just reaches to zero velocity. Other particle comes, it will reaches like this and start decreasing its velocity. First layer will be stagnant layer, no doubt. Second layer, when the fluid particle comes into the contact, it will feel some less friction and it will go like this. After some distance, it will start decreasing its velocity, and after next layer it will start decreasing like this, and next layer, and we will say, we will get the condition like this. So what I want to say, if there is a velocity of u infinity over here, it means up to here we are getting the same velocity as the free stream velocity, and in this condition the velocity start decreasing. So in this reason there will be what, it is losing the momentum continuously, So in this reason the velocity will be very less, and as more and more area comes into the contact, these layers will have the very less velocity. As the fluid goes like this, it will start decreasing its velocity, and so on and so on and so on. So this region will have the lower velocity, and this region will also have the lower velocity. But over here the fluid is coming with a high velocity, and definitely it will have some, if high velocity, it means mixing will start. Then we can say, in this region if the velocity of the fluid is very less, that's why this region is known as laminar region, and this region is known as what, transient region, where velocity start changing. And over here the mixing is very high, in this region mixing is very high, that's why we always say it is turbulent region. So we have three regions, laminar, transient and turbulent. Now coming to the next point, this age is known as leading age, this age is known as leading age, and this age is known as trailing age. This is known as trailing age, and this is known as leading age, and this region is laminar region. In this case we simply says the velocity is very less, and in our syllabus we have to study only laminar region. I'm not going into very deep, just we have to take the study like this. So this region, in this region we will get the velocity is continuously increasing. It means this is a region where velocity gradients are found, and this region is known as boundary layer region. This region is known as boundary layer region. Here the difference in the velocities will be very high, here the difference in the velocities will be little bit less. Since all of the fluid particles will reaches to approximately same velocity, in this region the velocity will be very less, like this. So if he is asking about the slope, in this region the slope is minimum, in this region slope is increasing, and in this region the slope will be maximum. This is the slope of the velocity. Now coming to the next point, what I want to say, this is the boundary layer region, and in case of the hydrodynamic boundary layer, we always deals with the velocity gradients. Means we simply says the region in which velocity gradients are found, that region is known as boundary layer region. And in the boundary layer region, if velocity gradients are found, it means the fluid will be treated as viscous in nature. Tau is equal to mu into d over dy. And if the fluid is treated as viscous in nature, so in the boundary layer region, the Bernoulli equation is not applicable. In the boundary layer region, Bernoulli equation is not applicable. Not applicable. That's why we use the Navier-Stokes equation or the Prandtl boundary layer equation. We will simply ask you what is the governing equation within the boundary layer region, whether it is a thermal boundary layer or hydrodynamic boundary layer. The governing equation is Prandtl boundary layer equation, which is a special form of Navier-Stokes equation. I am writing the governing equation will be, the governing equation will be Prandtl boundary layer equation, will be Prandtl boundary layer equation, which is a special form of Bernoulli equation. So you have to take like this. Now why I am discussing over here, as in case of the hydrodynamic boundary layer, we says the region in which velocity gradients are found, that region is known as boundary layer region. Similarly, in case of the thermal boundary layer, we says thermal boundary layer, we says the region in which temperature gradients are found, that region is known as thermal boundary layer region. Look, let's suppose we have a plate like this, and we always discuss with the laminar region. Laminar region, there is no discussion. Whatever the velocity profile you always discuss, these are the velocity profiles when the laminar flow takes place over the plate. So velocity profiles will be for laminar flow. Similarly, the temperature profiles will also be for laminar flow region. So here we always says, let's suppose some fluid is coming, whose temperature is T infinity. So again we says, when a fluid comes into the contact with the solid boundary, it attains the same temperature as the temperature of solid boundary. So initially we says, let's suppose the condition is like this. We are heating this boundary. Q. We are supplying the heat flux like this. If we are heating this boundary, so initially the temperature of the fluid reaches as same, and as we goes up, the temperature start decreasing. Over here the maximum temperature, and upper layer will have the lower temperature, and so on, and we will get the condition like this. So in this case, we always say, let the temperature of this layer is T, then the temperature of this layer will be what? T minus delta T. Temperature of this layer will be T minus 2 delta T, like this. So just similar to the hydrodynamic boundary layer, there is a region where the temperature gradients are found. That region is known as thermal boundary layer region. You have to understand, thermal boundary layer region is nothing, the region in which temperature gradients are found. Now we are going to discuss about the thermal boundary layer. Coming to the next point. So thermal boundary layer is a region where temperature gradients are found. Thermal boundary layer is a region where temperature gradients are found. Now we are just going to discuss the mechanism of the thermal boundary layer. In the thermal boundary layer, first we supply the heat from here, and whatever the heat supplied, Let's suppose this is a stagnant layer, and on the stagnant layer this heat is first get conducted, and while conducting it is simultaneously get transported by the flowing fluid. So in case of the thermal boundary layer, initially the fluid is flowing like this. So we are just supplying heat like this. Initially the heat first get conducted through the stagnant layer passing through the solid, and after conducting, simultaneously conducting, it is get transported by the flowing fluid. Means in this case we are seeing that when the layer is a stagnant layer, there is no convection. Since convection only takes place when the fluid flows over the solid boundary, it means over here fluid is not flowing, it means there will be a conduction. And when this conducted heat will be given to the next molecule, it will be transported like this. And other molecule will transport like this, other molecule will transport like this. So, in case of the convection, heat transfer by the conduction is simply transported by the flowing fluid. Now, in this case, we simply says heat conducted from the stagnant layer will be equal to heat transported by the convection. We apply this formula, and it is heat conducted, that is minus K of the fluid into dt over dy, and y is equal to 0, and Hx is equal to this. Y is equal to 0, why? We are taking stagnant layer. So from here we got the formula, that is Hx is equal to minus Kf del T over del y, and y is equal to 0 Tw minus T infinity. This is the generalized formula for heat transfer coefficient. Means we have to calculate only heat transfer coefficient in whole of the convection. Now, in that case, this del T over del y is what? It is known as the spatial gradient of temperature. This is the spatial gradient of temperature at y is equal to 0. The del T over del y is nothing, it is the spatial gradient of temperature at y is equal to 0. Since all we can see that the conductivity of the fluid is fixed, Tw and T infinity are fixed, it means this Hx is directly proportional to what? Del T over del y. And it is obvious, when a fluid comes into the contact with the solid boundary, let's suppose the fluid is coming into the contact with the solid boundary, it has a temperature 20 degrees Celsius and solid boundary is at 100 degrees Celsius. So initially from here it will start attaining the temperature, it will start gaining the temperature. So from here what I want to say, this flowing fluid, initially the temperature of 20 degrees Celsius, then it will increase to 30, then it will increase to 40 and 50 and so on. So the temperature continuously increasing means the difference between this continuously decreasing. Means we can say, as the distance from the leading edge increases, this del T over del y at y is equal to 0 decreases. Means we will simply ask you, as the distance from the leading edge increases, spatial gradient at y is equal to 0, increase, decrease, may decrease, neither increase nor decrease. Yes, so we will say it will decrease, and this local heat transfer coefficient is a function of this or directly proportional to this. It means local heat transfer coefficient in the direction of flow also decreases. So you have to remember this concept, they may ask you in the objective type. Now coming to the next point, we are discussing the energy balance equation for thermal boundary layer. Look, energy balance equation for thermal boundary layer is just similar as the momentum equation in hydrodynamic boundary layer. In the hydrodynamic boundary layer, the momentum equation is what? U del U over del X plus V del U over del Y plus is equal to nu of del 2 U over del Y2. This is the Prandtl boundary layer equation, governing equation of the boundary layer, hydrodynamic boundary layer. Now, similarly we can write, in this case we are discussing with the temperature, so we will replace this velocity by temperature. And what we are getting, U del T over del X plus V del T over del Y is equal to alpha del 2 T over del Y2. This equation is just similar as the momentum equation in hydrodynamic boundary layer. And hence, the solution of the thermal boundary layer, energy equation in thermal boundary layer will be same as the momentum equation in hydrodynamic boundary layer. And in the hydrodynamic boundary layer, we will says when the fluid flow takes place over laminar fluid flow takes place over a flat plate, then various profiles attain, and the profiles are like this. This is a linear profile, u by u infinity is equal to y by delta, that is, in that case we obtain delta and we have obtained tau w. Delta is equal to Cx upon under root Rex and tau w is equal to k mu u infinity. You have studied the fluid mechanics, Mukesh sir has given you. Now in the second case it is what? It is a parabolic profile. So in parabolic profile you will get the C value as this when you solve this, but no need to solve this, you just remember this. After, it is a cubic profile which is most important to you. Generally they ask the question from cubic profile. So cubic profile C you will get 4.64. So delta is equal to 4.64 x upon under root Rex and k will be 3 by 2, and in the quadratic profile you will get like this, k will be 2, and in sinusoidal profile or trigonometric profile you will get C is equal to 4.8. So when you calculate delta from here, after calculating the delta, similarly we can say these are the velocity profile. If these are the velocity profile, similarly we can calculate the temperature profiles. So the temperature profiles are just like this. What you will do? You will just do, let the temperature of this surface is Tw and temperature of the free steam is T infinity. Now we are discussing at any point temperature. So we just, in that case, u by u infinity, here we will take the difference. From here u was the velocity at any point and u infinity was the velocity of free steam. Here we will take the difference at any point T minus Tw, and the difference what T infinity minus Tw. That will be equal to y by delta T. Similarly, we can get the parabolic profile, cubic profile, and also quadratic and also sinusoidal profile. Just the delta will be replaced by delta T. Just the delta will be replaced by, and further we try to solve these profiles. Look, why we are solving these profiles? What you will do, they will simply ask you what will be the local heat transfer coefficient for cubic profile. What will be the average heat transfer coefficient for the quadratic profile? So what you have to do? You will just simply first, one more thing is what? These profile, when you solve these profiles, it was like this: a plus b y by delta t and a plus b y by delta t plus c y square by delta t square. So we have calculated these values of a, b, c. So in calculations we use these boundary conditions. You have to remember these boundary conditions. We can say first, at x is equal to 0, definitely the boundary layer thickness will be 0, and at y is equal to 0, boundary layer thickness will be 0, thermal boundary layer thickness. Similarly, you can also use for the hydrodynamic boundary layer thickness, delta is equal to 0, delta is equal to 0, and at at x, y is equal to 0, this is 0, and obviously the temperature of the layer will be exactly equal to temperature of the wall, since it is a stagnant layer. And if the temperature is equal to the temperature of this wall, it means over here and over here this T infinity, this temperature difference will be maximum. That's why at y is equal to 0, we get this del T over del y as maximum. This is maximum value. And as we go up, this temperature difference continuously decreases. So from here, if del T over del y is maximum, means we have any function which is maximum. It means if we take the derivative of this function, it will become 0, and second derivative of this function, it will become negative, which will become third derivative. Similarly, at y is equal to delta t, We will say the temperature will be what? Sorry, T is equal to what? T infinity. At y is equal to what? We will reach T is equal to what? T infinity. And if T is equal to T infinity, it means at y is equal to delta T, del T over del y we will get either 0 or minimum value, since temperature is continuously decreasing. Now if T it is minimum, it means second derivative, first derivative of this, let suppose we have function, and if we differentiate, this differentiation will be 0 and third derivative will be positive for maximum minimum condition. So you just remember these conditions. In the PSUs they generally ask these conditions. For hydrodynamic boundary layer it will become what? It will become what? Del U over del Y is maximum. Del 2 over del 2 over del y2 is equal to 0, it is negative. Just replace by velocity. So that hydrodynamic boundary layer and also in case of the thermal boundary layer, you have to remember these boundary conditions. Temperature profiles and velocity profiles will be exactly same. Now, how you will calculate the boundary layer thickness, thermal boundary layer thickness? Look, we have given a relation in case of the Prandtl number. What we have given? We have given delta T by delta is equal to what? 1 by 1.026 PR to the power minus 1 by 3. We have given the relation. This is the relation. So first you will calculate delta for any of the profile. If he is saying it is a linear profile, you will use delta is equal to 3.46x upon under root Rex. If he is just saying for parabolic profile, you will say delta is equal to 5.48x upon under root Rex. So simply calculate delta. Re you can calculate easily. After calculating the delta, you will put the value in this. And after putting the value, you will get the value of delta T. Prandtl number for any of the fluid will be defined since it is a property of fluid. So from here you can just give, for example, cubic profile you have just taken delta, and after calculating the delta you can calculate the delta T. Now from here one more thing we want to discuss. After calculating the delta T, the main aim is what? Main aim is to calculate heat transfer coefficient. In any of the question, he will simply ask you to calculate the rate of heat transfer. And to calculate the rate of heat transfer, you have to calculate the heat transfer coefficient. So from here, you will just apply heat transfer coefficient equation. And for cubic profile, you have to calculate del T over del Y. Whether it is a cubic or it is a quadratic or it is a parabolic, whatever. So from here, you will just calculate del T over del Y. How you will calculate del T over del Y? You will just differentiate this. This T infinity minus TW will be over here, and you will just differentiate this. After differentiating, you will calculate del T over del Y. When you put the value of del T over del Y, for cubic profile, you will get the value of Hx like this. Means what I want to say, it is again a condition CKF by delta T. So from here, we can say, as in the velocity profile we have calculated tau w, in this case we will calculate Hx, that is CKF by delta T, and in this case you will get C is equal to 1, C is equal to 2, C is equal to 3 by 2 and C is equal to 2. You have to remember in this manner. So it's a simple, you can just either you can calculation will be like this. You will just write the profile and del T over del Y, and after putting the del T over del Y over here, you will get the value of Hx. So it is like this. For any of the profile, I have just taken an example for the cubic profile. Now, after calculating, what I want to say, from here this delta T we are getting like this, and it is obvious that Hx is directly proportional to delta T. And delta T is what it is, 1 by delta T, and delta T is what directly proportional to root x. It means we can say this Hx is directly proportional to x to the power minus 1 by 2. Means as x increases, distance from the leading edge increases, Hx will decrease. Whatever I have told you in the initial over here when we have started. So from here we can say as x increases, Hx will decrease. You have to remember, they will simply ask you the problem. And if they ask in the graphical manner in the laminar flow, you will get Hx, it is in the ratio of x, it is in the proportionality of x to the power minus 1 by 2. And in turbulent flow, you just remember for the PSUs, it will be x to the power minus 1 by 5. That is 0.2. And from here, at any point, if he is just asking Hx, so you will just compare, you will just give the value of Hx. Now, this Hx is, you all are aware with this, it is local heat transfer coefficient. If anywhere he is asking the average heat transfer coefficient, it is nothing, it is 2 times of the local heat transfer coefficient at the trailing edge. 2 times of the local heat transfer coefficient at trailing edge. Now, so this was the for profiles. What you will do for any of the profile? The condition is what? You just knows what? The fluid flows like this, and we are transferring heat like this. So whatever the heat we are transferring through the stagnant layer by conduction, it will be transported by the flowing fluid. So we will use the concept and we will get the value of Hx, that is minus kf del T over del T over del y at y is equal to 0 upon Tw minus T infinity. Now after solving this, we have taken the governing equation within the thermal boundary layer, and governing equation within the thermal boundary layer is just similar as the governing equation within the hydrodynamic boundary layer. Just velocity is replaced by the temperature, and hence the solution of the governing equation will be exactly same as we have got the velocity profiles. Similarly, we will get the temperature profiles. So whenever at any of the point, if he is asking the del T over del y value or Hx value or delta T value, what you will do? You will first calculate delta. After calculating the delta, you will apply this equation, and after applying this equation, you will easily get the value of delta T. Now the second point is, you also have to remember these boundary conditions. These boundary conditions are very easy. At x is equal to 0, definitely delta T will be 0. X is equal to y is equal to 0, delta T will be equal to 0. Y is equal to 0, this del T over del y will be maximum temperature difference will be over here, and you will apply like this. Similar in case of the velocity profiles. Now what we have done? We have just studied that for any of the profile we can calculate Hx at any point. This is the local heat transfer coefficient. And if we want to calculate the average heat transfer coefficient, it is 2 times of the local heat transfer coefficient at trailing edge. Now sometimes in the questions they may not give you the profiles. Many times they have asked the question, but the profile is not given. If none of the profile is given, then you have to use the Blasius equations. Blasius equations, you all are aware with this. In that case, delta you take 5x upon under root Rex, and in case of the turbulent flow, delta is equal to 0.374 upon under root Rex. So CFX is nothing, it is known as the local skin friction coefficient. Local skin friction coefficient or local drag coefficient. This local skin friction coefficient, by using this this was the Reynolds-Colburn analogy. Recently they have asked the problem, they have asked one question in the ISRO exam. So it's a Reynolds-Colburn. By using this, we will calculate the heat transfer coefficient just coming over there. And CFX in case of the turbulent, it is given by this 0.059 upon under root Rex to the power 1 by 5. And CD is just double of it. It is 0.664 upon REL, average Reynolds number at trailing edge to the power 1 by 2. And in this case, it will be 0.074 upon REL to the power 1 by 2. You can neglect this. You can take this 0. Since it is 2 into 10 to the power 5, this is the approx value, you can go with this. So, it is what? These equations will be used when none of the profile is given. Up to when they have given the profile, you will solve like this. If they have not given the profile, then you will use the equation like this. Now one more thing we are going to discuss. If none of the profile is given, then we can use the equation for the Nusselt number for laminar flow over the turbulent flow as well as turbulent flow over a flat plate. Okay, comes to the next. Now for laminar flow over a flat plate, and if the laminar flow is taking place over a flat plate, then the equation for Nusselt number can be given as Nusselt number is equal to 0.332. If none of the profile is given, just simply saying laminar flow over a flat plate. So, you can also use this equation, and the equation is 0.332 Rex to the power 1 by 2 PR to the power 1 by 3. Also, this is for local Nusselt number. Why? I am writing Rex since we are writing local Reynolds number. But the Prandtl number will not be local since it is a property of fluid. I have told you Prandtl number is the only dimensionless number which is the property of fluid and which gives the connecting link between hydrodynamic boundary layer and thermal boundary layer. So, it is the property of fluid, and Nusselt number we can write as the average Nusselt number. Average Nusselt number will be what? 2 times of the local Nusselt number, and it will be what? Reynolds number at the trailing edge, since we have just written 2 times. Now, so you can use, if he is asking the average Nusselt number, you can calculate like this. Now, coming to the next point. Next point is what? Prandtl number, if you want to remember, you can remember. Prandtl number lies between 0.65 to 0.71, and for air, the Prandtl number at 20 degrees Celsius is given by 0.69. For water, the Prandtl number lies between 2 to 6. What I want to say, from here you can easily write Prandtl number is less than 1, means nu by alpha is less than 1, means nu is less than alpha. So, we can say from here the thermal boundary layer thickness will be greater than as compared to hydrodynamic boundary layer. For air, if we is simply asking the problem for air, the thermal boundary layer thickness and hydrodynamic boundary layer thickness, thermal boundary layer thickness will be greater as compared to hydrodynamic. And over here, if he is asking, you can easily write nu greater than alpha. It means hydrodynamic boundary layer thickness will be greater than thermal boundary layer thickness. So, it is a simple analysis, you can just take the analysis. Now, if he has given that the flow is turbulent over the flat plate, if the flow is turbulent over the flat plate, then you will use this equation. Nusselt number is equal to 0.036 Re to the power 0.8 PR to the power 1 by 3. This is for the flat plate. This is for the flat plate. If the flow is a turbulent flow over a flat plate, then you will use this equation. Now, we have given the 2 equations. One more thing is, or one more equation is also to calculate the local heat transfer coefficient. That is Reynolds-Colburn analogy. What Reynolds-Colburn has done? Reynolds-Colburn has just calculated the local heat transfer coefficient without giving the heat transfer. Means, from here they have just taken the local skin friction coefficient, that is local drag coefficient, and by using this local skin friction coefficient, they have shown the relation. What they have shown? From here, the local skin friction coefficient can be written like this. They know the formula for the Nusselt number is what? It is H into L by K. So, L is nothing, it is a characteristic length. On the plate, we have just put L is equal to X. So, from here, the formula is this 0.332 this. So, we have put it like this. Now, this value is replaced by Cfx by 2 and we have divided it by Reynolds and Prandtl number. When we have divided the Reynolds and Prandtl number, this Nusselt number upon RePr, this is known as Stanton number. Stanton number. And Stanton number is equal to, we have got Cfx by 2, Re to the power minus 1 by 2, Pr to the power minus 2 by 3. Now from here, you can easily calculate the local skin friction coefficient just by knowing the value of local skin friction coefficient. You can calculate the value of local heat transfer coefficient just by knowing the local skin friction coefficient. And if the local friction coefficient he has not given, then you can just take local skin friction coefficient. It is 0.003 to 0.004. It lies between 0.003 to 0.004. You can remember this. So just knowing the value of local skin friction coefficient, you can easily calculate the local heat transfer coefficient. Look, so Reynolds-Colburn analogy, in anywhere he is asking why we are using the Reynolds-Colburn analogy. We use the Reynolds-Colburn analogy to calculate the local heat transfer coefficient just by knowing the value of local skin friction coefficient without knowing the heat transfer given. Now, so it was the study of flow over a flat plate. We have discussed whether the flow over a flat plate is laminar or turbulent. In the turbulent, we don't have to study so much. We just have to study the laminar flow and in the deep. Now coming to the forced convection in pipes. We have taken the one case for the forced convection. Second case is forced convection in pipes. In the pipe, before studying the forced convection in pipe, means forced convection is what? The fluid is flowing and it is taking heat. The assumption should be the flow should be fully developed. Should be fully developed. This simply shows if you are going to study the forced convection in the pipes, but the condition is what? The flow should be fully developed. What is the fully developed flow? In case of the flow through pipes, you have studied if the fluid start flowing into the pipe and if the velocity profile in the direction of flow stop varying, then the flow is known as fully developed flow. Similarly, in this case we says if the temperature profile in the direction of flow stop varying, means initially let's suppose the fluid is entering like this, and after some time you will see, let's suppose it is heating. So you will see the temperature of this layer increases. Temperature of this layer increases and other layers temperature is lesser. Over here the temperature is also increasing like this. And when we reach at this condition, it is obvious now the profile will not change, since the temperature is continuously increasing and the lower layer temperature, middle layer temperature will be lesser. Now it is obvious that fluid start gaining heat continuously. It means the mean temperature of all the layers, it will continuously increases. And this mean temperature, the temperature which gives the rate of heat transfer at any section, is known as the bulk mean temperature. Bulk mean temperature is nothing, it is the average of all layers temperature which gives the rate of heat transported at any given section. So this mean temperature will continuously increase if there is a case of heating. Now coming to the next point, the case of heating will be of two types. One is known as constant heat flux condition, another is known as constant wall temperature condition. Constant heat flux condition can be maintained by binding a coil around the pipe and with the coil continuously supplying the same heat flux. And constant wall temperature condition, it can be only obtained by the condensing steam putting over here. Since if the steam condenses, it will start changing its phase, and during the phase change temperature remains constant. Now the question he will simply ask you whether these two conditions can be maintained together. No, these two conditions cannot be maintained together. Let us give you a small introduction about this. We can say, let's suppose we are taking first condition, that is constant heat flux condition. In case of the constant heat flux condition, you can say Q is equal to H. Q is equal to H into A into TW minus TB. If flux is same, it means this Q is constant, since area is fixed, no doubt. So if flux is same, Q is constant, and H we are saying, let's suppose we are taking in this, like this, in this fashion. So Hx into TW minus T infinity. Now what I want to say, this Hx is a function of L, V, rho, mu, Cp and K, and these all properties almost remains constant, and L is equal to what? Dia. And what I want to say, if dia remains same, then the velocity throughout the pipe remains same, and if the velocity in the pipe remains same, it means Hx will almost be remains same. If Hx is same, Q is constant, but TB, that is mean temperature, it has a tendency to increase. Since the fluid is continuously gaining heat, if TB increases, so what I want to say, this TW must also have to increase. In this case, when you continuously start heating, this wall temperature will continuously increases. That's why we always say, in this case, if we take Q as constant, then the wall temperature definitely increases. We cannot take constant as wall temperature. Now in the second case, if wall temperature we will remain fixed, it means what? If Q, H is constant already, wall temperature we have taken constant, but it has to increase, and if it has to increase, it means Q will decrease. So simply we can say constant wall temperature condition and constant heat flux condition will not be maintained together. These are two separate conditions. If you either you can maintain constant wall temperature condition or you can maintain constant heat flux condition. So it is just simply bulk mean temperature we have discussed. This is nothing, it is the average temperature at any given section which gives the total heat transported at that given section. Now it is obvious if Hx remains same, we are aware with the Nusselt number formula. Nusselt number formula is equal to what? Hx into L by K. If Hx is constant, L is nothing, it is the characteristic length, that means dia of the pipe, and K is the conductivity, it remains constant. It means it is obvious in case of flow through pipes, Nusselt number remains constant. And we got two values, laminar flow through the pipes. He will simply give you the problem, and he will not give you, he will just give you, also give you the Nusselt number and also give you the equation for the turbulent flow. It is your duty to first check whether the flow is laminar or turbulent. And if the flow is laminar, if the flow is laminar, then you will see whether it is a constant heat flux condition or it is a constant wall temperature condition. If it is a constant heat flux condition, you will just put this value, and constant wall temperature condition you will put this value. And you can easily calculate the Nusselt number from here. After calculating the Nusselt number, this is the fixed value of Nusselt number, and after putting the value of the Nusselt number, you can easily calculate the local heat transfer coefficient. Now if he has given the flow is turbulent, it means the Nusselt number will be given by this. So you will calculate again the Nusselt number. M is equal to nothing, it is 0.3, 0.4. Nusselt number is equal to what? 0.023 Re to the power 0.8 and PR to the power M. PR, he will give you the PR. You will just calculate Nusselt number, and by calculating the Nusselt number, you can easily calculate the local heat transfer coefficient, that is Hx into X by L. Hx into X by K, like this. So from here again you will calculate the local heat transfer coefficient. Now the next is what? expression for bulk modulus. Bulk mean temperature. Expression for bulk mean temperature. What do you want to say in case of the bulk mean temperature? Bulk mean temperature is the average temperature at any given section. So what we can do? First we will take the heat transported at any given strip, and we have just integrated this heat transported, and also we can calculate, if I just integrate, we will get the total heat transported through this section. And if I just take the heat transported by direct formula, it will be equal to what? Mass into C into T, that is equal to this. If we equate this, it will be this. So just you have to remember, in case of the bulk mean temperature, let's suppose we have a pipe like this. And if he is just saying what is the total heat transported between this section, you will simply say, sir, TB at 1 is TB1 and this section TB is equal to TB2. Let the mass flow rate is M. So we will say the total heat transported, Q total is equal to nothing. It is the mass flow rate into C into TB exit minus TB inlet. This will be the total heat transported through the pipe. If he is just saying total heat transport through a section, any section, it will be what? M into C into TB at this section. So this is the bulk mean temperature, and it is important for you. Just try some problems on this. We are just taking some not very deep. We are just taking a small description about the topics. Just we are memorizing all the things. I'm assuming all the things you have studied and just memorizing the things. Okay, now coming to the next topic. Now let us come to the free convection. And in free convection, we simply says, in case of the free convection, motion to the fluid is provided by the buoyancy forces which arises due to density difference. So in case of the forced convection, we generally takes the flow of the fluid by some external agent, but in case of the free convection, motion to the fluid is provided by the buoyancy forces which arises due to density changes. And in case of the free convection, we have discussed already that H is a function of G beta delta T, LV rho mu Cp and K. Now when you will again solve by using the Pi-Buckingham method, in case of the free convection, you will get this Nusselt number is a function of GR and PR, where GR is nothing, it is known as the Grashof number. It is known as the Grashof number, and simply he may ask you the question, in case of the free convection, Reynolds number is replaced by, in the forced convection, we have just seen Nu is equal to what? It is Re and PR. So this Re replaced by GR, that is Grashof number. So whenever he is asking in case of the free convection, Reynolds number is replaced by, it is replaced by the Grashof number. Where Grashof number is what? Grashof number is given by G beta delta T L cube upon mu by rho whole square. So mu by rho is nu, and we write G beta delta T L cube by nu square. So from here we calculate the Grashof number, and again we write like this, Nu is equal to C GR PR raised to the power N, where if he has given N is equal to if 1 by 4 you will use for laminar flow, and N is equal to 1 by 3 it will use for turbulent flow. So from here you can just put the value of N. C, here he will give you in the question the value of C, that is constant. So from here when you will put the value, you will just get the Nusselt number. And what I want to say? For laminar and turbulent flow, how you will calculate laminar and turbulent flow? So we calculate laminar and turbulent flow by, if GR into PR, that is Grashof number into Prandtl number multiplication is less than 10 to the power 9, then you will simply say the flow is laminar. And if GR into PR is greater than 10 to the power 9, then you will say the flow is turbulent. And this GR into PR multiplication is known as the Rayleigh number. Known as the Rayleigh number. Now sometimes in the PSUs they may ask you a problem on the characteristic length. This is the characteristic length L. So in case of if the flow is taking place through the pipe like this, let's suppose free convection is taking place. Free convection is taking place either like this or like this. It means it is just moving like this. So this dia will be the characteristic length. Similarly, if the flow is taking place like this and like this, then the characteristic length will be this length of the cylinder. And if the flow is taking place through this plate, then definitely this will be the characteristic length, that is A plus B by 2. So it is a description. We have discussed in case of the convection. In case of the convection, first we have discussed that what is the mechanism of convection, and in the mechanism of convection first we were discussing the forced convection through the pipe and also forced convection through the over a flat plate. Then we have discussed the free convection. So these some formulas you just have to remember. In the convection, most of the question asked on the base of formula. So you just have to remember. Generally in the convection there are so many formulas. You just remember 2-3 formulas and you will get the question from here. Now let us come to the next topic. So now let us start from the next chapter. Next chapter is radiation, and we are aware with this radiation is what? Radiation is the mode of heat transfer which do not require any material medium. Radiation is the mode of heat transfer which do not require any material medium, and hence radiation heat transfer takes place with the help of electromagnetic wave propagation which travels with the speed of light. So we have studied, and we also have studied, that all the bodies at all temperatures emit thermal radiation except the body is at 0 Kelvin. So let us start from the radiation, and we are just showing a spectrum of thermal radiation. Initially, let's suppose we are just showing, we are seeing a sun. We are seeing sun, and let's suppose some radiation is coming from sun to earth. So we are just seeing some spectrum on the thermal radiation. On this we have just taken the wavelength range. This is the wavelength range. We are starting from 0. And we are measuring the wavelength in micrometer. From here we are going 10 to the power 1, 10 to the power 2, 10 to the power 3 and so on. And this side we are just going 10 to the power minus 1, 10 to the power minus 2 and so on. So from 10 to the power minus 1 to 10 to the power 2, whatever the wavelength we are getting, this wavelength is known as thermal radiation. These wavelength radiation are known as thermal radiation. Simply he will ask you, what is the wavelength range for thermal radiation? The wavelength range for thermal radiation lies from 10 to the power minus 1, that is 0.1 to 100. 10 to the power minus 1 to 100. So wavelength range of the thermal radiation is 0.1 to 100. And what is the wavelength range for visible thermal radiation? This is the visible thermal radiation which lies between 0.4 to 0.7. So 0.4 micrometer to 0.7 micrometer is the wavelength range for visible thermal radiation. What is visible thermal radiation? For example, you can say filament of the bulb, which we can see, which is visible to us. That is known as visible thermal radiation. So visible thermal radiation wavelength lies from 0.4 to 0.7. And the thermal radiation range lies from 0.1 to 100. Now after 100, whatever the waves we are getting, these waves are known as microwaves, and before 10 to the power minus 1, whatever the rays we are getting, these rays are known as X-rays and Y-rays. Means in the X-rays and Y-rays, when you go to the doctor for the X-ray, definitely these are not visible to you. X-rays are not visible, or Y-rays, whatever. So these are known as microwaves, these are known as X-rays and Y-rays. So it is the spectrum of the thermal radiation. They simply in the PSUs, like Coal India is coming, it may be you will get the question from here. Just nothing, you have to remember the thermal radiation wavelength, visible thermal radiation wavelength, and after 100, what are the waves? The waves name is, it is microwaves, and the waves name is X-rays and Y-rays. So you have to remember like this. Now when you study the radiation, again and again you will get two names. One is known as diffuse, another is known as gray. So diffuse means independent of the direction. Means when you will say the body is diffuse, diffuse means it is emitting the radiation equal in all the direction. It is independent of direction. So whenever the body is diffuse, it means it is emitting the equal radiation in each and every direction. That's why we take diffuse. And gray means independent of the wavelength, means at each and every wavelength it is emitting same thermal radiation. That's why you always take like this. Let's suppose it is a surface, and this surface emitting like this. This surface is emitting like this. This is the case of diffuse and gray, like this. In each and every direction you are just getting the spherical shape, hemispherical. Now coming to the next point, we have some definitions which also we have to remember for radiation. Number one is total hemispherical emissive power. Total hemispherical emissive power is denoted by E, and it is what we says total hemispherical emissive power is the total radiation energy emitted from a surface per unit time per unit area. Total hemispherical emissive power is nothing. We can say it is the total hemispherical total radiation energy emitted from a surface per unit time per unit area is known as total hemispherical emissive power. Or we can say radiation flux emitted from a surface is known as, or total radiation flux emitted from a surface is known as total hemispherical emissive power. Now coming to the next point is monochromatic hemispherical emissive power. Whenever he is saying monochromatic, he can also say one another name is spectral. Spectral means at a particular wavelength. So he can also say like this. If he is just saying, you will say total radiation energy emitted from a surface per unit time per unit area at a particular wavelength. At a particular wavelength is known as the monochromatic or spectral hemispherical emissive power. Just try to understand. Total hemispherical emissive power is what? Total radiation energy emitted from a surface. And monochromatic is what? The radiation energy emitted from a surface on a particular wavelength. On a particular wavelength means it is like this. It is like this. Means we can easily say monochromatic emissive power is given by per unit wavelength we are calculating dE by d lambda. And if I just take the dE is equal to E lambda into d lambda and integrate, then we will get E is equal to 0 to whatever the limit E lambda d lambda. And by using this, we can also say like this, that the monochromatic emissive power is a quantity which when integrated over a wavelength range of lambda to lambda plus d lambda, it gives the total hemispherical emissive power. You can also define like this: monochromatic emissive power is a quantity which when integrated over a wavelength range give the total hemispherical emissive power. Or one more way you can define, that the area projected on the lambda axis, wavelength axis, area projected on the wavelength axis on a E lambda lambda diagram gives total hemispherical emissive power for this. So whenever you take the area, you will get the total hemispherical emissive power. Or you can also define like this, it is a quantity which when integrated over a wavelength range, it gives the total hemispherical emissive power in that particular wavelength range. Now coming to the next is what? Total emissivity. And total emissivity is nothing, it is a ratio of total hemispherical emissive power of a non-black surface to the total hemispherical emissive power of a black surface. And one more is monochromatic emissivity. Monochromatic emissivity is what? It is a monochromatic emissive power of a ratio of monochromatic emissive power of a non-black surface to the monochromatic emissive power of a black surface. So when you take like this, what you can write? Total emissivity is equal to E by EB. When you put the value of E is equal to 0 to lambda E lambda d lambda, 0 to infinity E lambda d lambda. So you will put, for black body you can write 0 to infinity EB lambda d lambda. Now if we just put the value, and if I just assume this epsilon lambda is independent of this lambda, it means we can take outside and we will get, these will be cutted and we will get epsilon is equal to epsilon lambda. What we are getting from here? From here we can say the body whose monochromatic emissivity means the emissivity at a particular wavelength. So he is just saying the body whose monochromatic emissivity is independent of the wavelength, the type of the body is known as gray body. Means the gray body is a type of body whose monochromatic emissivity is independent of the wavelength. Means at each and every wavelength you will get the same emissivity. Now, so from here, if we just want to represent graphically, we can draw the graph. This is epsilon lambda, this is lambda. So for a black body, no doubt emissivity at each and every point will be same. So we have shown like this. For general bodies, it will be like this. It will be either increases, decreases, whatever. It will fluctuate. But for gray body, it will again not fluctuate. And its emissivity at each and every wavelength will be same. Its monochromatic emissivity is not the function of this lambda. So the body whose monochromatic emissivity is independent of the wavelength is known as gray body. Also, he may ask the problem like this. Let it is E lambda, let it is lambda. So he will show you the three bodies. You all are aware with this. Total emissive power will be for black body, and gray body may have the lesser emissive power, may have the greater emissive power, but it is obvious that epsilon lambda of the gray body will be same. So from here we can just write, if he just ask, if anywhere if he is asking which graph represent for which body, you can simply say it is a black body, it is a gray body, and it is a general body like this. Now for gray body you can write epsilon lambda 1 is equal to epsilon lambda 2 is equal to epsilon lambda 3, and we all are aware with this. Epsilon lambda is what? E lambda by EB lambda. So we put E lambda by EB lambda 1, E lambda 2 by EB lambda 2, E lambda 3 by EB lambda 3. Means in the gray and black body, if you take the ratio at each and every point, the ratio will always remain same. Means the gray body is behaving, giving the same behavior as the behavior of black body, but the emissivity of the gray body will be always less than the black body. It will behave like a black body. That's why we always say the body is, all the bodies cannot be perfectly black, but we can assume all the bodies are diffuse and gray, independent of the wavelength. Now from here, so we have studied what is gray body. Next point is absorptivity. Absorptivity is nothing, let's suppose we have a surface and on the surface we are just incidenting some of the radiation energy. And on the surface if some radiation energy is incident and let the surface absorb some part of that radiation energy. So absorptivity is what? It is the fraction of radiation energy which is absorbed by the surface that incident on it. That is known as absorptivity. Absorptivity is what? Fraction of radiation energy which is incident on the, which is absorbed by this surface which is incidenting on it. Let's suppose 100 units are coming and it is absorbed 20. It means absorptivity was 20 by 100 like this. And similarly we have monochromatic absorptivity. It is what? It is the fraction of radiation energy which is absorbed by the surface which is incidenting on it at a particular wavelength. So you can write like this. Similar another definition, that is reflectivity. Fraction of radiation energy which is reflected by the surface that is incidenting on it, and monochromatic at a particular wavelength. Transmissivity is what? Fraction of radiation energy which is transmitted by this, that is absorbing, incident on it and at a particular wavelength. Now it is obvious whatever the total radiation energy coming, there are three parts of that radiation energy. One is absorption, another is reflection, and third one is transmission. So it means if we just make the sum of absorptivity, reflectivity and transmissivity, it will be equal to 1. And by chance if we just say what will be that particular wavelength, you will also get at particular wavelength that is equal to 1. And if the body is black, so in case of the black body, you will just say reflectivity will be 0. In case you will say transmissivity will be 0, since a body which absorb all the thermal radiation. So if it is absorb all the thermal radiation, it means absorptivity will be what? 1. So we are saying in case of the black body, absorptivity will be 1. And at particular wavelength, it will also become 1. Similarly, if the surface is a opaque surface, opaque matlab means there is no transmission. If there is no transmission, so transmissivity 0. So from here we says that the surface is opaque. Opaque, it means there is no transmissivity. Means from here we will write tau is equal to 0, means alpha plus rho is equal to what? 1. Alpha plus rho is equal to 1. You can write like this. Or you can write alpha lambda plus rho lambda is equal to 1 like this for a opaque surface. Now let us discuss some laws of thermal radiation. Some laws of thermal radiation. Laws of thermal radiation means the first law was Stefan Boltzmann law of thermal radiation. Stefan Boltzmann law always says the total radiation energy emitted from a surface per unit time per unit area will be directly proportional to the fourth power of the absolute temperature of the body if the body is a perfectly black body. So it means from here we can write like this. We have already studied this. Next is Planck's law. Planck's is just given the experimental data. It just says the total monochromatic hemispherical emissive power of a black surface is given by. So monochromatic emissive power of a black surface is given by 2 pi C1 upon lambda to the power 5 e raised to the power C2 by lambda t minus 1. You just have to remember this. They will ask so many times this equation, where C1 is equal to 0.596 10 to the power minus 16 and C2 is equal to 0.01437 like this. Now one more law is the Planck's law was the basic experimental law, and again there were so many experiments done on the Planck's law, and Wien has done again an experiment on this formula. What Wien has done, he was just thinking this EB lambda can be maximum or can be minimum. So for maxima and minima, he has just differentiate this EB lambda. And after differentiating, what he have got? He got lambda into t is equal to constant. And when he draws the graph between them, he got the graph like this. This is what? This is lambda m1 is the wavelength at which EB lambda is maximum. Lambda m means wavelength is not maximum. Wavelength is continuously changing like this. Lambda m1 means the first wavelength at which EB lambda is maximum. And second one, lambda m2 is what? The wavelength at which this EB lambda is maximum. And again third one is like this. Now what he has draws, Planck's Wiens, what draws by, what graph has been drawn by the Wiens. He has drawn the graph and he simply says, let's suppose it is at temperature T1, it is at temperature T2, it is at temperature T3. It is just drawn at constant temperatures. So he says, at a particular temperature, as lambda increases, at a particular temperature as lambda increases, EB lambda also increases, reaches maximum, then start decreasing and reaches to 0. Just try to understand. It says when he differentiate this and when he made some experiment on this, he just got the results. First result was at a particular temperature, as lambda increases, EB lambda also increases, reaches maximum, then reaches to 0. Again, he says for this also, at a particular temperature, EB lambda increases, reaches maximum, then reaches to 0. EB lambda increases, reaches maximum, then reaches to 0. Now, one more thing he has just solved. He solved at a particular wavelength, as temperature increases. At a particular wavelength, as temperature increases, most of the thermal radiation shifted to shorter wavelength side. At a particular wavelength, as temperature increases, most of the thermal radiation shifted to shorter wavelength side. What do you want to say? Let's suppose you can feel in the winter season or in the summer season. Winter season and summer season, you feel that the rays of the sun penetrate very, very closely in case of the summer season. But in case of the winter season, you feel the rays of the sun do not penetrate very, very closely. That's why you feel it is too hot in case of the summer season. It behave like point to point action will be there. That's why when temperature increases, most of the thermal radiation shifted to shorter wavelength side. The radiation coming out from the sun is same, but in winter season it will behave different and in summer season it will behave different. That's why he just got two results. One results at a particular temperature, as lambda increases, EB lambda increases and reaches maximum, then decreases, or at a particular wavelength as temperature increases, most of the thermal radiation shifted to shorter wavelength side. So whenever he is asking to draw the graph, you just have to remember, you will not draw graph like this. You will not draw graph like this. If you increase the temperature, then definitely the graph will shift like this. Definitely the graph will shift like this. So you have to remember over here. Now from here, he just says it means, if I just differentiate and we are getting lambda into t is equal to constant, what it means? It means that the wavelengths are inversely proportional to the temperature. As temperature increases, wavelength decreases. As temperature decreases, wavelength increases. So from here he just got the result, the lambda into t will be constant, and please remember the value of this C. This C is equal to 0.0029 meter Kelvin or 2900 micrometer Kelvin. So this will be the result which you have to remember. This is the Wien's displacement law. Now from here, if I just take the area below this, we can easily calculate EB by taking the area. So EB is equal to like this. So from here, when we are calculating, we have to integrate this EB lambda, and EB lambda is this. So when we integrate, what we are getting the simple 2 pi C1 60 to the power 4 C2 to the power 4. This is the result. Now from here, what we are getting this is at 5.67 into 10 to the power minus 8, which is known as sigma. That's why we have studied that EB is equal to sigma into T to the power 4. Means what we are getting, we can simply say that the integration of Planck's law, gives this Wien's displacement law. Integration of the Planck's law gives Stefan-Boltzmann law, and differentiation of the Planck's law gives Wien's displacement law. When you differentiate the Planck's formula, you will get the Wien's displacement law. When you integrate the Wien's displacement Planck's formula, you will get the Stefan-Boltzmann law. So whenever he is asking integration of the Planck's law, differentiation of the Planck's law, integration of the Planck's law gives the Stefan-Boltzmann law, and differentiation of the Planck's law gives Wien's displacement law. So you have to remember like this. Now the next law is Kirchhoff law. Kirchhoff law simply says, if a body is in thermal equilibrium with the surrounding, then the total absorptivity of the body will be equal to total emissivity of the body. Just try to remember. Means what you want to say, if the body is in thermal equilibrium, then the energy absorbed by the body will be equal to energy emit from the body. It is obvious, if it is in thermal equilibrium, the absorptivity will become 0. Whatever it will absorb, it will definitely reflect from here. Emit from here. So that's why it says, if a body is in thermal equilibrium, means total absorptivity is equal to total emissivity. So from here, we have just taken the 4 laws. One is Stefan-Boltzmann law, the second one is Planck's law, third one Wien's displacement law, fourth one Kirchhoff law. You just have to remember the Stefan, Planck's and Wien's, these are same. If you just differentiate Stefan-Boltzmann Planck's law, you will get Wien's. Planck's law, if you differentiate, you will get Wien's. If you integrate, you will get Stefan. So these are the experiment done. Now from here, we are also taking some properties. One is known as irradiation. Irradiation is nothing. It is the total radiation energy which is joining the surface, which is incidenting on the surface. Total radiation energy incident on the surface is known as irradiation, and total radiation energy which is leaving the surface is known as radiosity. So from here we are just saying, let's suppose G is irradiation which is incidenting on it, and let's suppose alpha times of G is absorbed by this surface and rho G is reflected. So this is the energy which is leaving the surface, and also it will emit some part of the energy from here. So the total radiation energy which is leaving the surface will be what? E plus rho G. That's why we write J is equal to E plus rho G, and we have studied E is equal to epsilon is equal to E by EB. So we have written in the form of black body epsilon times of EB, plus rho can be written as 1 minus alpha, since we have studied alpha plus rho is equal to 1 for an opaque surface if transmissibility is 0. So we will write like this. Now if we calculate this J is equal to this. So he may ask you what is the net radiation heat exchange. We all are aware with this. We have a surface. This is G which is coming, this is J which is going. It means the net radiation heat exchange will be what? Difference of these two. So we have calculated it is the difference between these two, and it was per unit area, so we have multiplied by the area. When we solve, we are getting Q net is equal to EB minus J upon 1 minus epsilon into A. What it means? It means, let's suppose we have a surface. Let's suppose we have a surface, and if the surface was black or maybe black, then definitely it will emit what? EB. But if it is not black, then it means there will be some resistance over here. And if it is not black, what emitting? It is J. It means there will be some resistance which is just broken up, or which is just reducing the amount of EB. So this resistance is known as surface resistance. The resistance which appears on the surface is known as surface resistance. So it is what we have taken a chain over here, EB minus J, and there is a surface resistance over here, that is 1 minus epsilon. Now whenever you are studying the radiation, so in case of the radiation, first you have to take the spectral of thermal radiation. You just have to remember this, and after remembering this, you just have to remember some of the definition. First is total hemispherical emissive power, which was the total radiation energy emitted from a surface. Second was monochromatic hemispherical emissive power, the radiation energy emitted at a particular wavelength. And third one was total emissivity, that is the ratio of the total hemispherical emissive power of a non-black surface to the black surface. Similarly, monochromatic emissivity. And irradiation is the total radiation energy incident on the surface, radiosity which is leaving the surface. So we have given the 6 definitions, and after that you can also remember that what is gray body. Gray body is what? The body which has epsilon lambda is independent of the lambda. That means it behave like a black body. So you can just remember these, and these are the results which we have calculated. Absorptivity, reflectivity, transmissivity, these 3 values also you have to just remember. Now coming to the next point you also have to remember these laws. So if you just remember these laws, then you will be able to hold the further things which I am going to discuss. So let us come to the next topic. So the next topic is shape factor. Let's suppose we have 2 surfaces. We are discussing shape factor. We have 2 surfaces. One is surface 1, another is surface 2. And let the heat, whatever the radiation energy which is leaving the surface is Q1, and absorbed by the part of Q1 is absorbed by the surface is Q12. Q12 which is absorbed by the surface 2. What I want to say, Q1 is the total energy which is leaving surface 1, and Q12 is the amount of radiation energy, fractional part, which is absorbed by the surface 2. So this ratio is known as shape factor of surface 1 with respect to surface 2. How we define? It is the fraction of radiation energy which is absorbed by surface 2 coming from surface 1. It is the fraction of radiation energy which is absorbed by surface 2 coming from surface 1 is known as shape factor of surface 1 with respect to surface 2. We just have to take the prefix as what? From where the heat is coming. Fraction of radiation energy which is absorbed by surface 2, that is coming from surface 1, is known as shape factor of surface 1, that with respect to surface 2. Similarly, we can also write like this: fraction of radiation energy which is coming from surface 2 absorbed by surface 2 is known as shape factor of surface 2 with respect to surface 1. Like this. fraction of radiation energy which is absorbed by surface 1, that is coming from surface 2, is known as shape factor of surface 2 with respect to surface 1. So you can simply, shape factor is nothing, whatever the radiation energy emitting from this surface and the fraction of radiation energy emitted is just absorbed by this surface is known as shape factor of this surface with respect to this. Now let us discuss. We can also define like this. Let's suppose we have a surface like this and on this side it is opaque, and here we are just saying, let's suppose it is only radiating, it is not absorbing. So we will definitely say shape factor of surface 1 with respect to this surface 1, it will be 0. Now we can also say like this, over here it will just emit like this, it will emit like this. It means it can absorb some of the energy which is just reflecting from here or emitting from here. So over here we will definitely say the F11 will not be 0, F11 will be, some of the part will be reflected, some of the part will be absorbed. So from here we will say it will less than 1 and greater than 0. Over here the F11 will be definitely 0. In that case we are taking two surfaces. Let it is surface 1, it is surface 2. So over here we will say thus whatever the fraction energy coming from surface 2, it will go like this. It will go like this. Means F12 is obviously 1, since whatever just emit from here it will be absorbed by the surface if these are the perfectly black surfaces. Now F12 is 1, but F21 is what? Less than 1, and F22 also less than 1. What I want to say, if we just can calculate, let's suppose we have n number of surfaces. We have two surfaces. If we are two surfaces, it means total number of shape factor will be what? F12 plus F21 plus F11 plus F22 like this. So if there are two surfaces, then the shape factor will be 4. Means if there are n surfaces, shape factor will be n square. Now what I want to say, if I just add up, that is F11 plus F12 plus F13 and so on, then the sum of shape factors will be 1, since it was a fraction. We can write like this. Let's suppose we have a surface 1 and it is attached with 4 surfaces. So we can say we have total number of surfaces what? How many? 5. So we will write 5 and 5 like this. We will get F11, F12, F13, F14, F15, F21, F22, F23, F24, F25 and so on. So you can easily calculate the number of shape factors by using this table. Total number of shape factor will be definitely n square and the sum of these will be definitely equal to 1 like this. Now we also have to use, let's suppose there are two surfaces like this. There are two surfaces like this. It is obvious the shape factor of this surface is what? 1 with respect to this. But this for this surface shape factor will not be 1. It will be less than 1. So from here we can easily write F12 is equal to 1. Now from here, sometime they may ask about the shape factor. It is an important topic. You just need to solve 4, 5, 6 problems on this topic. There is a relation, which relation is known as reciprocity relation. And reciprocity relation is nothing. It says area of surface 1 into shape factor of surface 1 is equal to area of surface 2 into shape factor of surface 2. This is also known as configuration factor. This is also known as view factor. So you can use the reciprocity relation. You will just put the value of F12 as 1 and you can easily calculate F21 is equal to what? A1 by A2 like this. So it is just easy past. You just calculate the shape factor by using the reciprocity relation. And all the shape factor, if you want to calculate, you can make table like this and you will calculate. Now if we are ready that the shape factors are like this, reciprocity relation does not mean you will apply between two surfaces. Any of the two surfaces can be there. For example, if we will apply about third surface, so we will write like this. Fourth surface we will write again. Now, when we, let's suppose we have two surfaces, one surface is this, another surface is this. Now what I am doing, I am just doing, let's suppose the area of this surface is A1, area of this surface is A2, and shape factor of this surface is F12, shape factor of this surface is F21. Now it is obvious the radiation energy leaving from this surface will be what? It is obvious it will be leave by EV1 into A1, but it is not a black surface. So due to resistance offered at the surface, the radiation energy leaved will be J1 into A1. Similarly, from the surface 2, the radiation energy leaving will be J2 into A2. And whatever the energy leaving from the surface will not be totally absorbed. So let's suppose the total radiation energy which is absorbed by this surface is equal to J1 A1 into F12, and absorbed by this surface is equal to J2 A2 into F21. So what I want to say, let's suppose it is just sending 100 rupees and absorbed number of rupees are 50, and it is sending 50 rupees and it has absorbed 25. So the net exchange will be what? 50 minus 25. That's why from here what we can see, the net radiation heat exchange will be, it is given by, simply we can say it is equal to J1 A1 F12 minus J2 A2 F21. And from here it is obvious by the reciprocity relation, A1 F12 is equal to A2 F21. So we can write like this, J1 minus J2 upon 1 by A1 F12. And this is just acting in this space, that's why it is known as space resistance. So from here, when we have two surfaces, this surface wants to emit EB1, but it is emitting J1, and again this surface wants to emit EB2, but again emitting J2. So from here we will get first surface resistance 1 minus epsilon 1 by epsilon 1 A1. Over here there will be one space resistance and one surface resistance. So when the radiation heat exchange takes place between two surfaces, there will be two surface resistances and one space resistance. So we have just calculated the surface and space resistance. Now we can easily calculate the net radiation heat exchange between two surfaces. These are two junctions. If I just take these two junctions, means we have to take the total resistance like this. And when we put the value of the total resistance, you will get a generalized formula for the net radiation heat exchange, that is given by sigma into T1 to the power 4 minus T2 to the power 4 upon 1 minus epsilon 1 into epsilon 1 A1 and plus 1 by A1 F12 plus 1 minus epsilon 2 upon epsilon 2 A2. So it is like this. Now if we just apply some cases, if he says that one body is larger, another body is smaller, it means one shape factor is equal to 1 and another shape factor is less than 1. Then when you apply, then you will get the condition like this. This formula is valid in all the cases where one shape factor is less than 1, one is equal to 1. You will simply just write this formula, and by chance if we just saying the area of a smaller body is very, very small, for example a bulb in a room, a filament in the bulb. So if we just saying like this, then definitely this term becomes 0 and you will get Q net is equal to sigma into epsilon 1 A1 into T1 to the power 4 minus T2 to the power 4. So you will simply get the formulas like this. Now coming to the next point, by chance if we just saying the all areas and all shape factor are same, all the bodies are making perfect enclosures. So from here you will just put epsilon 1 is equal to epsilon 2, this will be 1. So you will get like this, sigma into A1 into T to the A, it will become A, into T1 to the power 4 minus T2 to the power 4 upon 1 by epsilon 1 plus 1 by epsilon 2 plus minus 1. And again, if we just saying all the emissivities are same, it means it will become 2 by epsilon minus 1, and you will get the formula like this. So these are some cases, you just remember this formula only. If we just saying F12 is equal to 1, 1 is less than 1, you will get this. If we just saying it is very, very less, you will get this. If we just saying all the areas are same, you will get this. If we just saying all the emissivities are also same, you will get this. Now coming to the next point, next topic is radiation shield. Radiation shields are what? These are the parallel plates which are used to reduce the radiation heat exchange between two surfaces. Radiation shields are nothing. These are the thin parallel plates which are used to reduce the radiation heat exchange between two surfaces. We have the shields like this. What I want to say, we just want to reduce the radiation heat exchange between two surfaces. And if we want to reduce, it means this radiation shield should have very, very low absorptivity. The first condition is radiation shield should have very, very low absorptivity, and it should have very, very high reflectivity. So the material of the radiation shield should have high reflectivity and low absorptivity. That's why in case of the radiation shields, we always used polished aluminum sheets. In general, we used polished aluminum sheets. So this is a simple concept of the radiation shield. It is a simple, it is a plate which just comes parallel to the surfaces, and due to this plate, the radiation heat exchange will reduce. Now the question they will ask you, when I just put one radiation shield, how many the surface resistance will increase and how many space resistances will increase? Look, when there was no radiation shield, there were only 3 resistances, 2 surface resistances, 1 space resistances. Now when we have put it one radiation shield, there is 1 surface, 1 space, surface, surface, space, surface. So we are getting what? 3 number of resistances, say 6 number of resistances. Means by putting one radiation shield, the total number of resistances increases by 3. It means there will be 2 surface resistances increases and 1 space resistances increases. So he may ask you the simple problem. These are the resistances which now will behave over here, and we are just simplifying the problem. Now what? If we just put 0 number of radiation shield, number of surface resistances increases by 0, number of space resistances increases by 0, total surface resistances will be 2 and total space resistances was 1. That case. This was the case when there was no radiation shield. Now if I just put one radiation shield, so by putting the surface resistances increases by 2, space resistances increases by 1, total surface resistances become what? 2 initially and 2 increases, it means 4, and total space will be 2. It means it can be written like this: 3 is equal to 3 into 0 plus 3 and 6 is equal to 3 into 1 plus 3. It means by putting one radiation shield, the total number of resistances increases are 3. 2 surface, 1 space. If I just put, we are getting like this. It means if I just put n number of radiation shield, the total number of surface and space resistances increases by 3n. Just try to understand. So he will simply ask you the problem, total number of resistances increases by either total number of surface or total number of space. You have to remember. Now also he may ask you, if you are just putting a radiation shield, by what amount the heat reduction, radiation heat reduction takes place. So from here, the initial formula was this: if they have the same area and same emissivity, that is Q with radiation, without radiation shield, sigma A T1 to the power 4 minus T2 to the power 4 upon 2 by epsilon minus 1. And when we have put the same radiation shield of same material and same area, so there will be two surface resistance increases and one space, and we will getting the formula S2. This sigma A T1 to the power 4 minus T2 to the power 4 upon 4y epsilon minus 2. So from here, if I just take that with radiation shield, by putting one radiation shield it will become half. If I just take two common, it will become same. So from here it means Q with radiation shield is equal to half of without radiation shield, and it can be written as Q with is equal to 1 plus 1 of Q without. Means if we put n number of radiation shield, so the remaining radiation heat exchange will be Q with by n plus 1. Means at what amount the radiation heat exchange reduced? It will be what? 1 minus 1 plus n plus 1. So from here we can write, if we have put it 0 radiation shield, the reduction will be 0. If we have put it 1, reduction will be 50%. If we have put it 2 radiation shields, reduction will be 66%. And if we have put it n, it is will be 1 minus n plus 1 into 100. So it was the concept of the radiation shield. I think you are aware with this. We are just revising. Now one more concept is what? Error in the temperature measurement. Whenever you are measuring the temperature, what will be the error in temperature measurement? What error? We have two shields. Let's suppose two plates are there, and let's suppose a canal is there or whatever. So from here we are just measuring the temperature of a gas stream whose temperature, actual temperature is T infinity, and let we are using a thermocouple which is measuring the temperature as Tc. So the temperature measured by this is Tc. Means we can say it is a fluid, it is a solid. So rate of heat transfer by the convection can be given as Q convection is equal to H into A into T infinity minus Tc. Now if I just calculate this, whatever the rate of heat exchange takes place between this and this will be transferred over here. Whatever the radiation convection heat transfer, it will be transferred over here. So from here we can say Q radiation is equal to, that is Tc minus Tw. So we are writing sigma A Tc to the power 4 minus Tw to the power 4 upon 1 by epsilon C, that is emissivity of this. We are using thermocouple, and this is what area of the thermocouple upon area of the wall, 1 by epsilon W minus 1. You can also take this area of the wall is very high, as very large as compared to this. So you can take as 0. If you just compare, this will be equal to this. You will get a difference T infinity minus Tc. So this T infinity minus Tc will be equal to what? This epsilon C will go up. Epsilon C into sigma into Tc to the power 4 minus T2 to Tw to the power 4 into H. And this is known as the error. This is known as the error, which is approx error. If you just want to calculate actual error, so actual error you will calculate with this formula only. So it is, sometimes they may ask the problem, find the error. Error is nothing. Whatever the error which comes into the temperature measuring. Let's suppose gas stream temperature is 50 degrees Celsius and thermocouple is measuring 40 degree. So the error will be what? 50 minus 40, that is 10. So this is the error. So this error we have calculated like this. So it may be, they may ask the question this side, this year from here. So simple, it's a simple concept. You are just measuring the temperature from here. So it was the radiation. Now coming to the next topic. Now let us discuss the next chapter, that is heat exchanger. So we have revised already conduction, convection and radiation. Now coming to the heat exchanger. So we simply says heat exchanger is what? Heat exchanger is an open system steady flow adiabatic device in which two flowing fluid exchanges their heat between them. We simply says heat exchanger is an open system steady flow
adiabatic device in which two flowing fluid exchanges their heat without losing any amount of heat to the surroundings. So we simply says, let's suppose we have a system like this, and in this system we are saying two flowing fluid are like this and they are exchanging their heat. This is hot fluid, this is colder fluid, so they are exchanging their heat, means the heat transfer to the surrounding we have taken as 0. So for example, we can simply say, for example, economizer. Economizer, in case of the economizer, the heat transfer takes place between hot flue gases and feed water. In case of the economizer, heat transfer just between hot flue gases and feed water. Similarly, next is steam condenser. In case of the steam condenser, the steam continuously condenses and heat transfer takes place between the steam and cooling water, the water which comes in the use of condensation. Next is radiator, and in the radiator the heat transfer takes place between the hot water and whatever the atmospheric air. And similarly, cooling tower. Cooling tower you have seen, I think, hot water and atmospheric air. Evaporator, in case atmospheric air and refrigerants, like in our fridges, there is an evaporator in which the refrigerant and atmospheric air exchanges their heat. Now, when we have this simple heat exchanger is very easy topic. It's just an application of the conduction, convection and this. So what I want to say, it is an open system steady flow adiabatic device in which two flowing fluid exchanges their heat without losing any amount of heat to the system and surrounding. Now, how many types of heat exchangers are there? We have three types of the heat exchangers. One is known as direct contact type, another is known as direct transfer type, and third one is known as regenerative type. So in case of the direct contact type, we simply says hot and cold fluid directly mix with each other. So in case of in the direct contact type, hot and colder fluid directly mix with each other and exchanges their heat. These types of the heat exchangers are known as direct contact type heat exchanger. And in case of the direct transfer type, hot and cold fluid do not mix with each other but transfer their heat between them with the help of a separating wall. So they transfer their heat with the help of a separating wall, and these types of the heat exchanger are known as direct transfer type. For example, steam condenser. And the next one is regenerative type. If I just talk about next one is regenerative type. In the regenerative type, we simply take a high heat capacity cellulose matrix. And in the high heat capacity cellulose matrix, what we do? We just simply enter the colder fluid or hotter fluid, and hotter fluid just entered and it loses its heat to this cellulose matrix. This is high heat capacity cellulose matrix which generally absorb the heat of the hotter fluid, and when it comes out in the form of colder fluid, again the colder fluid alternatively they passes and colder fluid absorb this heat which is absorbed from the hotter fluid. So one by one, alternatively hotter and colder fluid passes and they exchanges their heat. In this case, this regenerative type, there is one more case in which we get the rotating shaft type, in which shaft continuously rotated and hotter and colder fluid passes like this and they exchanges their heat like this. So these are the three types of the heat exchangers. We just need to know the basic. What are the heat exchangers? Now in that case, these direct contact, direct transfer type of the heat exchanger we have to study. I think you know very well. So these are the direct transfer type of heat exchanger. In these types of the heat exchanger, there are three types of the heat exchanger. One is known as parallel flow or co-current type. Another is known as counter flow or counter current type. So what is parallel flow? In case of the parallel flow, the hotter and colder fluid both flow parallelly and in the same direction. Both hotter and colder fluid flow parallelly
and in the same direction. And in case of the counter flow, both hotter and colder fluid flow parallelly but in opposite direction. If hotter fluid is flowing like this, colder fluid is flowing like this. Now we are just making the temperature profiles over here. You can easily understand that temperature of the hotter fluid will continuously go down and temperature of the colder fluid will continuously increases. So temperature of the hotter fluid will decrease and temperature of the colder fluid will increase. And in case of the counter current, as hotter fluid is going like this, colder fluid is entering from here. And if the colder fluid is entering from here, the temperature of the colder fluid will increase continuously and temperature of the hotter fluid will decrease continuously. So we will get the two types of the temperature profile in case of the counter current and in case of the parallel flow. Now there is one more type, that is known as cross flow, in which hotter and colder fluid flow perpendicularly. So these three types of the heat exchanger we have to study. We will discuss cross flow. Now from here you can easily see that at this point the temperature difference, that is delta T I, is equal to Thi minus The, and at this point the delta Te will be The minus Tce. And if in this case we will say delta Te will be what? The minus Tci, and over here delta Ti is equal to what? Thi minus Tce. So you have to remember what is delta Te and delta Ti and delta Te in the case of counter flow and counter flow and parallel flow. Now one more thing we have to discuss, that in case of the counter flow heat exchanger, the difference is this delta Ti is very high and this difference is going like this. Now what I want to say, it means the mean temperature is continuously varying. So in case of the parallel flow, the variation in the mean temperature is more as compared to the variation in mean temperature in counter flow. As compared to variation in mean, you can see the mean temperature over here will be like this and mean temperature over here will be like this. Now from here we can easily say that in this case the temperature variation is more. It means the parallel flow heat exchanger will be thermodynamically more irreversible as compared to counter flow heat exchanger. Means the counter flow heat exchanger will be more efficient as compared to parallel flow heat exchanger. Means the losses in the counter flow heat exchanger will be less. So simply he will ask you if the area is given. It means it is obvious the delta Tm value for this. You can just see, he will simply ask you, this colder fluid exit temperature cannot cross this. But over here it will increase like this. And you can definitely see it can be greater than The. So what I want to say is simply ask you, can the colder fluid exit temperature greater than the exit temperature of the hotter fluid? Yes, colder fluid exit temperature can be greater than only in case of the counter flow heat exchanger. It is not possible in case of the parallel flow heat exchanger. Parallel flow heat exchanger is less efficient. If we are just saying, we have designed two heat exchangers, one is parallel flow, one is counter flow, and both the heat exchangers have the same area. Which heat exchanger will be more efficient? It will be counter flow heat exchanger. Since the temperature variation is in this case the temperature variation is not so high as compared to this. So thermodynamically this will be more irreversible. Irreversibility in this case will be more as compared to this. So it means if irreversibility is more, it means we will say the entropy generation for this type of the heat exchanger, parallel flow heat exchanger, will be more as compared to the entropy generation in counter flow heat exchanger. So if we are just saying for the same rate of heat transfer, which heat exchanger will take more area? Obviously, it will take parallel flow heat exchanger, since parallel flow heat exchanger is less efficient. So you have to understand, they will ask you 3-4 questions from here and you just try to understand what they are asking. Now from here, what we will use in the heat exchanger part, we will just use the first law of thermodynamics, which is like this: Q minus W is equal to delta H, delta of kinetic energy. We all know the external heat transfer is 0, so we have taken 0. We are aware with this that there is no work transfer, so work transfer is 0. Kinetic energy, whatever the velocity of the fluid, it always remains same, means kinetic energy same. Potential energy will also be same. That's why it will be delta H is equal to 0. But we have to take the delta H of the heat exchanger. It means delta H of the hotter fluid plus delta H of the colder fluid will be 0. So from here we can see rate of decrease of enthalpy of the hotter fluid will be equal to rate of increase of the enthalpy of colder fluid, and change in enthalpy is equal to heat transfer at constant pressure. So whatever the heat transfer takes place in case of the heat exchanger, it is at constant pressure. Now from here, if I just calculate the heat transfer, we can say yes, Q is equal to U into A into delta Tm, where delta Tm is nothing, it is the mean temperature. Now if you will calculate the U, you have the formula like this: 1 by, let's suppose heat exchanger is very new, there is no loss in the heat exchanger. At that time the Q will be calculated by 1 by Hi plus 1 by H2, 1 by H1 plus 1 by H2. But after some time, when the flow takes place, let after 2 years or 3 years, it will be definitely, there will be chemical deposition on the surface or on the separating wall. So on the separating wall on either side there will be chemical deposition, and this chemical deposition is known as falling factor. This phenomena is known as falling. So that's why when we measure the U after 2 years, 3 years, this is known as U dirt, and it is given by 1 by Hi plus F1 plus F2, falling factor on one side and other side, and 1 by S2. And from here, if you just compare with these, you can say U dirt is equal to 1 by U clean plus falling factor on both the sides. Falling factor value can lies between 0.004 to 0.005 like this. So from here you can just calculate the value of U like this. Now you can easily say as time increases, it is obvious falling increases, and as the falling increases, this value of U will decrease. Means as the time increases, as heat exchanger get older and older, the rate of heat transfer will decrease, since the overall heat transfer coefficient is decreasing. So you have to understand, as the time increases or heat exchanger become older, it means the rate of heat transfer will decrease. In this you can also calculate the mean temperature, and the mean temperature formula is like this. It is 1 by A inlet to exit delta T into dA. Either you can write like this: area is equal to what? Width into length. So width into length, and delta D B into dx. So B will be finished, and we are getting like this. So you can use any of the formula to calculate delta Tm. By using this formula, we can calculate the delta Tm parallel LMTD. The most important topic for you. LMTD is what? Logarithmic mean temperature difference. The formula for logarithmic mean temperature difference for parallel flow as well as counter flow, both the cases will be same. It is equal to delta Ti minus delta Te upon ln of delta Ti upon delta Te. But in the counter flow and parallel flow, this delta Ti and delta Te will changes. We have calculated delta Ti and delta Te. So in this case, delta Ti will be what? Delta Ti is what? Thi minus Tci, and over here delta Te is what? It is Thi minus Tce. So from here we can write delta Ti is equal to Thi minus Tci, and delta Te is equal to what? Thi minus TCE. Over here delta Ti will be what? Thi minus TCE, and over here the delta Ti is what? Thi minus TCI. So this is the formula which you have to remember. Most of the time they ask the problem from here. Now in this formula we can use a special case. Case 1 is what? When one of the fluid is undergoing in phase change. Look, when one of the fluid is undergoing in phase change, it means the heat exchanger will totally depends on the one fluid only. Since the fluid which is going in undergoing in phase change, it means that type of the fluid will not have any of the heat capacity. It will not absorb any amount of heat. So from here, that's why we always says when one of the fluid is undergoing in phase change, any type of the heat exchanger you can use, the mean temperature LMTD value for the parallel as well as counter flow will be same. He will simply ask you the case of evaporator or condenser. In a condenser it is this, in a evaporator this. So you just take mean temperature difference, and mean temperature, whether you will calculate parallel flow or you calculate counter flow, you will get the same values. Now coming to the next point, next case is what? When the fluids have equal capacity rate in counter flow heat exchanger. So he is just saying if the fluids have equal capacity rate in counter flow heat exchanger, means he is just simply saying MSCPH is equal to MCCPC. And if you are getting this case, it means the temperature difference will be at each and every point same. And if the temperature difference is same, it means delta Ti will be equal to delta Te, that will be equal to LMTD delta Tm. So when one of the fluid is undergoing in phase change in case of the counter flow heat exchanger, the LMTD value will be simply anywhere the temperature difference between the two fluids. Now, how we will design the heat exchanger? So the designing part of the heat exchanger, we are just saying, it is a LMTD method, and in the LMTD method, he will give you a specific heat of both the fluids, CPH and CPC, mass flow rate of both the fluids, hotter and colder, overall heat transfer coefficient, and any of the three temperatures. And he will simply ask you, when you are designing the heat exchanger, what will be the value of A? Then how you will calculate? I am giving you the steps. What you will do? You will simply write MSCPH Thi minus Dhe is equal to MCCPC TCE minus TCI. This is nothing, it is the heat transfer. This is the heat loss by the hotter fluid, and this is the heat gain by the colder fluid. That will be equal to Q. When you apply this energy balance equation, you will get the fourth temperature. And after getting the fourth temperature, you will just draw the temperature profile. And after drawing the temperature profile, you will first calculate delta Tm for parallel, either for parallel or for counter, whatever the temperature profile. After calculating the delta Tm, you have already calculated Q. You will put Q is equal to U into A into delta Tm. And once you put Q is equal to U into A into delta Tm, you will simply calculate the area. Area is equal to Q by U into delta Tm. Now the condition is how the area we will calculate. Let's suppose he will simply give you a cell and tube heat exchanger. And in case of the cell and tube heat exchanger, let it is a one tube. Let it is a single tube heat exchanger per power. So it means if we are calculating the area, we will simply say the area of the heat exchanger will be what? The surface area. And surface area will be definitely equal to area of the tube. So we write like this, it is equal to area of the tube, that is pi into d into L. And if he is just saying that there are n number of tubes we will use, then the total surface area will be like this. And also he is just saying we will use number of passes. This is one pass, and add another pass, and add another pass. So at different passes, if he is just taking different tubes, so you will take the area will be equal to pi into d into L into number of tubes and number of passes. This is nothing, this is the number of tubes per pass, and these are number of passes. So by using this you can calculate the area. Now one more thing, also he may ask you, you all are aware this mass flow rate is equal to what? It is rho into A into V, and this area is what? It is area of cross section. So it may be he may ask you what is the velocity of the fluid flowing through the heat exchanger. So you will simply write it is equal to rho into area is equal to pi by 4 into d square into velocity. This is for single tube. If there are n number of tubes over here, then you will multiply by the tubes. It is a single tube. If nothing is given, then you will assume it is a single tube. So by using this, you can design the heat exchanger over here. Now coming to the next topic is effectiveness of the heat exchanger. Effectiveness of the heat exchanger is nothing, it is the ratio of actual heat transfer to the maximum heat transfer. And we all are aware with this actual heat transfer, either we can take from the hotter fluid or we can take from the colder fluid, since the heat losses by the hotter fluid will be equal to heat gained by the colder fluid. So we will simply write it is equal to Ms Cph or Thi minus Dhe upon Mc Cpc, Tce minus Tci upon, we are taking Mcp minimum upon Thi minus Tci. So most of the students confused why you are taking this Mcp minimum, Thi minus Tci. We are taking the maximum temperature difference. Look, when you are saying, we are simply saying we have a heat exchanger like this. So this is your Thi, this is your Tci. So for the maximum temperature difference, we will take the maximum temperature difference like this, maximum heat transfer for. Now why I am taking this Mcp minimum? Look, let's suppose this fluid wants to lose 1000 kilowatt of heat. But if this fluid has a capacity of 500, then only it can absorb 500 kilowatt. So the minimum absorption will be what? 500. Or if this fluid has the capacity of 1000 and if it can send only 500, then it means the exchanges will be different.